All right, we're going to go and get started. So hi, everyone. Welcome to the third Explainable AI for Computer Vision workshop. We're really excited to bring it back again this year with an expanded group of organizers. So speaking of which, right there. Okay, so my name is Indu. I'm a master's student at Princeton University, where I recently completed my bachelor's. I work on explainable AI, particularly at the intersection of human-computer interaction and geosciences. I'm joined here by my co-organizers, Sukrit, Jawad, and Pushkar, who will now each introduce themselves.
Hi, I'm Sukrit Rao. I'm a PhD student at the Max Planck Institute for Informatics in Germany. And yeah, I work in the area of explainability currently in vision language models and concept-based explanations. And nice to see all of you here today.
Hey everyone, I'm Jawad. I'm head of research at Hauser in Germany, and my areas of focus are 3D generative models and explainability for generative models.
Hi, I'm Pushkar. I'm a PhD student at Toyota Technological Institute at Chicago. I work in explainability, fairness, and currently interested in text-to-image models and making them more explainable. Have a good workshop.
All right, so now you know the faces to the names, so you can flag us down if you need anything during the workshop. So we started planning for this workshop back in September, and we poured a lot of time and energy into it, so we hope you enjoy. So throughout this workshop, we hope to firstly initiate discussions across industry and academia to identify successes, failures, and priorities in current XAI work. Secondly, examine the strengths, weaknesses, and underlying assumptions of proposed methods and establish best practices in evaluation of these methods. And lastly, discuss the various nuances of explainability and brainstorm ways to build explainable computer vision systems that benefit all involved stakeholders. So here's the first part of the workshop schedule. Everything is also on the website, which is pretty updated. All events are going to take place in this room, except for the poster session and the lunch social, which are highlighted in gray here. So the poster session will be in Arch 4E at those poster board numbers. We'll announce it again later. And then for the lunch social, we're planning to meet back here and then head over to the lunch together if you so wish. And then for the afternoon, we're going to start off with 2 more invited talks, and then we have a spotlight session, our second spotlight session. And again, for the poster session, we'll head back over to Arch 4E. And then we'll wrap up the workshop with our last 2 invited speakers, and then some closing remarks, and actually also a feedback form for what went well, what didn't, and also if you'd like to become involved next year. So speaking of speakers, we're pleased to introduce our invited speaker lineup. We really try to bring speakers who can share different perspectives on explainable AI, particularly on the applications of XAI, from human-computer interaction to obviously computer vision itself, and even computational biology. Each talk will be 20 minutes long, followed by a 5-minute Q&A, hopefully allowing for a 5-minute buffer between the talks. So please think of any questions as you listen to the talks. Moving on to submissions, we called for papers and demos in 2 tracks. The proceedings track received max 4-page submissions that were published in the CVR workshop proceedings. And the non-proceedings track received max 2-page extended abstracts of published, accepted, or ongoing work. And so here is just a snapshot from the website of our proceedings track papers. And then the website has links to the PDFs of each and also the posters and the short videos if you want to see those. And then here's a snapshot of the 8 extended abstracts that were accepted into the non-proceedings track. All of this obviously would not have been possible without our amazing program committee, our organizers, and also our reviewers who submitted reviews on time and really provided the feedback that our authors could benefit from. So thank you to those of them listed here for really helping make this workshop fall into place. Okay, and then just some more logistics. I already mentioned the times for the invited talks. The spotlight talks will be 8 minutes each, followed by a 2-minute Q&A. And to ask questions, if you're in person, you can come up to this mic or raise your hand. Probably come up to the mic since I don't think we can walk that around the room. And then if you're on Zoom, you can type into the Zoom chat or CUPR's Rocket chat system, and we have an organizer who will be looking at that. For the poster sessions, these will be in person only. For virtual attendees, we'll be playing a 2-minute video loop in this room. But for the in-person one, it'll take place in Arch 4E at boards 279 to 299. And for those of you who have posters, all posters have to go up at the session, not before, and have to be taken down at the end of the session, even though we're actually at the same poster boards for both the morning and afternoon. So you'll have to take it down. Okay, and then finally, in our workshop today, we expect everyone to engage in respectful communication. So we hope to foster an inclusive and respectful conversation between different and potentially conflicting perspectives. So please do not do the following: insult, bully, disparage, shame, or mock others, campaign, fundraise, or lobby for active political candidates or pending legislation, discuss or pressure others to change their religious belief, or share inaccurate or misleading information that could cause fear, disruption, or harm to others. And last but not least, have fun and tag us on X/Twitter. We'd like to know what sort of events you enjoy and would love to amplify your work as much as we can. With that, I'll pass it on to Jawad, who will introduce our first invited speaker.
Thanks very much, Indu. So we're very happy to be joined by Professor Bernd Schiele. He is the Max Planck Director at MPI for Informatics and Professor at Saarland University. He obtained his PhD from IMT Grenoble, France, and has held many positions, including full professor at TU Darmstadt, assistant professor at ETH, and visiting professor at MIT. So his research focuses on addressing really fundamental challenges in image and video understanding, 3D object recognition, and activity recognition. Moreover, he investigates the inherent interpretability present in deep learning. So we're very excited to have him here to talk, to give a talk on inherent interpretability in deep learning in computer vision. Thank you. You take away the...
From the charger.
Stop sharing.
Oh, so good. Could you stop sharing screen? Okay. I'm actually.
That's good. Can you stop sharing? It's still showing.
I'm making you the co-host. Your co-host. And turn on your video.
Yeah. Yes, should I click on video? Sure, use the audio, but let me switch on the camera.
And I have the audio on here.
Yeah.
That's okay.
Okay, yeah, good. Yeah, sorry. Yeah. Yeah, thanks very much for the invitation. It's a pleasure to be here to talk about the inherent interpretability. And let me actually start a bit about motivating how, why we think actually inherent interpretability is sort of a great goal, right? Rather than doing this post-hoc explainability that, you know, the majority of the community is doing. Let me start by sort of, you know, quickly motivating roughly, right, what we want. We want in explainability, right? We want to do obviously not just to classify an output, right? But we really want to have some sort of explanation, and there's many reasons for that, right? And some of this is that we want to gain trust in the in our networks. We might even want to detect all the biases or overcome them, or just, you know, understand better, right? As a debugger, or actually as somebody who's really using the system and understand why a certain prediction has been made. But let me actually recall ourselves, right? One of the important or two important requirements that we really need to think about every time we actually do think about and use explainability. The one is the faithfulness, right? We really want that when we get an explanation from our system, that actually really represents what our system is doing, right? It really represents the kind of processing that happens in the network. And actually, it's surprising how often this is not the case in the kind of explainability methods that we happen to use on a daily basis. And the other part of the game is really having something that is interpretable for us as humans, that really something we can use to understand literally the explanation. And there is many methods out there, right? And there's gradient, right? And you might argue this is faithful. It can be argued if the gradient is faithful as such, but I would argue it's not very interpretable because it's essentially just noise in the image. It's very hard to grasp anything. And there was something guided backpropagation some time ago that has been shown actually this is sort of actually not very faithful, and the way this was done in this paper from Europe, right? Intuitively it's very interpretable. It seems to be very intuitive to look at these images. But if you do this sanity check where they basically are randomized, various layers, literally from the preamp to the back, right, from this network, it happens that this on the right, the explanation actually stays roughly the same if you go from 2 to 5, even to 10 layers. Now this is basically a completely random network, right? And you still see something that is interpretable to us. But remember, this is actually completely random network what the processing is doing. So that set is not really faithful at this point anymore, right? So it's kind of clear that this network is processing something, right? It's literally just random noise, but actually this seems to be highlighting some saliency in the original image and not anything from the network. And there's even go further. We had with Tukot actually, one of its first works was basically really trying to understand sort of different postback attribution methods. If you look at the kind of methods that are out there, there's sort of backpropagation-based ones, there's sort of the activation-based ones with the GraphCam and others, and sort of the occlusion perturbation ones. At the end, right, if you look at those, right, these are all for the same network, right? In principle, they should really show all the same thing if they were faithful, but they're not, right? They're really showing very different stuff, right? So it's clear that not all of them can be faithful, right? And that's really something to keep in mind when we start using those things. And another thing, which is also actually an important question in our community, and still actually is something that is not well understood, is how to really evaluate these kind of attribution methods. Because at the end, you want to show what actually the network is really using, right? But how to evaluate without knowing what it is, right? So somehow there's a chicken and egg problem right here. There has been some attempts here, and I don't really want to talk about this here today, but there have been various attempts to try to address this actually more fundamental. What I want to do though is what I'm talking about today is sort of our journey in sort of trying to rather not using post-hoc attribution methods, but trying to have something that is by design inherently interpretable. And I start with CNNs, but also talk about the transformers. And in the end, I'm also going to talk quickly, if time permits, right, how we can use this to guide models to be right for the right kind of reason. So let me start with this inherent interpretable CNN. This is sort of work in particular from my PhD student Moritz Böhle. And let me just remind us, right, what we want to have something that is faithful and interpretable explanation, right? And for the faithfulness, we have something that we call dynamic linearity. Now, obviously in a slide or two. And at the same time, it's interpretable. For this, we need alignment pressure, or we're using alignment pressure in our network. So let me quickly show you the cost networks that we happen to have. So if you look the network input, basically each of the layers here, that's multiple layers as in any deep neural network, each of these layers gets an input, but the output is actually a linear transformation from the input. This sounds like not very powerful, but the key is it's actually dynamically linear. It's dependent on the input, so it changes depending on what the input is, right? What the linear mapping is. But still, when you have that, right, at the end, because every single layer still just generates a linear mapping from its input to its output, the overall entire network can be basically visualized as a single linear transformation. But still remember, this linear transformation can be different for every single image that we give it, right? But in the end, that means we can summarize the entire network with a single linear transformation. And what I'm showing you on the right is literally what the computation of the network is. If you marginalize over this image, you literally get the logic of the network. So in that sense, this visualization is not just post-hoc attribution or something. This is literally visualizing the computation, right? What generates the logic. That's sort of the difference in a sense than what most other post-hoc methods are doing. And if here, right here for these two birds in this image, right, we get for the goldfinch, we get some 48%. probability, right? And for the bunting, we get 47% probability. So really, both of these computations are faithful in the sense that I'm just marginalizing this image, I literally get the budget for those two birds. So the nice thing of this dynamic linearity is that it allows to faithfully summarize the model. But actually, you might know there's this piecewise linear models, as you will know, right? There's ReLU network, right? In principle, you can also write the dynamic linear mapping from the input to the output, right? Of any of these ReLU networks, and actually is also faithful. However, if you can look at this kind of visualizations, and I don't have examples here today, but if you look at this visualization, they again look very noisy, this kind of gradient-based method I have shown before. So that is dynamic linearity is not enough to get something that is sort of interpretable for us. It's good enough to get us something that is faithful to the model. So there's a second component in our networks, which we call alignment pressure. Let me briefly discuss what this is. So here's the standard linear information, just written as the norm of W, norm of X, and times cosine. Let me slightly rewrite this by sort of pulling out the sign of a cosine. And then our because transformation is essentially taking the cosine to the power of b, right? This is where the name comes from, the because transformation. And we constrain the W to be norm 1. You might wonder, right, what the heck is that changing here, anything, right? Let me show you a toy example here of a two-class problem, right? You have the red class versus the gray class on the left, right? The optimal linear classifier would have sort of the arrow to the right, right? And you would have this minima where for the blue curve is, right, to the, pretty much to the left of this curve on the classic sort of a linear classifier. On the right, you have another gray class against the same red class. And here again, the optimal linear classifier would point, right, with the arrow to the upper left, which is sort of the minima of this green curve. So now this is for the classic linear classifier where b equal 1, right? So that b equal 1 is the classic linear classifier. So now if I increase b, and as I'm doing this in this visualization, what happens that these two basically minima start to coinciding, because now basically this arrow becomes aligned with the input data. Right, so the red class now gets classified optimally, right, when basically it starts aligning. So this is pretty, this visualization here for b equal 20 or 25 at the end. We're using as in practice only b equal 2, but still we're aligning literally, so still this vector with the input dimensions, the input, the images, which really then gives us sort of very sort of intuitive, interpretable results. Let me show you examples of this kind of thing. So here you see the input, right? And again, I'm showing the W matrix that I just talked about, the dynamic linear W matrix that is now aligned with the alignment pressure. If you multiply these two, right, what I'm getting here is literally the output here, the confidence here of the respective classes. If I'm sort of showing this, then sort of intuitive, I would argue these are very detailed, very intuitive explanations of what basically the network is now using, right? It's sort of interpretable for us as humans, and actually it is faithful, right? Because again, I'm literally visualizing a computation here in this case. If I compare this to other methods like breadcrumb, integral gradient, and Sublime, right? So these are clearly not sort of as intuitive for us as humans to interpret, right? So we argue with it that is quite nice also for us as humans, this kind of interpretation in this of this W matrix. And there's also, you get actually quite highly class-specific explanations. And here's sort of there's always two class problems, right? Here on the left, you have the peacock, on the right, you have the cock, and you see sort of the left explanation, the orange one is for the peacock, and the right is for the cock, and then on the very right, you see the difference of the two. You really get a line sort of explanation for these two different classes. Here's another case for the tennis ball and the Rottweiler, so this dog here, right? Again, these are very aligned, right, with the two individual classes. And the third example here again, right, here's two classes to the fence here and the ram. So, and since this, this because transformation actually is applicable, I mean, it's a very standard transformation that we can use for essentially always replacing any of this linear transformation we have in neural networks. This really generalizes it's not just for a single CNN. We have this here for ResNet, DenseNet, and two different versions of ResNet, and also then for a vision transformer. So we are all getting this very similar kind of visualization. And again, these are the computations that these networks perform. So in terms of evaluation, as I said, right, it's a tricky business, right? How do you evaluate sort of these kind of evaluations? What we're using here as a proxy, and it's not perfect, we can discuss this afterwards, is the so-called grid pointing game. What we're doing is looking at the evidence. If you have a 4-class problem with a 2x2 grid, right? We're saying that the upper left corner is where the evidence should come from for the upper left corner class, right? Divided to the divided by the rest of the evidence, right? So and then if you're looking at this kind of evaluation for standard methods, you see the standard post hoc methods, right, from GraphCam over integral gradients and whatnot. They're all not quite as good as the method that we have here, which is very very powerful, pretty close to one actually in this particular case. That again is not just for a single CNN, but also works across multiple CNNs here. And since we are basically having this dynamic linearity, the alignment pressure not just on the last layer, I only showed visualization so far for the last layer, right? But actually that applies to every single neuron, basically in every single layer of the network, right? So we can also visualize what actually the individual neurons, right, sort of correspond to what they're basically firing on. That's exactly what we're doing in this image here. So here you're finding a neuron that basically fires here on wheel type structures. We're having here a neuron that actually fires on face-like structures. Here we have a neuron, which basically, that's sort of an image net. We have sort of a neuron that actually fires on dog faces, which is not too surprising because dogs is a very prominent class in ImageNet. And interestingly, we've also found sort of a watermarking neuron, right, which is something which you don't want, but it happens to be spuriously correlated actually with some class of an ImageNet, which is sort of a perfect thing to do for a network to pick up the spurious correlation of these watermarks and to use it actually for classification. So in that sense, it really is something that you can then also start sort of debugging your network. So what I've shown so far is really, my argument is we really don't want to have deep networks that are both faithful and interpretable, right, in their explanation. And for faithfulness, in our case, we have this dynamic linearity. For interpretability, we have this alignment pressure. And I haven't shown the numbers, but we're actually losing very little performance with the CNNs, which are precausified, which have this precaution transformation in there, and they obviously then provide interpretable explanations for their decisions. Let me move on for just vision transformers, because obviously the vision transformers is something we really want that they happen to be sort of a very prominent thing in our field. And sort of just to remind us, right, so the classic vision transformer has some tokenization, right? They have some projection, has this multi-attention layer, has an MLP and a classifier. These are pretty simple kind of things, right? You can also have a tokenization, which is also CNN-based, for example, right, as an input, which means we really have a tokenization, right, which then often happens to the CNN attention mechanism, sort of MLP and a classifier. These are all the kind of components I have. And if I look at the classic sort of post-hoc explanations like the final attention layer or rollout, that really basically just shows you the attention either from the very last layer or from the entire attention layers across the layer across the network. However, it's actually not very high resolution because it's only at the last layer, really, right? And it's not really a holistic explanation because it only explains the attention layers. It doesn't explain sort of your MLP layers, right, which are an important ingredient, has been shown actually multiple times in various work. So again, we want to have sort of a high resolution holistic explanation. For this, we need to precautify, as you call it, right, or a vision transformer. And here, just as a precursor, right, these are kind of explanations also be getting for vision transformer. But how can we get there? Actually, it's much simpler when one thinks about it, right? Because the tokenizer itself, I mean, we have to have, again, everything to be dynamic linear. Tokenizer, we're using sort of a because CNN, right? Just the CNN that has been sort of the because transformation, and we're done. Right? For the MLP, you can always think of this as a CNN as well, if you like. And the classifier as well is just an MLP essentially. But all these things are already, right, covered from what I always talked about. The last thing that is lacking essentially is the self-attention part. But again, if you think about the self-attention, what it does, it calculates the weighted sum of the values, right, of the input, which again is just a linear transformation. I mean, the attention weights are dependent on the input, which is why we're saying this A of X, right, dependent on the input. But again, it's dynamic linear, depends on the input. Once I have this weight, I can basically sort of again write it down as a dynamic linear equation, the whole thing. And again, I have again this dynamic linearity that I need for the faithfulness of my explanation. Right, and for the purpose of this talk, I'm just going to have a dense net, sort of various layers of a dense net here as the tokenization. And just to give you here some quantitative results as well, right? So here, if you use sort of 13 layers from a dense net as the tokenization, right? On the left, you see the conventional VIT, on the right, you see the because VIT. Actually, here in that particular case, we can even slightly improve performance with our because networks. And if you increase, obviously, the backbone layers for the tokenization, you can also further improve the performance. That is also true for different sizes of my transformer from tiny, small to big. And again, if I look at the interpretability results that we can get for this kind of because transformer, right here on the left, the two basically columns for our method, and then on the right you see the classic sort of postdoc explanation method, which I would argue they're all not quite as convincing as our explanation. Right, and then just to summarize this part here, right? We have this because framework is also compatible with this VITs, right? Because self-attention itself is dynamic linear, as I've argued, right? The remaining modules are essentially just because DNN. We get highly performant results and also highly repeatable results, and again, they're faithful because the way we've constructed this, these are all faithful. So let me come to my last point here in this presentation, then using really the explanation, because remember, right, my explanations are really faithful now to the processing of my network, how to guide sort of my network towards something that I might want the network to be using for its processing. This is work actually from Rao that was published last year at ICD. So the main idea or the gist here is trying to guide models, right, to be right for the right reasons, right? You really want, if you have a, for example, let's take this example here. If you want to detect a bicycle, right, there is often a spurious correlation with a person sitting on the bicycle being a rider, right, of the bicycle. That's the core current that happens many times in the data, and that actually is something that the network picks up and actually uses for detecting bicycles. So basically, whenever there's a person or having a person in a sort of rider pose, it actually sort of hypothesizes there's a bicycle. And obviously, that generalizes not quite as nicely to sort of a bicycle without a rider on top. And there's one example, if I don't know if you know this waterbird data set where you have sort of land birds on land and water birds on water, right? Where there really is spurious correlation by construction in this data set. And sure enough, right, you see the spurious correlation at the background is picked up by the network, right, as sort of a basis for classification. So what we're doing is basically we're doing beyond the classic classification loss, right, for our network. Now we're basically guiding basically the network to basically focus on the foreground. In that particular case, we're using bounding boxes. We're using actually to guide the network to be, guiding using the foregrounds, right, of the image, right, to really sort of do the kind of classification. And again, right, since I basically know that the explanation is faithful, I know that the network really will really then focus on the foreground part here. And the way to do this actually, this is actually often or sometimes people have been doing this with the so-called L1 objective. You're saying sort of you have a bounding box and you say sort of the explanation of the foreground should be basically all of the object should be all in this bounding box. What happens is that you basically then start flooding the bounding box, because some of the bounding box might be not relevant for your task at hand, right? So it might really also take the borders or actually background regions into account for actually sort of focusing on those. And we came up with a new, what we call an energy objective guidance, where you basically look actually that the foreground within the bounding box should be higher with respect to the rest of the background. But I don't care if actually there is still also low values in the foreground. It has only be stronger in the foreground than in the background. So that actually gives you, for example, in this case for the bicycle, a much more convincing, I would argue, right, kind of a feature representation, which is also closer to what the original network had been doing, right? This sort of in the denominator of this equation. Just to give you more examples of this kind of guidance thing, right? So here at the top we have, before this guidance, right, the kind of features that are used, right, or which kind of mapping is actually created for doing the classification. When you do this energy minimization, right, you're getting more convincing, more localized, right, and really sort of highly detailed, visualizations of what features are used. And we came up here sort of a way also with this so-called EPG score to evaluate how much we're improving, right? And here to Kaya said, I'm not going to go into details of this particular evaluation, but the bottom line of the story is that we can really sort of essentially keep the performance or very slightly lose performance while really guiding it to the foreground and still actually gaining sort of a lot of interpretability scores here. Okay, so let me just, if I have still a minute, try to give you all this waterbird example here. So here, as I said, there's during training, you have land birds on land and you have water birds on water. And if you basically, and that's a construction, right? Sort of a synthetic data that you literally stamp out sort of the individual bird, right, and put them on the respective backgrounds. So if you look at the standard network, right, it does classification correctly on this, but actually if you see sort of the visualization, it really uses a lot of background, right? So here in the top row, and it even becomes more apparent, right? If you look actually sort of the water birds and water, it really uses the water information right in the background to do the classification. And not surprisingly, if you go then to the test data where you now basically have the two cases Also, where you have land birds on water and water birds on land, so you have sort of what they call the worst setting, right? The opposite, where the spirit relations now basically kill you if you have them picked up, right? So then, sure enough, in the classic setting, right, you basically do not classify that correctly. And if you basically now do this guidance, right, that you really focus on the foregrounds objects here, right, you're not only getting them right, and sort of the visualizations are more really focused on the foreground, but you're also getting it in this worst setting, right, the right classification and also for the right reason, right? Okay, so then let me summarize. So what I made the argument here is we really should think about sort of having faithful, interpretable explanations as a goal, really as a goal for our communities for deep neural networks. What I talked about is this inherent repeatable networks, right? Particularly because ENNs and because BITs that said, right, have the dynamic linearity for faithfulness and alignment pressure for interpretability. And I also showed an example where we can now use this kind of explanation to guide networks to basically focus on the foreground. With that, I'll thank you very much for your attention.
So we have time for questions. Please come up to the microphone over there or type it in the Zoom chat.
Thank you for the talk. So my question is humans don't perceive the world as pixels, and most of the all the explanations are pixel based. And so, how do you think about pixel based explanations as being really useful for humans, especially non-technical users, and what's the potential in these types of explanations?
No, very good question. So what we have here is the faithful explanation as you said in pixel space, and we don't have it in sort of concept space, where we don't have sort of an explanation. It uses really sort of the head of the bird or sort of the tail of the bird or something like this. That's exactly where the concept bottleneck kind of models are coming in, and Stuttgart has been sort of working on this, right, in the last couple of months. This is really where we see, once we have this, let's say, concept sort of extraction, right, where we can really, again, link it back to the image, right, and then you can name it, right, and you're getting closer to what you want, right? You can also explain it in words. So this word explanation, where linking it to semantics that humans can understand, I fully agree. That's something that is not here in this kind of work. But still, right, I still think when you do these kind of works, which are out there, right, so they often, again, don't really sort of faithful, right, attribute where the concept comes from. So I think, again, the argument I'm making, so you're right, I mean, there's a dimension that I'm currently not covering here, but that's a dimension that actually still, the faithfulness still applies here as an important ingredient, and then the repeatability, really, we want to make a step towards more semantic concept. Absolutely, yeah.
But just to follow up, you're saying that if we can build faithfulness in the pixel space, then we can build upon that to.
I would argue it's a necessary condition, right, to move forward. That's sort of the argument I'm making.
Thank you.
Yeah.
Yeah. Go ahead.
Very much for the talk. I have two questions. I'm not familiar with Vico's networks. So is the network itself, is it possible to convert it into a linear model, or is it your approximation that we want?
No, I mean, the because network itself is not a linear model, right? Because at the end, it would be too simplistic. Linear models will be not powerful enough, right? So in that sense, it still, I mean, it still has a lot of nonlinearities in here. Actually, the one nonlinearity it has is the because transformation itself. We actually skip, well, we can't skip all the other nonlinearities. We also have it combined with reload, but doesn't really change the performance so much. But the point is that you still need these nonlinearities to have a powerful classifier or, model, right? So you can't just extract sort of a single linear model that actually does it all. Right, that you can't do.
Otherwise, you don't need the whole.
Exactly. So that's what the dynamic linear part is.
So you approximate each nonlinear layer with linear.
It's not an approximation. It's exact. So I mean, the easiest that most people know about is ReLU, right? In ReLU, actually, on the left, right, it has sort of on the negative has 0, right? On the right, it's sort of identity. If you every single of those transformations, you add them up, right? You have a linear transformation from input to output. But since the activation function depends on the, on the convolutions you have, right? Still, you can still write down an exact linear mapping from input to output. It's no approximation. It's exact. That's critical. You can do this also for ReLU networks, right? So it's just that, as I argued, right? So I should really show that ReLU networks, the kind of visualizations you're getting are very noisy. They're looking very much like the gradient, right? That I showed there very initially, right? So that's which is why this alignment pressure is so important, right? To add, or some additional ingredient in our case is the alignment pressure, basically to make this linear mapping also, interpretable for us as humans.
second question. You mentioned interpretability, but in my wording would translate to intelligibility because it's usually used for the whole model. Did you study or are you planning to study the model level interpretability?
So what do you mean by the model? I mean, this is what I'm showing here for the entire model, right?
Yeah, I understand. As the image itself should be interpretable or intelligible rather than overlaying, for example, a graph and a pixel attribution. But did you use something like network dissection on the model, Vicos network or transform network, to understand whether the units correspond to commonly understandable?
So I think what I showed here, right, is the closest to this, right? So I mean, this kind of things are essentially network dissection thing, right? Here you're looking at single neuron, what they're giving you, right? So in that sense, that's close to what network dissection does, right? And again, as I said, right, you don't have that. The complete visualization that were at the beginning, right? This visualization on the right is just from the full network, right? The last layer, right? Again, right? What the entire network has been computing, but visualizing from the last layer to the front. I can do this for every other layer earlier as well, so which is what the network dissection would do.
Any other in-person questions? Any Zoom questions? Okay, I actually just have one quick question. Recently I've also been working with a birding data set, and something I hear from a lot of birders is that they actually do want to know about what environment the bird is in to classify it, so like whether or not it's on the ground or in a tree. So I was wondering, do you have any thoughts on how well the foreground selection is?
Yeah, I mean, to me, this is actually a more general thing. Like, there's actually these two, for simplicity, I only talked about the one setting where you really care about the foreground. But actually, if you have water bird on water, it's actually not clear if you label it as, let's say, water, is the bird mentioned or is the background mentioned, right? So in that sense, actually, there's this reverse setting, right? And again, right, you can guide this to that. But more generally speaking, I think what we here doing is really you're choosing the information that the network should use, right? Which is the foreground. But what we really want, I guess, at the end of the day, is sort of a factorization, right? How much comes from the foreground and how much comes from the background, and make it more explicit. I mean, at the end of the day, we are training this basically as a posteriori probability kind of estimation, right? And there we basically mix everything in, right? So we really should, in my view, really have this disentanglement of foreground and background, which we haven't done in this particular work, but in principle, I can think of it, right? So you're having a separation of what comes from, the bird itself when it comes from the background.
And then do you think like sort of human in the loop training might help with that?
Sure. No, absolutely. I mean, this is one of the things one could definitely imagine, right? Because again, once you have, the guarantee that actually what is used to really see, right? You can have obviously also look in the.
Thank you.
Now?
Yeah.
Kristen is also online.
Yeah.
Next speaker.
Wait. 1 minute.
Yeah, okay. Thank you very much once again. We'll be great and talk. So we'll take a 5-minute break and we'll be back at 10 for Chris' talk.
No, because the reason is that people.
Yeah, that's right.
Right. And then you can just keep your video on, by the way. He's online now.
Hey, can you hear me?
Yeah, we can hear you. Thank you for coming.
Awesome. No, thank you for having me, and sorry that I cannot join in person. I'm
We're
jealous.
taking a break, and then we'll have you start at around 10.
Yeah,
10 a.m.
sure.
here.
This microphone goes. Yes.
Well, maybe not yet, because you have to introduce.
Oh yeah, then I hold it down there.
Yeah.
That's how we're doing it. Okay.
Yeah.
Videos.
Hmm?
Video.
Yeah, but also he's on Zoom, so yeah. actually works. Just use it.
Yes, it's not funny.
Oh, I thought it was. So it's not, everyone comes to the session.
No, it's okay.
Yeah.
I need to meet you.
For the-
Okay.
And that's all on our, I believe it's on Thursday, but otherwise, we're gonna announce it again.
Okay. So I'll sign up for this session to go and hang the phone right now.
So after this session, I forgot the schedule. I think after this session, we have. Okay, after this, we have, after Christian's talk, we have spotlight.
Yeah.
And then after that.
Okay, yeah, after.
Go, yeah.
Okay. Thanks a lot.
Can you read it from?
It's fine. I'm paraphrasing anyway, but
It's fine.
it's good. Yeah.
Well, it actually doesn't matter because Christian's online, so his video is gonna show up there, so this one doesn't matter.
Oh, okay, so,
Yeah, you'll just go there.
that's good.
Yeah.
It's just something like that. Christian, can you say something? Just say testing.
Sure, happy to say something. Can you hear me?
He shows up. Okay, cool. Thank you.
Great, thank you.
Let's go ahead and starting to do.
Okay. All right, then moving along to our next speaker, Professor Christian Kersting. He serves as the co-director of the Hessian Center for AI, also head of research department, foundation of systematic AI at the German Research Center for KI of AI, and professor for AI and machine learning at TU Darmstadt. So he got his PhD from University of Freiburg, and since then he has held many research positions at several institutes such as MIT and Fraunhofer IAIS. In 2019, he received the German AI Award. And his research interests include interpretable machine learning, with recent investigations on editable policies within reinforcement learning. So we're really honored to have him here with us today, and he'll be talking on reasonable AI. Christian, you can go ahead and start.
Thank you. I hope you can see my slides, and thank you for the invitation. I'm very, very sorry to not be there. And thanks for Bernd, for this wonderful talk. I guess we can make use of many of his results as on our research. So what I would love to talk about is really, well, essentially the story is that the game is not over, and that this community of the workshop is very, very central for the next generation of AI systems. Before going there, let me also give you a warning. You may see some images that some people may feel are inappropriate, and I can guarantee you the next image you will see is not inappropriate. Though
Wait,
some
hold on just a second. It disconnected the microphone.
Oh, okay.
The microphone disconnected.
Should I say something to test?
Just a second. I need to
Yeah.
reconnect it to the laptop. Is that one gonna?
Yeah. Does it work?
It's not. Wait, hold on. It's not showing up here. Should I rejoin?
Yeah.
Okay, I'm gonna have to make someone a host. Okay, I'm going to make. And just unmuted. Let's try this again. Is that one working?
Okay,
Yeah, but it's not showing.
it's not showing.
Let's see. Is it connected? Okay. Sorry, Christian, just give us a few
Oh,
minutes.
fine. Yeah,
Thank you.
go ahead.
What does it normally show? What's the
It usually has emeet M2. Sure. I'm gonna reclaim myself as a host. Okay, are we absolutely sure it's not showing up here?
Just switch.
Okay. Here you go.
Recording in progress.
Yeah, I'm muted.
Hello, test.
Okay.
Hello, test.
Okay. Turn on your video.
Yeah, better.
For now, yes.
All right. Okay, test, see if they can hear us.
Christian, can you say something now?
Sure, happy to say test, 1, 2, 3.
Perfect.
Great. You can
All right,
continue.
continue. Sorry about that.
It's okay. So I guess game is not over in the real sense. Well, anyhow, so the game is not over. And I want to argue that this community is super central for the next generation of AI. But let's start now the story a bit. So I guess all of you have heard about this kind of fight even between symbolic people, neural people, whatever. I think actually that this fight is beside the point, because ultimately what we are talking about is white box and black box. And whether you now say the black box is neural, symbolic methods can be very black box as well. So I really think it's about having a black box model that somehow can trigger a white box model or help to communicate via a white box model or whatever. This is, I guess, what we really have to work on. So this is triggered by this overall story that some people saying, well, the game is over like Nando, and it's because we have all these successes by just attention and scaling, and you need enough compute. And to be honest, of course, my group and I have also contributed to that. For example, at ICML, we were looking together with Chris and Che, for example, and Stefano and many others. We were looking at, can we also help coming up with these large architectures by maybe trying out a kind of AutoML, or you can also say architecture search on smaller indicative architectures that tell us via scaling laws something about if we then scale up. Because we try to still get larger models. And we have also contributed because we are in a lucky position that we have our own superpod model called 42. So it may take sometimes a bit longer, but we hope that we always find the right solution. But it's because we strongly believe that getting the right people at the right place means that you also need the infrastructure. And with that, within roughly half a year, a bit longer than half a year, we got also quite a number of different models already trained. Of course, not really from scratch, but quite often fine-tuned also in an interesting way. So I'm in particular happy about Aurora M, that some of my students contributed there, because I think we really have to somehow make sure that these models agree with what we as society come up with as rules. And this becomes even more important because many people think it's not just about AI. There are GPT moments of human behavior. And this goes back into a strong debate that actually argued saying that human behavior is so complicated. There's so much different human behavior that we cannot expect to just come up with this one model explaining all kind of human behavior. And there's a very interesting paper by Patterson et al. That argued because of that, we should also just collect enough and a large set of human behavior here, for example, economic decisions of humans, and then apply some deep learning to get new models of human decision making. So in a sense, trying to capture theories of how humans are doing, making decisions implicitly via the data, because only the data can capture this huge variety of behavior. To be honest, I don't believe in that, and I'm a bit scared. I mean, I like the paper, and it's wow to go into that direction, but I'm also a bit scared because there's also Karl Popper that has already argued all observations and actions are hypothesis driven, and I think it's not just about, you know, coming up with human looking like behavior, but also understanding and explaining and trying to get the reasons for that behavior. And so we had a look at that paper and then the data, and it turns out actually that that particular approach might be better explained by a huge, strong data set bias, because essentially they were overfitting on the larger data set, and the other data sets were, in terms of distributions that were taken in the lab, are quite different. So that is already maybe indicative that, yes, indeed, we can do a lot with with large models, large data, but it might also go something wrong. And I guess also in the computer vision community, we may know that something goes wrong. Here, for example, you can figure out that in some of the data sets we are using, you may find the 4 horsemen, but then if you're asked, for example, stable diffusion for the 4 horsewomen, you get this bias in there that unfortunately most women in stable diffusion, if you don't take care, they're kind of naked. It's always somehow disturbing. And then what we did at CVPR last year and also at NeurIPS with a lot of work is showing that you can actually steer the diffusion process in a way that somehow you try at least empirically reduce the probability of getting hate, harassment, violence, self-harm, and so on. So what I want to tell you simply is really to get Gen AI right, we need to know how it can go wrong. But to understand how it can go wrong means also in the long run that we have to make assumptions on what is right and what is wrong. And that's pretty tough. I mean, we are living in societies, and the societies are maybe defining what is right and what is wrong. There are cultural biases, and maybe we can't even easily put this knowledge in there. And my argument is a bit like Daniel Kahneman, who argued we have system 1 and system 2, meaning we have something that is maybe more really doing long-term reasoning and something that is just reacting to what is going on. We also need that, and I call that explainable, respectively interpretable. And I think in the long run, we need a blending of these 2 terms. And I'm coming from a slightly different perspective than Bernd, because for me, explainability is more, for example, something like relevance, propagation, and interpretability is that the model per se is more interpretable. So it's a bit more like Cynthia Rudin's view on these 2 terms. Overall, I hope with that we can get something like a reasonable AI where we can get learning and reasoning together. And because we have both of them, we can have both explainability and interpretability. And of course, I also would like to get more of composability, so we get software engineering ideas in there again. So explainability, first step, if you have large models, in particular multimodal ones, then explainability, even if you do something like relevance propagation or GradCam or whatever, it's not easy because you need extra memory. And here, this is one model deployed by Aleph Alpha. Maybe you can't afford additional memory. So our idea is then, okay, we trade off memory by running several forward iterations. And by that, in a sense, getting an empirical evaluation or simulation of an influence function. So we were wondering, if I change this input, how much is the output or the embedding changing? So yes, we are doing it on the attention scores, and I think it might be very interesting to plug in our B-course layers also in here. If you think now, explaining a black box model is nice, but it's not everything, because quite a lot can go wrong. And you may have seen all these debates on X, but also at conferences. Do we need symbols? Do we need reasoning? Do we need neural symbolic? What does it mean to be neural symbolic? Is it hybrid? Whatever. Here are just some examples in a recent Alice in Wonderland paper arguing that many of the current large-scale models can't do even very, very simple logical reasoning. So it's a bit of it's sad if people tell us next year we have AGI and then there's a paper showing that very simple reasoning can't be done. So as said, my argument is let's do blending of explainability and interpretability. And let me tell you now a bit what that means. So interpretability, for example, could be really a programmatic interpretability. So you ask to get a representation of a visual concept in terms of a program. Let's abstract a bit and let's say it's a lambda calculus, expression in lambda calculus. And that's what we did. It's a follow-up work of all what Josh Tenenbaum's group and many others have done. And here we go to the extreme and really say, via a program synthesizer, we really not want to get just a distribution over programs, but a concrete single program. And it's doable. Maybe it's not always doable, but here is definitely doable. And that's nice because they can now use any kind of, here, if it's lambda calculus, you may map it to Python and you get directly also a reasoner. You can check, is it really true? And it's because we can make use of neural kind of smart sensors. So neural models that tell us something about the image, and we combine it directly with a symbolic reasoning. If you don't like this very harsh neural plus symbolic, you can also have a differentiable, for example, here logic. So what we are doing essentially, think of it, it's not exactly true, but think of it, you replace all the discrete choices in a logic forward reasoner. You can replace by something like a gamble trick into something that is fully differentiable. Think of it like that a bit. And you can do the same even if you now try out in a forward search. So here it's a beam search. You can also try that out for learning the rules. So overall, we can present to you a fully differentiable rule learning system that you can now make use together with another neural system, whatever you want to use as, for example, you can use YOLO here to understand rather complex scenarios like in Clever, and trying to learn from few examples now really a logical concept, at least an approximation, because maybe the probability for the concept will only converge towards one. Why is that interesting? Well, if you can not only do static image analysis, you can also put it into, for example, games, some kind of videos. And that's what we have shown, because if you check out some of the arcades, you actually make use of your common sense reasoning. If you see a key and if you see a door, you as a human, you know, pick up the key, go to the door. So you make use of implicit knowledge that is maybe not written even in the manual. So we can try to extract this now or tell the system in a background knowledge fashion. So what we are doing is we use a neural policy. We extract from the neural policy a differentiable logical policy, and then we can make use of background knowledge about the semantics to get an even better policy in the long run. And what we are currently doing is to even learn a logical policy, a logical formula or program together with a deep network learner like PPO or Rainbow or whatever you want to use. And if you do that, you get actually very interesting behavior. So on the right-hand side, the little video, that's what you get if you just try to use neural PPO policy learning. or you learn the policy via PPO, and you see that the submarine is just trying to kill all the sharks. By that, in the early stage of the game, you get a lot of points, right? It's very attractive, but you forget about getting oxygen. And so at some point, you simply die. If you, however, make use of both a pixel-based representation of the policy plus some guidance in a logical policy, and then you try to balance when to use which one, you learn, in a sense, in this situation, you use the logical one, here you use the pixel-based, then all of a sudden you see this behavior of trying to collect enough divers and then even go and surface in order to get oxygen and to also rescue the divers. So in the long run, you get actually much more points. And I think this is what we really should appreciate in the long run as a community, that it's not neural deep versus symbolic, whatever symbolic exactly means, but it's really the combination. And if you don't like symbols, go for a differentiable symbol, a symbolic system, then you're essentially like any neural network. Here's another example for the computer vision community. If you look at SAM and you would like to do a prompt-based segmentation here, and you would like to have something like give me all the objects that are holding an umbrella that are on the boat, then this is what standard methods are giving you, because the concept of the boat is so dominating that you don't get what you actually want to get. If you then combine with a logical reasoner, which is differentiable again, then all of a sudden you get actually what you want. So I think it also illustrates, for sure, maybe you get lucky with more data to get the right answer, but I guess it's much easier to make use of scene graph generators and also mappings of natural language to logic, and then doing a bit of segmentation and logical reasoning together. So essentially, you're making use of the differentiable forward chainer to give you constraints on the segmentation that should be respected. And if you'd like to know more about that, check out also our Alice program on semantics, symbolic and interpretable machine. However, I also don't think that it's really just about machines and enough data and maybe enough knowledge. It's also in the previous talk, in the discussion round, question round, we also ask in a sense, oh, how do you get maybe the human in there? Because we humans in particular, if we are experts, we are like infinite data. And there's this very classical paper by now talking about the clever Hans moments, and you can find them in images and textual information. You can find it almost everywhere, and it's clear because you can overfit. What we did is we moved beyond this paper, because it's not enough to simply say, oh, this is wrong, but as also Bernd pointed out, we would like to correct. And so we put the system into a loop by providing feedback, very much like he did in his second part of the talk. We can provide feedback on saying, okay, yeah, your prediction is right, but the reason is wrong, and now please correct. And we can do that also in an interactive way, or you provide, let's say, a programmatic model that is telling you maybe what you think is the truth. And this is not only one single approach, but you can, of course, combine now different approaches. You can use GradCam, you can use relevance propagation, you can use different loss functions, and also different approaches on how to provide the feedback and how to incorporate the feedback. And of course, you can also make use of because. We haven't done it, but I think it would be very, very interesting. So roughly, just to give you an intuition of how it works, have a look at the classical husky or wolf example. And let's say here you say, yes, indeed, it's correct that you say that this is a husky, but definitely not because of the pixel that you tell me are the reasons for telling it's a husky, right? There is a correlation with the snow, and you should not use the confounder of snow, but rather focus on other parts in the image. So what you can now say is don't use them, right? You give feedback, and you can incorporate this feedback in different ways. You can go for a differentiable loss. That's what Finalis Doshi's group did originally. But you can also do it by sampling now different versions where you try to decorrelate the part that you shouldn't use. So you replace the part that you shouldn't use by random noise, essentially, and you try to get different versions of that. Now, moving beyond that, because I'm fully with Bernd, that we should not just think of heat maps as explanations. I mean, I'm also explaining a lot to you, not by heat maps only, but also by slides. So I think also by talking, by language. So we may have to move very much beyond heat maps. And here's an example. If you use, again, Clever, and you know that the concept that you're looking for is something like there's a large cube and a large cylinder, then you can go for a CNN, and of course the explanation is wrong in terms of a heat map. You can even try to get now something like SIL in a very simple way, but it's super hard because there's no way of extracting the conceptual level here. You can try to use something like a neural symbolic learner. So here we used a very simple set transformer plus some logical rules. But without feedback, it can, of course, also overfit and get it completely wrong, right? Here it's kind of the inverse. So it's a confounder that we may have introduced as well. And only if you do both a reasoning system and now providing what we did before, but now on both levels, the visual level as well as a logical level that may then even generalize across different examples, you can get overall the answer correct. So again, I feel like, although here it's computer vision, we have to think about other modalities and other ways of making use of explanations. And so other forms of explanation, how to make use of them in an interactive way. And even there, it's maybe that we do not have to use all explanations all the time. Now, don't be afraid. You don't have to go completely neural symbolic. You can also maybe go halfway. And so we had a look at concept bottlenecks, which try to map whatever you have as an image into a concept space, right? So essentially you get also attribute values vectors, but that hopefully carry some meaning for you. Now, what Percy and others did then is to say, okay, now that is cool. I can intervene, what they call intervention. It's not a causal intervention.
Hold on. Sorry, Christian. I think the audio is not working again. Sorry.
Okay. No, it's okay. It's an intervention. It's fine.
Oh, it's actually.
It's frozen.
Am I frozen?
Now it's back. Okay. Yep. You're good. Oh.
Okay.
Yep, you're good to go.
Yeah. So thanks for the intervention. I think what we can do is we can now also intervene on this concept level stuff. So you could say, oh, no, actually, that's not a woodpecker, but it's a cardinal. But for that, the wing color should be red, and it's actually red on the image. Now, what was striking to us is that Percy et al., they were all, and others, they were always just staying there, essentially just providing interventions, but never seeing the interventions as a new source for learning. And so what we present at ICML this year is then how to make use of feedback by using something like a retriever. So in the retriever, you can now keep the mistakes, which is how your example looks like in embedding space and how you intervened. And now you override, in a way, the behavior of the original model, and by that correcting and generalizing to other examples. Generally, I think it's very exciting to talk to our models and to interact with our models. And that's what we also did with a multimodal model here by saying, okay, you can use your model and you can ask for what do you see here and why is something maybe bad. So you can ask directly for rationalizations here. So here we used Luminous from Aleph Alpha, but you can use whatever model you want to use, as long as you can then adapt the model. And here we were using use of bottleneck adapters so that we don't have to adapt the whole model again and again, but we can do a more efficient fine-tuning. But what I really like is this example that you can see here, where you can really say, okay, what's going on in this image and why is it bad? And then you get something like, because it hurts. But maybe that's not the best explanation. And then with iterations, you can get actually that you say it is about displaying the act of bullying. And it also shows you that I guess our models really do not have the best understanding of the world. And this is where this community plays a major role, because that's what we are all talking about. If you hear about safety, AI safetiness, if you hear about alignment, I really think we have to talk not only about the technical aspects, but also about how we want to align. And that's why we moved over to the next generation kind of explanations, namely safeguards, where you would like to encode a policy where you say why something is good or bad, and then you take images, and then you say, according to this policy, you ask for a rationale, and you say, is it aligned, or is it okay to provide this answer or not? And I think we have to do much more there, and this has to even be distributed across the world, because what is right or what is wrong is very much in the eye of the beholder, right? So in that sense, let me conclude. I think the game is definitely not over. And I think that we have to think much more about who designs the idle world, whatever idle means. I mean, I have no clue. I think that's the biggest question. It's not just a computer science or AI question. It's I think the whole world works on that. But definitely it's also a question who sets the rule, because in all these discussions, we have to make us aware of our cultural biases, and it's a debate, and it's maybe a moving target that we do here. And what I can say is that we need both explainability and interpretability, meaning if it's a black box model, I can ask for reasons. That's what I call explainability. But I think we need also interpretable models that are, for example, programmatic, so that have a clear semantic, and they are easy to understand even without an extra tool that may explain their decisions. And this is where we need your help, all of our help. And I think it's just exciting, though also a bit scary future ahead. Thank you.
Thank you very much. So now we have time for questions. You can come to the mic here or write your questions in the Zoom chat or comment.
In the meantime, I'll just put a question up. So this is more of like a specific question, I guess, but for the human in the loop process that you were talking about, do you know if there's a way to definitively cap like how many times a human should iterate? Is it just based on their intuition, or is there like a quantitative way to cap that?
So we don't know it yet. We just were lucky enough, and we were iterating long enough, and then we were checking out again. But I think it's a very interesting question. And it should be, in my opinion, related to questions like regrets, and maybe we can connect to continual learning, but now not on the label prediction, but on the explanation level. So in general, what I think lies ahead is a time where we are not just looking at supervision, supervised, unsupervised, whatever. I mean, all on the input output. But I think what we need is input output explanation, and we may learn on the explanation, and we should go for online learning with explanations and new forms of regret. I don't have an answer there yet.
Thank you. Okay, there's an in-person question.
Hi, thank you for the very nice talk. I would like to ask for your opinion about integrating explainability with foundational models. Because, for example, when we see the inherently interpretable models, they're still mostly designed for, let's say, classification, part of like a supervised learning. So how would you say, what would be your opinion? How would this develop? Thank you.
Yeah, sure. Thank you. Great question. So first of all, I think we have to, and here's an example, right? So here we use just the vision language models of Aleph Alpha, but you can use any other. So I'm full in for we have to get explanations in there. And to be honest, I can't imagine how you can be an AGI, if something like an AGI exists at all, if you cannot explain your behavior. Or so for me, this is central to the question of achieving a smart system. Explanations for me are much more important than input-output predictions, and I'm using us humans as an example. I think I'm enjoying humans not because they can predict things or they do things, but because I can have a discussion with them about interesting things and explanations.
All right, I think that's all the time we have for questions. So another round of applause.
Thank you. Thank you for the invitation, and enjoy the workshop. Great one.
There you go. So we're gonna start with spot.
Okay.
Oh, sorry, first.
Where's the screen?
Do you want to put up the spotlights?
Yes. Just put up the spotlight presentation. Yeah. Okay, so yeah, but I need to time. Okay. Right, so we'll get into the spotlight session. We'll start with we'll have 3 talks now. Each will be 8 minutes, followed by 2 minutes of Q&A. And yeah, so the first talk is going to be recent trends, challenges, and limitations of experimental AI and remote sensing. And this is going to be given by Ivika Obarik. So please welcome and thank you.
Yeah, you can. Yeah.
Yeah,
Okay.
you
Okay.
choose
Sorry. Right. Which is a paper line. Yeah,
You need the paper ID.
no, go ahead.
And let me see. Share your screen on Zoom. And so audio is on, I hope. Is it?
Yeah, just unmute it.
Okay, cool. All right, take it away.
Okay. So hello everyone, my name is Ivica. Hello everyone, my name is Ivica. I'm coming from the Technical University of Munich, and actually I work on Explainable AI for Earth observation. And today I will give an overview of the recent trends, challenges, and limitations of Explainable AI in remote sensing. So to start with, training deep learning models on satellite imagery became a popular approach for tackling nowadays critical problems. As you can see, some of the examples in this slide, such models are used for flood detection, urbanization, or agricultural monitoring. Explainable AI can be essential in supporting this application, as it can enable assessing model trustworthiness, ensuring fairness, and gaining new scientific insights about these processes. As we can see on the right, Explainable AI is increasingly used in remote sensing in the recent years. Basically, it follows a similar trend. So the number of publications of Explainable AI in remote sensing follows a similar trend to the number of publications of machine learning in remote sensing. This increasing usage motivates us to conduct a scoping review of Explainable AI in remote sensing with the goal to identify the state of the art by providing a detailed overview of the current key trends in the field, and at the same time revealing the current challenges and limitations. We did this, but in our approach we followed the PRISMA guideline to obtain transparent and reproducible review process by making the following steps. So first, we performed search queries in 3 established literature databases to collect the works from 2017 until 2023. Afterwards, we did screening and filtering of the papers. And so from 1,075 initial papers, we obtained our final literature database that amount to 207 papers. Out of these works, first we started to summarize them by which application explainability is most often used in remote sensing. As we can see on this graph, in the recent years, there is increasing usage of explainability for applications related to natural hazards or atmosphere monitoring. At the same time, the traditional remote sensing applications, such as land cover mapping, where we want to determine from image if a pixel on the ground is vegetation or built-up area, or atmosphere monitoring, are also being constantly used. Next, we looked at what are the popular explainable methods in remote sensing. And what we can see, which might be a bit surprising, in the last 2 years, there has been a huge increase in the usage of local approximation methods, particularly the Lyman-Sharp approaches. Also, as we can see here on the left of the slide, the backpropagation methods such as GradCam are also highly used. Observing this pattern leads us to the first challenge that we discussed, which is the one towards interpretable neural networks. As it was mentioned in the beginning of today's workshop, in the first talk, this high usage of post hoc approaches can be problematic because, as we know, they are only an approximation to the original model and might not really represent its workings. Further, the attribution-based saliency maps, such as GradCam, might lead to noisy explanations. In recent years, these shortcomings were addressed by developing inherently interpretable models, and in remote sensing, we found the following 4 approaches that are used. So, first, the mostly used are attention networks that use the attention weights to explain the relevant pairwise relationships for the learning task. Second, we have usage of joint training approaches that first predict intermediate interpretable concepts to which the model outcomes are conditioned. Next, also recently, graph neural networks are used that provide intuitive problem representations in terms of objects and relations. And finally, there are a line of works using the backnets. The backnets are interpretable architecture that first split the image into patch, predict logits per patch, and then linearly aggregate to obtain the final prediction. The next challenge that I will discuss comes from the specific properties that are present in remote sensing data. So first, on the left, we have spectral resolution, and very often in remote sensing, there are much more channels than the 3 RGB channels that are present in natural imagery. For example, we have multispectral sensors, such as Landsat, which has 3 to 10 channels, or often there are hyperspectral sensors that contain more than 100 channels. Next, the temporal resolution is. Yes. Next, the temporal resolution is also a fundamental part of many remote sensing problems, as for example, in agriculture monitoring, it's necessary to follow the temporal evolution of a parcel given the calendar year. The third property is the topology, that as every geographical location has its own intricate dependencies, and also there exist different relations specific to the geography. Finally, we have the spatial resolution, as the remote sensing images represent a view from above, so there are a lot of small objects having irregular shapes and boundaries. These specific properties, we found that they are increasingly addressed by adapting the existing explainable methods, and you can see in the last year there has been a spike of such works in the areas, and the highest focus is given on enhancing the localization capability of the class activation maps methods such as Grafton. The final challenge that I will talk about is the evaluation, and in the literature we discriminate between anecdotal evaluation that is usually done on a few examples, quantitative evaluation that attests whether explanation meets set of predefined objective metrics, and user studies. As we can see in this graph, in remote sensing, mostly anecdotal evaluation is performed, with few studies conducting quantitative evaluation and only a single study relying on expert evaluation. In summary, the key trends that we extract is that explainability is increasingly used for critical applications such as monitoring natural hazards or atmosphere and air quality application. And we saw that there is a high usage of local post-hoc approximation methods. And the 3 key challenges that we identified are towards interpretable neural networks, where we see that there are only a few of such approaches in remote sensing. Then the unique properties of the remote sensing data that are usually addressed by adapting the existing XAI methods, and finally the evaluation problem, which we saw that it's barely tackled in remote sensing. With this, I conclude, and thank you for your attention.
So really, we have time for one burning question, please. Okay, good.
Thank you again very much. Right, so we'll move on to second spotlight, and this is spatial sensitive GradCam++, improved visual explanations for object detectors via weighted combinations of gradient maps by Toshinoro. And this is going to be a pre-recorded session, but then after we can have questions. I'll just play the video. Okay. YouTube.
This one?
Yeah, that's it.
Because it can increase model transparency and help in developing better models. Hello, I'm Toshinoro from Hitachi. Today, I'm going to talk about our work, Spatial Sensitive GradCam++, improved visual explanation for object detectors via weighted combination of gradient. Visual explanations are important tasks because it can increase model transparency and help in developing better models. Various methods have been proposed, but most of them focus on image classification, and applying to object detectors is a relatively unexplored area. Unlike classification models, object detectors detect each instance in an image. Therefore, the task of generating heat maps for object detectors, we need to generate instance-specific heat maps which correspond to each detected instance. However, methods which are primarily designed for image classification models such as GradCam typically generate class-specific heat maps that also highlight regions unrelated to the detected instance. So to generate appropriate heat maps for object detector, we need to consider the characteristic of it. In this study, we focus on generating heat maps for object detectors and propose a novel.
Sorry, I just need to pause this. Zoom doesn't have screen share on right
From the
now.
perspective of it.
All right. I can just share this, right?
Yes.
All good. All right, I'm just gonna start it back.
I'm Toshiya from Hitachi. Today, I'm going to talk about our work, Special Sensitive GradCam++, improved visual explanation for object detectors, the weighted combination gradient work. Visual explanations are important tasks because it can increase model transparency and help in developing better models. Various methods have been proposed, but most of them focus on image classification, and applying to object detectors is a relatively unexplored area. Unlike classification models, object detectors detect each instance in an image. Therefore, the task of generating heat maps for object detectors, we need to generate instance-specific heat maps which correspond to each detected instance. However, methods which are primarily designed for image classification models such as GradCam typically generate class-specific heat maps that also highlight regions unrelated to the detected instance. So to generate appropriate heat maps for object detector, we need to consider the characteristic of it. In this study, we focus on generating heat maps for object detectors and propose a novel method. From the perspective of visual explanations for object detectors, some methods have been proposed in recent years. One of the methods is Special Sensitive GradCam, or short SS-GradCam. SS-GradCam is based on GradCam and extended to apply to object detectors. As I will explain later, SS-GradCam generates instance-specific heat maps by considering the spatial importance. However, SS-GradCam may generate heat maps that only highlight a part of important regions for the detected instance, as shown here. In this study, to improve the quality of heat maps, we propose Special Sensitive GradCam++, which improves SS-GradCam. The main idea of the SS-GradCam++ is inspired by GradCam++, which improves GradCam to generate higher quality heat maps for the classification models. As shown here, by incorporating this idea into SS-GradCam, SS-GradCam++ can generate reliable heat maps that more accurately capture the important regions. In the following slide, I will first explain the base method of SS-GradCam, its challenges, and the proposed method is one by one. In this slide, I first explain SS-GradCam, which forms the basis of the proposed method. SS-GradCam is based on GradCam, and it first computes the weight W by taking the average of gradient map. The target of differentiation is the predicted score corresponding to the detected bounding box. This weight W represents the importance of features in the case feature map. Next, SS-GradCam computes the space map S by normalizing the absolute value of gradient map. This space map S indicates the spatial importance of each neuron in the feature maps. Original GradCam computes the heat maps by multiplying the weight W with feature map A, but SS-GradCam modified its multiplied product with space map S. In this manner, SS-GradCam reflects the importance of both feature and space in the final heat maps. This slide summarizes the differences in the heat maps generated by GradCam and SS-GradCam. Again, GradCam generates heat maps by multiplying the weight W with feature map A. Because the weight W is a scalar value and lacks spatial information, GradCam generates class-specific heat maps, which also highlight regions unrelated to detected instance as shown here. On the other hand, SS.CAM modified its multiplied product with spacemap S because the gradients only flow back to the regions related to detected instance. And so this spacemap S can provide special information of detected instance. As a result, SS.CAM can generate instance-specific heat maps as shown here by computing the importance of both features and space. However, a challenge with SS.CAM is that, similar to GradCAM, it computes a weight W basically from the average of the gradient map. In this case, the magnitude of W depends on the spatial size of the feature, and the features with smaller spatial size tend to be less emphasized in the final heat map, resulting in only the out of important regions being highlighted. This problem is also mentioned in the GradCAM++ paper, and to mitigate this problem, GradCAM++ introduced a weighted combination of gradient map to the computation of W. Inspired by this idea, we incorporate this computation into SS.CAM and propose SS.CAM++. So in the proposed method, the weight W, which represents the importance of the features, is defined like this. Here, alpha is the weighting coefficient for each gradient value, so the weight is computed by a weighted combination of gradient map. To get alpha, we assume that the predicted score is computed by this equation. In this assumption, considering the architecture of object detectors, we introduce a binary mask n, which has a value of 1 for regions related to detected instance, and others are 0. If we use faster RCNN and set the last layer of the backbone CNN as visualization target, the binary mask M with 1 corresponds to the loitering area, because the score is computed from features in such regions. By substituting equation W into this score assumption and calculating the second derivative, and we finally get the alpha like this. This slide summarizes the proposed method. For each detected instance, SS.CAM++ first computes the weight W by the weighted combination of gradient map. Then, similar to SS.CAM, the proposed method modifies the multiplied product of the weight W with and the feature map A with space map S to generate instance-specific heat maps. Next, let me explain content results. To evaluate whether the generated heat maps accurately identified important regions, we conducted an evaluation based on deletion and insertion. These metrics evaluate changes in the model's output by deleting or inserting each pixel from the original image or into the empty image based on the generated heat map. At each step, a score is calculated to evaluate the similarity between the original output and output at each step. In this study, we evaluate using the score S1 and S2. Score S1 is the class probability for the predicted class corresponding to detected results. And score S2 is a following equation that takes into account both the class probability and the bounding box corresponding to the detected results. We apply each method to faster RCNN and evaluate it on MS-COCO dataset. The results are summarized in this table. We report area under curve, and lower is better in deletion and higher is better in insertion. As you can see from this table, the proposed method achieves the best value for all metrics. These results indicate that SS.CAM++ generates heat maps that more accurately capture important regions. This slide shows the result of pointing game and energy-based pointing game. These metrics are useful for evaluating the localization of heat maps for each detected instance. As you can see from this table, the proposed method achieves the best values for almost all metrics, which indicates that SS.CAM++ generates highly localized heat maps for each detected instance. Here's a summary of our work. Please come to my poster session and discuss our work. Thank you for your attention.
Okay, so are there any questions for Yoshinori?
can just do one actually. What would you do for future work in terms of evaluation? Are you happy with like these metrics, or would you add anything?
Yeah, basically we evaluate these metrics, and we want to plan to apply the another architecture, right? The fast SSD or also the transform-based architecture such as DTR. All right, yeah.
Okay, thank you so much. We'll move on to the next spotlight.
So the next spotlight is going to be exploring explainability in video action recognition by Shashank Gupta. So please welcome him. Thank you.
Let's see.
Yes. Make sure you wanted them to. Make sure you monitor
the Hi everyone, my name is Shashank, and I'll be presenting our work on exploring explainability in video attribution with my wonderful colleagues from UT Austin. To start off with, while we've all seen that there are many explainability methods for image tasks like classification and detection, as we just saw, when we looked at video, we found that there's very scant work specifically for video. And so if we just directly try to extend attribution methods for images on videos, we found that there are several issues, primarily dealing with the temporal aspect and how attributions change with time, which I'll talk about in my slides. And so instead, what we propose is an extension of TCAP, video TCAP, which provides a more robust alternative and allows you to directly test for temporal correlations in video tasks. For those that are familiar, TCAP has this limitation that you have to generate these concepts. And so we also propose an automated method to generate concepts as part of this framework. And this actually reveals several interesting properties about SOTA models, which I'll also talk. So just to start off with, I'll go over a little bit over GradCam again, especially how it pertains to video. As all of us are familiar, attribution methods tell you how much each input contributes to the output. There are a lot of methods out there, but we found that GradCam is like standard. It's present in a lot of libraries, so we decided to take a look at that further. So to be more specific, we look at how GradCam performs on video swim transformer, which is a SOTA model for video action recognition. Video action recognition is kind of like the analog for image classification. And we're training on Kinetics 400, which is the standard data set for this task. So the first issue that we see is that attributions vary widely between frames. So as you can see in the first one, firstly the tennis racket is highlighted, but in the later frames it seems to disappear. We have things in the background highlighted which don't even seem to be extremely relevant. So there's this wide variation as time goes on, which is very hard to explain. You have unstructured attributions that disappear and reappear. So it's known that GradCam is very noisy, but this kind of ghost attributions which just appear and disappear from different frames is also very hard to interpret. Thirdly, attributions can occasionally just drop out entirely. So in the beginning, you have these rackets which are highlighted, but later on in the clip, rackets seem to play no importance at all. So it's also very hard to, it's basically what I'm getting at, it's very hard to identify temporal correlations or causality or what's going on as time progresses. And besides that, there's also an issue with directionality. Like, is picking up a cup the same as putting it down? One could argue that maybe you play the frames in reverse, and then by reversing it, maybe you'll get some understanding of the impact. But that's only bidirectional, like up and down. So what if you want to identify different types of cup behaviors? Then what do you do then? And then it's also impractical to use at scale for videos, because then you have to look at all of these clips in parallel, which is much easier to do for images, but not practical for videos. So I'll move on to GradCam, which is kind of our proposed solution. And for just as a refresher for what TCAV is, TCAV is like, instead of testing for pixel level attributes as we have in GradCam or attribution methods, it's trying to test for high level properties like the presence of certain objects or textures. So as in this image, the presence of a sign or the presence of a human, it's trying to test for those things. So a concept is defined as like a collection of inputs that are defining some concept. So like, for example, you have a collection of images of stripes. And you can test whether, stripes are important for example, predicting a zebra. And the most important thing is that it tells you, striped versus non-striped, what is the relative importance of having stripes in your image. And the bar graph on the bottom is kind of like the typical output for TCAP. And we'll see more bar graphs like this later, so it's kind of important that this makes sense. So the first thing that we do is we extend TCAP from image classification to video action recognition. And again, we study the video swim transformer to be consistent. And these are like the layers that we probe. So it's kind of basically 3 different levels of depth. Now, we need to, so similarly, we need to design concepts for action recognition. And the important thing here is we just don't want any concepts. We want concepts that can tell you about temporal impact, like temporal, what is going on as the object moves in the video. So we conceptualize 2 types of concepts. So the one is this, like just the spatial level concepts, and the next is the spatio-temporal concepts. So we have just as we said, we have an automated approach to generate the concepts. The static concepts are just crops of like different objects in the videos using YOLO V7. So essentially, it's like this tennis racket crop repeated for 1 second, or like this tennis ball crop repeated for 1 second. And so essentially, what these spatial concepts are doing are just testing for simple presence, like nothing else. Next, we have spatio-temporal concepts, which are just objects tracked across the frames. So now it's no longer just a tennis racket, but how the tennis racket moves when you're trying to play a shot, or how the human moves as they're playing tennis. So again, this is not just testing for presence, but now we're also testing for temporal behavior. And both of these types of concepts were visually verified. And of course, these are limited by the COCO class, like, what you can achieve with YOLO V7. But we found that's pretty broad. So that's not that big of a limitation. So coming to results, so the concepts that we're testing here, like are the person, sports ball, tennis racket, and like a random control concept. So those are like the 4 colors as you can see for each layer. And these are showing you the relative importance at different levels of decision making, like different levels in the neural network. And as you can see, the random concept is important throughout the network. Like it's showing that compared to a random concept, it still has importance even as you go down. So this doesn't mean that random is important. It means that the simple spatial concepts are not particularly informative. You might as well just have something random, and you would still get a similar impact on the final output as you would get from having just the simple presence of a tennis ball or a simple presence of a racket. And the effect of the random concept persists until the last stage, which is also interesting to see. As we move on to spatio-temporal concepts, we see that these have much more predictive power. Like as you can see, as you progress in the layers, the red bar just goes to 0 completely, especially in the last layer. So it's showing you that these temporal concepts are much more distinguishable than random. The importance increases with depth. As you can see, like last layer, it's exclusively temporal concepts. And this is very similar to the human brain, basically how motion is processed in the V5 region of the human brain, which is like the deeper layer in the human brain, versus like just in the V1, which is responsible for initial processing of spatial aspects. So also it's interesting to see that more static objects have less importance. So when you take a crop of a tennis ball, even though it's moving, it will still look static. So as you can see, like towards the end, it's not like in the layer 3, we have almost 0 importance for for sports ball, versus like a person moving around or like a tennis racket moving around has more importance. So that's also very interesting to see. Finally, the acid test, or like what big thing is, what about spatial versus spatio-temporal of the same thing? So here we're looking at like tennis racket and person. So here you can clearly see that like the orange bar, which is the spatio-temporal, is dominating over the blue bar, and especially especially with increase in depth. So it was again at the end of the the classification sort of at the head. It's exclusively that temporal concepts are preferred. And this, so just to kind of recap what we have here is in the GradCam domain, you have this heat maps which are noisy and don't explicitly tell you about temporal correlations. But here you have an explicit test that, okay, I have a spatial something that I think is important, like a tennis racket, versus I have a tennis racket moving when it plays this particular shot. And you have a clear way of telling that, okay, this temporal information was important for the model. And so that's what we found is kind of a powerful idea that we could get from TCAP. So we also verified that this is statistically significant, tried multiple random sets, TCAP scores are consistent. This also does have the foundational issues of TCAP. So TCAP picks up on things which are tangentially related as well. So for example, the presence of a bench is also seen as important if you compare it against a random. But benches could be anywhere, but they're generally seen in tennis courts, so that's why it tries to pick up. But yeah. So in terms of future work, I think what we're looking at is more variety of concepts. Basically, pose estimation can tell us about how humans move within scenes, and you also have like multimodal models which can tell you about language described abstract events, and that would be interesting to see that if we can get clips for abstract events. We want attribution methods that are targeted for videos, not just graph, so similar to what we saw for object detection, but something for video. And metrics also to assess how well you can capture these temporal aspects. That would be an interesting area of work. And I mean, finally, as everyone's been talking about generative AI, like generating concepts here, using diffusion models, for example, or Sora, where you can just type something and you can automatically generate like a batch of concepts and then use that for testing. That reduces a lot of the labor involved in this process. So yeah, that's all. Feel free to scan the QR if you're interested in my paper, and please come back to talk at our poster. We're actively looking for interested collaborators, so we would love to talk if you're interested.
So, is there a question? All right, one question.
So I have a question. Were there any challenges that were associated with segmenting these concepts, spatial temporal concepts, like them appearing, disappearing, or when do they start and when do they end, or things like that?
Yeah, that's a very good question. So we were lucky that the object tracking algorithms are very good. We did do like a sanity check on like just looking at the concepts, but broadly we found that the detections are pretty stable. So we didn't have to do a lot of manual work there. But yeah, there is some filtering that you need to do.
Sorry, another follow-up question. Were most of these spatial temporal concepts just objects, or were there things beyond them as well?
So for this line of work, it's just objects because we're using an object detector. But again, like I said, in future work, we would like to extend it to other kinds of concepts as well. So I think the main aim was like object static versus like object moving. Like how does the temporal aspect of that matter for recognition? So that's the approach we took. Thank you. Thank you.
Okay, so we're going to start our poster session now. This is going to be in person only in Arch 4E, number 279 to 299. We request all presenters to go up there and put up your posters. Please do make sure that you take them down at the end of the session. And for authors who couldn't attend, we will be playing 2-minute videos of their presentations on a loop here. And you can come back to this room at 12 o'clock for our lunch social. If you want, we can go to lunch together, have a discussion, and resume right after lunch. Thank you very much.
You can stay here, stay with the loop that's fine. And then you also do like a point of contact if anyone needs anything here. Pushkar, you go with the authors. I'm also going to come in a bit after I finish some things. And then Sukrit, you'll also come to a poster. So you'll be the only one in this room taking care of that playlist.
Should I remove my laptop? I think I need it.
I'm bringing my stuff just because I might need it. No, I might need it.
Yeah, I think there's no point there.
That's fine.
How much is this thing?
So you have
It's
in the Slack channel. And it'll be on mute, so like there's no sound gonna be playing here.
Today, I will be presenting our work on a semantic
And
approach.
just to make sure it's gonna play the next video when it's done.
So just a quick question. Where can I get the email with all the poster numbers if anybody needs help?
Oh yeah, that's in the Slack channel. It's pinned.
Okay.
Just look at common links.
And the numbers you said from
279 to 299.
279 to 290.
Yeah.
Then do we return here or do we go for lunch?
So if you want to go lunch with us, we meet back at 12 o'clock.
Go to lunch, but I don't know if there will be some presentations right before lunch here.
No. So poster session until 12 o'clock, that's lunch, and then after 1:30 is when we come back.
After 1:30, I have another workshop, but it's very relevant to my research
Oh, great.
and also my teaching. So
Oh, nice.
I'm very much impressed.
I'm happy you enjoyed it.
Yeah. Very useful and it's conversion with it. It's not just a side thing, but it should be more central.
We hope so.
Not only explainability, but interpretivity.
Yeah.
Inherent interpretivity.
Where are you based?
At Utrecht.
Utrecht.
Utrecht University, yes. And
This is in the Netherlands.
then
Ah, yes, nice.
There is a break.
Yes, we're at the poster sessions.
What time will it start again?
So we'll start at, good question. 1 second, let you notice. 1:30 is the next talk. 1:30, yeah. But you're free to go to the poster session in Arch 4E.
In real-world problems, how do we reconcile the desire for diversity and creativity in generated outputs with the need for consistency and coherence relative to the input prompt? By quantifying consistency, we can enable decisions reconciling creativity and consistency for particular applications, detect unintended bias, validate interpretations of model outputs, and enhance user understanding. The semantic consistency score we propose here is a simple approach to this problem that leverages multimodal embedding models with a pairwise mean clip score. To evaluate a model, we have some input prompt, which is used to generate n iterations from a model. In this study, we examined 2 open source models, Stable Diffusion XL and PixArt Alpha. These n iterations are then passed through the clip image encoder, and a pairwise cosine similarity is computed across the embeddings for each iteration. When comparing SDXL and PixArt Alpha, we found that the distributions of consistency scores across the models were significantly different. For each pair of results from the models, human annotators labeled which image was the most consistent. The model with the highest semantic consistency score matched the most common selection among annotators 94% of the time. We also looked at the impact of fine-tuning on the semantic consistency score. The distributions of scores across base SDXL and SDXL fine-tuned on Monet paintings using low-rank adaptation were significantly different. It's important to note that there exist biases in embedding models like CLIP. Alternative models and other consistency methods should be explored. The idea behind this paper is to start the conversation around consistency in diffusion model image generation and posit new ways to harness the power of multimodal embedding models for explainability. All code and data generated for this study are available in GitHub and Hugging Face.
Welcome to our presentation of SUNNY, a visual interpretation framework for convolutional neural networks from a necessary and sufficient perspective. This is a collaborative work by the University of California, Davis, and National Taiwan University. Saliency maps are widely adopted for CNN interpretation, aiming to highlight the most important input features for model decisions. However, existing approaches often focus more on model parameters, overlooking the fundamental why behind their decisions. Aligned with counterfactual thinking intrinsic to human cognition, SUNNY rationalizes CNNs from the causal sufficiency and necessity perspective. Our method considers the input features as hypothetical causes and the model's predictions as outcomes. The causal necessity, N, is measured by the outcome differences when changing the causes, while sufficiency, S, is measured by the outcome stability when specific causes are unchanged. Inspired by Shapley values, we define the NS Shapley values to quantify the causal importance of input features bidirectionally. Our framework starts with a forward pass through the CNN to extract feature maps. Then we obtain corresponding input features and perform interventions by removing or keeping them respectively. Following the definitions, we compute N and S Shapley values. The necessity and sufficiency heat maps are constructed by the weighted integration of feature maps. We evaluate SUNNY on 2 benchmark datasets using 3 different CNN architectures, where we compare SUNNY with 7 baseline methods to assess its effectiveness in providing class discriminative explanations. The quantitative evaluation with metrics such as the deletion insertion and energy pointing games indicates SUNNY's superior performance over competitors. By visually comparing with others and validating the sanity check results, SUNNY's capability of providing high-quality explanations can be further proved. Please check out the full paper for more details.
Hello, my name is Mohammad Reza, and I'm going to present our paper, Allowing Humans to Interactively Guide Machines Where to Look Does Not Always Improve Human AI's Team's Classification Accuracy. In this study, we explore a binary classification task where humans and AI collaborate. The AI receives an image of a bird and provides both a prediction and an explanation for its prediction. The human must then decide to accept or reject AI's decision. Current explanation models only offer one static explanation for each prediction. The question we want to address here is, what if we allow users to interact and manipulate AI attentions to generate more prediction and explanations? We modify CHM core to allow the user to select specific regions on the image, forcing the AI to focus its attention on the chosen region. In this example, the user selects only the body of the bird, which leads to the prediction of summer tanager. After seeing the prediction, the user can decide to include beak, which leads to the correct prediction. We ran a study to measure the effectiveness of this approach and report 2 major findings. First, we found that despite being able to interact with the AI models, AI errors are still very challenging for human users to recognize. This aligns well with previous studies in XAI that show humans, even those with machine learning expertise, are easily fooled into accepting AI predictions. The second finding is interactivity does not improve overall human decision-making accuracy or static explanations. This finding goes against the popular hypothesis from the community that interactivity can improve human AI team accuracy. However, we found that for certain cases, interactivity is indeed more helpful than static explanations. In conclusion, we have open sourced our interactive interface to lay the groundwork for future work, although we did not observe an improvement in human performance. We believe our interface can benefit other user-centric aspects of XAI, such as trust calibration, user satisfaction, and perception.
Hello, and welcome to a brief presentation of our work titled CA Stream, Attention-Based Pooling for Interpretable Image Recognition. What we present is an attention-based pooling mechanism that improves interpretability measurements on existing CNN models. How we do it is we introduce a cross-attention stream that runs in parallel to existing CNN models, updating a class-agnostic representation, a CLS token, with feature maps found at critical stages of a model, generating the representation that is used to replace gap during inference to produce explanations. Overall, our approach improves interpretability measurements of existing CLC map methods. It provides class-agnostic raw attention maps, as well as maintains the recognition properties of each model that we use. We validate qualitatively our experiments using class activation methods on both Pascal and ImageNet datasets, as well as we provide raw attention images on the MIT 67 dataset. This last dataset is important because it highlights the capacity of our class-agnostic raw attention maps to capture salient information from images and classes that it never saw during training. Conversely, regarding the quantitative experiments, we evaluate the interpretable properties following interpretability evaluation of 3 different class activation methods on both ImageNet and Pascal dataset. Experiments here demonstrate that our updated representation provides improvements for interpretability evaluation of different class activation methods, in turn enhancing the interpretable properties that they might convey. We expect to see you in our poster for further details. Thank you.
Why does a model predict an image as private? I'm Miriam, and I will show you which objects influence privacy decisions. Most people don't realize that sharing images online can reveal sensitive information. Designing a tool that warns them and also explains the decision is challenging. We consider a pipeline that first detects objects in an image and then uses a privacy model to recognize if the image is private from these objects. To quantify the influence of objects on models' decisions, we used an explainability method that assigns scores to object features. Here are objects detected in private images correctly classified by a privacy model. The presence of a person influences the model. The number of objects has less impact. Here we show the scores obtained from 2 models on private images correctly classified. Person is the most relevant concept for both models. Interestingly, one model tends to classify images as public when more than 2 people are detected. So we derived 2 classification strategies that are explainable by design. The first one classifies an image as private if at least 1 person is detected. The second one does so if only 1 or 2 people are detected. A high recall in the private class for the first strategy reflects that many private images contain people in the dataset. However, images with people are not always private. If you want to design a privacy model, make sure that it is not biased by the presence of people by comparing it to our person-centric strategies.
Today, I will be presenting our work on a semantic approach to quantifying the consistency of diffusion model image generation. There exists variability in diffusion model image generation due to the stochastic elements inherent to the diffusion process, and there are differences in the level of variability across different models. In real-world problems, how do we reconcile the desire for diversity and creativity in generated outputs with the need for consistency and coherence relative to the input prompt? By quantifying consistency, we can enable decisions reconciling creativity and consistency for particular applications, detect unintended bias, validate interpretations of model outputs, and enhance user understanding. The semantic consistency score we propose here is a simple approach to this problem that leverages multimodal embedding models with a pairwise mean clip score. To evaluate a model, we have some input prompt, which is used to generate n iterations from a model. In this study, we examined two open source models, Stable Diffusion XL and Pixart Alpha. These n iterations are then passed through the clip image encoder, and a pairwise cosine similarity is computed across the embeddings for each iteration. When comparing SDXL and Pixart Alpha, we found that the distributions of consistency scores across the models were significantly different. For each pair of results from the models, human annotators labeled which image was the most consistent. The model with the highest semantic consistency score matched the most common selection among annotators 94% of the time. We also looked at the impact of fine-tuning on the semantic consistency score. The distributions of scores across base SDXL and SDXL fine-tuned on Monet paintings using low-rank adaptation were significantly different. It's important to note that there exist biases in embedding models like CLIP. Alternative models and other consistency methods should be explored. The idea behind this paper is to start the conversation around consistency in diffusion model image generation and posit new ways to harness the power of multimodal embedding models for explainability. All code and data generated for this study are available in GitHub and Hugging Face.
Welcome to our presentation of SUNNY, a visual interpretation framework for convolutional neural networks from a necessary and sufficient perspective. This is a collaborative work by the University of California, Davis, and National Taiwan University. Saliency maps are widely adopted for CNN interpretation, aiming to highlight the most important input features for model decisions. However, existing approaches often focus more on model parameters, overlooking the fundamental why behind their decisions. Aligned with counterfactual thinking intrinsic to human cognition, SUNNY rationalizes CNNs from the causal sufficiency and necessity perspective. Our method considers the input features as hypothetical causes and the model's predictions as outcomes. The causal necessity, N, is measured by the outcome differences when changing the causes, while sufficiency, S, is measured by the outcome stability when specific causes are unchanged. Inspired by Shapley values, we define the NS Shapley values to quantify the causal importance of input features bidirectionally. Our framework starts with a forward pass through the CNN to extract feature maps. Then we obtain corresponding input features and perform interventions by removing or keeping them respectively. Following the definitions, we compute N and S Shapley values. The necessity and sufficiency heat maps are constructed by the weighted integration of feature maps. We evaluate SUNNY on 2 benchmark datasets using 3 different CNN architectures, where we compare SUNNY with 7 baseline methods to assess its effectiveness in providing class discriminative explanations. The quantitative evaluation with metrics such as the deletion insertion and energy pointing games indicates SUNNY's superior performance over competitors. By visually comparing with others and validating the sanity check results, SUNNY's capability of providing high-quality explanations can be further proved. Please check out the full paper for more details.
Hello, my name is Mohammad Reza, and I'm going to present our paper, Allowing Humans to Interactively Guide Machines Where to Look Does Not Always Improve Human AI's Team's Classification Accuracy. In this study, we explore a binary classification task where humans and AI collaborate. The AI receives an image of a bird and provides both a prediction and an explanation for its prediction. The human must then decide to accept or reject AI's decision. Current explanation models only offer one static explanation for each prediction. The question we want to address here is, what if we allow users to interact and manipulate the AI attentions to generate more prediction and explanations? We modify CHM core to allow the user to select specific regions on the image, forcing the AI to focus its attention on the chosen region. In this example, the user selects only the body of the bird, which leads to the prediction of summer tanager. After seeing the prediction, the user can decide to include beak, which leads to the correct prediction. We ran a study to measure the effectiveness of this approach and report two major findings. First, we found that despite being able to interact with the AI models, AI errors are still very challenging for human users to recognize. This aligns well with previous studies in XAI that show humans, even those with machine learning expertise, are easily fooled into accepting AI predictions. The second finding is interactivity does not improve overall human decision-making accuracy or static explanations. This finding goes against the popular hypothesis from the community that interactivity can improve human AI team accuracy. However, we found that for certain cases, interactivity is indeed more helpful than static explanations. In conclusion, we have open sourced our interactive interface to lay the groundwork for future work. Although we did not observe an improvement in human performance, we believe our interface can benefit other user-centric aspects of XAI, such as trust calibration, user satisfaction, and perception.
Hello, and welcome to a brief presentation of our work titled CA Stream, Attention-Based Pooling for Interpretable Image Recognition. What we present is an attention-based pooling mechanism that improves interpretability measurements on existing CNN models. How we do it is we introduce a cross-attention stream that runs in parallel to existing CNN models, updating a class-agnostic representation, a CLS token, with feature maps found at critical stages of a model, generating the representation that is used to replace gap during inference to produce explanations. Overall, our approach improves interpretability measurements of existing CLS map methods. It provides class-agnostic raw attention maps, as well as maintains the recognition properties of each model that we use. We validate qualitatively our experiments using class activation methods on both Pascal and ImageNet datasets, as well as we provide raw attention images on the MIT 67 dataset. This last dataset is important because it highlights the capacity of our class-agnostic raw attention maps to capture salient information from images and classes that it never saw during training. Conversely, regarding the quantitative experiments, we evaluate the interpretable properties following interpretability evaluation of three different class activation methods on both ImageNet and Pascal dataset. Experiments here demonstrate that our updated representation provides improvements for interpretability evaluation of different class activation methods, in turn enhancing the interpretable properties that they might convey. We expect to see you in our poster for further details. Thank you.
Why does a model predict an image as private? I'm Miriam, and I will show you which objects influence privacy decisions. Most people don't realize that sharing images online can reveal sensitive information. Designing a tool that warns them and also explains the decision is challenging. We consider a pipeline that first detects objects in an image and then uses a privacy model to recognize if the image is private from these objects. To quantify the influence of objects on models' decisions, we used an explainability method that assigns scores to object features. Here are objects detected in private images correctly classified by a privacy model. The presence of a person influences the model. The number of objects has less impact. Here we show the scores obtained from two models on private images correctly classified. Person is the most relevant concept for both models. Interestingly, one model tends to classify images as public when more than two people are detected. So we derived two classification strategies that are explainable by design. The first one classifies an image as private if at least one person is detected. The second one does so if only one or two people are detected. The high recall in the private class for the first strategy reflects that many private images contain people in the dataset. However, images with people are not always private. If you want to design a privacy model, make sure that it is not biased by the presence of people by comparing it to our person-centric strategies.
It's a very slow process.
Today, I will be presenting our work on a semantic approach to quantifying the consistency of diffusion model image generation. There exists variability in diffusion model image generation due to the stochastic elements inherent to the diffusion process, and there are differences in the level of variability across different models. In real-world problems, how do we reconcile the desire for diversity and creativity in generated outputs with the need for consistency and coherence relative to the input prompt? By quantifying consistency, we can enable decisions reconciling creativity and consistency for particular applications, detect unintended bias, validate interpretations of model outputs, and enhance user understanding. The semantic consistency score we propose here is a simple approach to this problem that leverages multimodal embedding models with a pairwise mean clip score. To evaluate a model, we have some input prompt, which is used to generate n iterations from a model. In this study, we examined two open source models, Stable Diffusion XL and PixArt Alpha. These n iterations are then passed through the clip image encoder, and a pairwise cosine similarity is computed across the embeddings for each iteration. When comparing SDXL and PixArt Alpha, we found that the distributions of consistency scores across the models were significantly different. For each pair of results from the models, human annotators labeled which image was the most consistent. The model with the highest semantic consistency score matched the most common selection among annotators 94% of the time. We also looked at the impact of fine-tuning on the semantic consistency score. The distributions of scores across base SDXL and SDXL fine-tuned on Monet paintings using low-rank adaptation were significantly different. It's important to note that there exist biases in embedding models like CLIP. Alternative models and other consistency methods should be explored. The idea behind this paper is to start the conversation around consistency in diffusion model image generation and posit new ways to harness the power of multimodal embedding models for explainability. All code and data generated for this study are available in GitHub and Hugging Face.
lunch?
Yeah.
Welcome to our presentation of SUNNY, a visual interpretation framework for convolutional neural networks from a necessary and sufficient perspective. This is a collaborative work by the University of California, Davis, and National Taiwan University. Saliency maps are widely adopted for CNN interpretation, aiming to highlight the most important input features for model decisions. However, existing approaches often focus more on model parameters, overlooking the fundamental why behind their decisions. Aligned with counterfactual thinking intrinsic to human cognition, SUNNY rationalizes CNNs from the causal sufficiency and necessity perspective. Our method considers the input features as hypothetical causes and the model's predictions as outcomes. The causal necessity, N, is measured by the outcome differences when changing the causes, while sufficiency, S, is measured by the outcome stability when specific causes are unchanged. Inspired by Shapley values, we define the NS Shapley values to quantify the causal importance of input features bidirectionally. Our framework starts with a forward pass through the CNN to extract feature maps. Then we obtain corresponding input features and perform interventions by removing or keeping them respectively. Following the definitions, we compute N and S Shapley values. The necessity and sufficiency heat maps are constructed by the weighted integration of feature maps. We evaluate SUNNY on 2 benchmark datasets using 3 different CNN architectures, where we compare SUNNY with 7 baseline methods to assess its effectiveness in providing class discriminative explanations. The quantitative evaluation with metrics such as the deletion insertion and energy pointing games indicates SUNNY's superior performance over competitors. By visually comparing with others and validating the sanity check results, SUNNY's capability of providing high-quality explanations can be further proved. Please check out the full paper for more details.
Hello, my name is Mohammad Reza, and I'm going to present our paper, Allowing Humans to Interactively Guide Machines Where to Look Does Not Always Improve Human AI Team's Classification Accuracy. In this study, we explore a binary classification task where humans and AI collaborate. The AI receives an image of a bird and provides both a prediction and an explanation for its prediction. The human must then decide to accept or reject AI's decision. Current explanation models only offer one static explanation for each prediction. The question we want to address here is, what if we allow users to interact and manipulate the AI attentions to generate more prediction and explanations? We modify CHM core to allow the user to select specific regions on the image, forcing the AI to focus its attention on the chosen region. In this example, the user selects only the body of the bird, which leads to the prediction of summer tanager. After seeing the prediction, the user can decide to include beak, which leads to the correct prediction. We ran a study to measure the effectiveness of this approach and report 2 major findings. First, we found that despite being able to interact with the AI models, AI errors are still very challenging for human users to recognize. This aligns well with previous studies in XAI that show humans, even those with machine learning expertise, are easily fooled into accepting AI predictions. The second finding is interactivity does not improve overall human decision-making accuracy or static explanations. This finding goes against the popular hypothesis from the community that interactivity can improve human AI team accuracy. However, we found that for certain cases, interactivity is indeed more helpful than static explanations. In conclusion, we have open sourced our interactive interface to lay the groundwork for future work. Although we did not observe an improvement in human performance, we believe our interface can benefit other user-centric aspects of XAI, such as trust calibration, user satisfaction, and perception.
Hello, and welcome to a brief presentation of our work titled CA Stream, Attention-Based Pooling for Interpretable Image Recognition. What we present is an attention-based pooling mechanism that improves interpretability measurements on existing CNN models. How we do it is we introduce a cross-attention stream that runs in parallel to existing CNN models, updating the class-agnostic representation, a CLS token, with feature maps found at critical stages of a model, generating the representation that is used to replace gap during inference to produce explanations. Overall, our approach improves interpretability measurements of existing saliency map methods. It provides class-agnostic raw attention maps, as well as maintains the recognition properties of each model that we use. We validate qualitatively our experiments using cross-activation methods on both Pascal and ImageNet datasets, as well as we provide raw attention images on the MIT 67 dataset. This last dataset is important because it highlights the capacity of our class-agnostic raw attention maps to capture salient information from images and classes that it never saw during training. Conversely, regarding the quantitative experiments, we evaluate the interpretable properties following interpretability evaluation of 3 different class activation methods on both ImageNet and Pascal dataset. Experiments here demonstrate that our updated representation provides improvements for interpretability evaluation of different class activation methods, in turn enhancing the interpretable properties that they might convey. We expect to see you in our poster for further details. Thank you.
Why does a model predict an image as private? I'm Miriam, and I will show you which objects influence privacy decisions. Most people don't realize that sharing images online can reveal sensitive information. Designing a tool that warns them and also explains the decision is challenging. We consider a pipeline that first detects objects in an image and then uses a privacy model to recognize if the image is private from these objects. To quantify the influence of objects on models' decisions, we used an explainability method that assigns scores to object features. Here are objects detected in private images correctly classified by a privacy model. The presence of a person influences the model. The number of objects has less impact. Here we show the scores obtained from 2 models on private images correctly classified. Person is the most relevant concept for both models. Interestingly, one model tends to classify images as public when more than 2 people are detected. So we derived 2 classification strategies that are explainable by design. The first one classifies an image as private if at least 1 person is detected. The second one does so if only 1 or 2 people are detected. A high recall in the private class for the first strategy reflects that many private images contain people in the dataset. However, images with people are not always private. If you want to design a privacy model, make sure that it is not biased by the presence of people by comparing it to our person-centric strategies.
Today, I will be presenting our work on a semantic approach to quantifying the consistency of diffusion model image generation. There exists variability in diffusion model image generation due to the stochastic elements inherent to the diffusion process, and there are differences in the level of variability across different models. In real-world problems, how do we reconcile the desire for diversity and creativity in generated outputs with the need for consistency and coherence relative to the input prompt? By quantifying consistency, we can enable decisions reconciling creativity and consistency for particular applications, detect unintended bias, validate interpretations of model outputs, and enhance user understanding. The semantic consistency score we propose here is a simple approach to this problem that leverages multimodal embedding models with a pairwise mean clip score. To evaluate a model, we have some input prompt, which is used to generate n iterations from a model. In this study, we examined two open source models, Stable Diffusion XL and Pixart Alpha. These n iterations are then passed through the clip image encoder, and a pairwise cosine similarity is computed across the embeddings for each iteration. When comparing SDXL and Pixart Alpha, we found that the distributions of consistency scores across the models were significantly different. For each pair of results from the models, human annotators labeled which image was the most consistent. The model with the highest semantic consistency score matched the most common selection among annotators 94% of the time. We also looked at the impact of fine-tuning on the semantic consistency score. The distributions of scores across base SDXL and SDXL fine-tuned on Monet paintings using low-rank adaptation were significantly different. It's important to note that there exist biases in embedding models like CLIP. Alternative models and other consistency methods should be explored. The idea behind this paper is to start the conversation around consistency and diffusion model image generation and posit new ways to harness the power of multimodal embedding models for explainability. All code and data generated for this study are available in GitHub and Hugging Face.
Do we have the lunch social here? Sorry? Do we have the lunch social here? We're just meeting here at 12 and then we'll walk in together.
Welcome to our presentation of Sunny, a visual interpretation framework for convolutional neural networks from a necessary and sufficient perspective. This is a collaborative work by the University of California, Davis, and National Taiwan University. Saliency maps are widely adopted for CNN interpretation, aiming to highlight the most important input features for model decisions. However, existing approaches often focus more on model parameters, overlooking the fundamental why behind their decisions. Aligned with counterfactual thinking intrinsic to human cognition, Sunny rationalizes CNNs from the causal sufficiency and necessity perspective. Our method considers the input features as hypothetical causes and the model's predictions as outcomes. The causal necessity, N, is measured by the outcome differences when changing the causes, while sufficiency, S, is measured by the outcome stability when specific causes are unchanged. Inspired by Shapley values, we define the NS Shapley values to quantify the causal importance of input features bidirectionally. Our framework starts with a forward pass through the CNN to extract feature maps. Then we obtain corresponding input features and perform interventions by removing or keeping them respectively. Following the definitions, we compute N and S Shapley values. The necessity and sufficiency heat maps are constructed by the weighted integration of feature maps. We evaluate Sunny on 2 benchmark datasets using 3 different CNN architectures, where we compare Sunny with 7 baseline methods to assess its effectiveness in providing class discriminative explanations. The quantitative evaluation with metrics such as the deletion insertion and energy pointing games indicates Sunny's superior performance over competitors. By visually comparing with others and validating the sanity check results, Sunny's capability of providing high-quality explanations can be further proved. Please check out the full paper for more details.
Hello, my name is Mohammad Reza, and I'm going to present our paper, Allowing Humans to Interactively Guide Machines Where to Look Does Not Always Improve Human AI's Team's Classification Accuracy. In this study, we explore a binary classification task where humans and AI collaborate. The AI receives an image of a bird and provides both a prediction and an explanation for its prediction. The human must then decide to accept or reject AI's decision. Current explanation models only offer one static explanation for each prediction. The question we want to address here is, what if we allow users to interact and manipulate AI attentions to generate more prediction and explanations? We modify CHM core to allow the user to select specific regions on the image, forcing the AI to focus its attention on the chosen region. In this example, the user selects only the body of the bird, which leads to the prediction of summer tanager. After seeing the prediction, the user can decide to include beak, which leads to the correct prediction. We ran a study to measure the effectiveness of this approach and report two major findings. First, we found that despite being able to interact with the AI models, AI errors are still very challenging for human users to recognize. This aligns well with previous studies in XAI that show humans, even those with machine learning expertise, are easily fooled into accepting AI predictions. The second finding is interactivity does not improve overall human decision-making accuracy or static explanations. This finding goes against the popular hypothesis from the community that interactivity can improve human AI team accuracy. However, we found that for certain cases, interactivity is indeed more helpful than static explanations. In conclusion, we have open sourced our interactive interface to lay the groundwork for future work. Although we did not observe any improvement in human performance, we believe our interface can benefit other user-centric aspects of XAI, such as trust calibration, user satisfaction, and perception.
Hello, and welcome to a brief presentation of our work titled CA Stream, Attention-Based Pooling for Interpretable Image Recognition. What we present is an attention-based pooling mechanism that improves interpretability measurements on existing CNN models. How we do it is we introduce a cross-attention stream that runs in parallel to existing CNN models, updating a class-agnostic representation as it was to.
Yeah.
So you mentioned in the beginning about if anybody wants to take part in organizing the next edition or something like that.
Mm-hmm.
Is it like you just talk with people and together come up to organize the next edition?
So we're going to share a feedback form at the end of the workshop, and there's going to be a question there on if you're interested in organizing for next year,
Okay.
and you'll put in your name. Obviously, we're not guaranteeing that we're going to get everyone on the organizing team. You know, if we have 20 people sign up, that's too many people. But we'll see. We'll see if some people want to trade off their spots, then we'll just see who is interested. But usually what we do is we send out just a big email to anyone who answered that question, basically.
Okay.
And then some people don't respond, so they're obviously not interested. And then, yeah, it's I'm not really sure how we're going to do it next year. This year we had a pretty big organizing team, which was kind of nice in a way, because then people could kind of.
Yeah, I saw the slide. There
were 10 of us.
Yeah.
And I mean, I'm the lead organizer, so I took on a big chunk of the work. But in terms of like how much other organizers could do, they could sort of choose in a way how much time commitment they had. All we need to be sure of is that we have organizers when we need them, especially when we're reviewing. That's the big one. And obviously attending. Yeah, it was definitely a sprint. So yeah, either way, sign up on there if you're at all interested. We will likely follow up through an email. And that probably, like, the follow-up will probably be in like August, maybe September even.
Okay. That's great.
Yeah.
And do you plan on like any afternoon activities?
For today?
Yeah.
Absolutely. This is a full day workshop. So
I mean,
we have
afternoon, like post sort of. Yeah.
Oh, I saw you afternoon. I was like, this is a full day workshop. I'm here all day. Post workshop, what am I doing? Probably taking a nap.
Okay, I fully understand. I'm just
No. I think I am meeting up with a few people to catch up and stuff, as one does at a conference.
Yeah. I've also heard like people from Computer Vision for Sports. They like organize. They send the forms.
Oh.
You have to sign up for the beer at 6 p.m. right?
Yes, they have like happy hours and things.
Yeah,
We're not doing that, but
this is great. I mean, you're all probably very tired already, so.
Oh no, I'm fine. I ate food just now. So.
Okay, right. But okay, all right.
Yeah.
Great. And
yeah.
Should we head to lunch? 5 minutes? Maybe?
I'm gonna give it 2 more minutes because I see people filing in.
Okay.
And then we'll head down.
All right. And where is?
How do you make? Like, he's downstairs.
Yeah, I think
How do you play it?
there's a button.
That's okay. I mean, it's just an announcement message. It's not a big deal.
I have to leave the laptop here on it.
No. No, you should just take it then.
Yeah, then so it doesn't matter.
Let me just stop sharing. Okay, how do we want to do this?
Or if someone wants to keep it on Zoom while they have the laptop or phone with them, I guess they would keep it. No, why don't you ask someone online to share this and keep like with some.
Yeah, let's see if it comes.
Because we don't actually need that slide. Like, I don't care if we have that slide on or not. What I care about is just the recording. So if you leave the meeting, it's fine. The recording will just kind of keep going. And then when we re-enter, it'll continue.
Oh, I could.
Can you just leave the meeting and then
make
we'll...
him the host?
Actually, let me first put yeah, I made you the host. Let me join back in. Because I also realized you might have to assign someone else. Kyle will back during lunch for another. All right, I sent a message to Zoom. Actually, can one organizer? Oh no, I don't think we can pick up lunches for other organizers. I'm not really sure. Okay, fine. We'll just that's true. We don't see that.
Yeah, not since last year.
But for what reason?
Well, I would want someone to just stay here. That's fine. We'll have everyone go, but do you want to keep your laptop open or should I? Because if you leave, we have to assign a host. Vikram, I'm not sure if. Let me see if he is on. I don't think.
No, he's not.
Okay, let me message him real quick. Why don't you guys go ahead and go down? So go ahead and take them all down, and then just keep messaging me where you are and if you find tables.
Okay.
Yeah.
You want to?
All right, everyone head out with Pushkar and Jawad here, and I will meet you all downstairs. We'll both meet you all downstairs. So we'll just figure this out real quick.
Let's go, guys.
You'll find us, right? There might be one more speaker, like presenter who might be coming.
What?
The one I was talking to, she said that she'll be joining us for lunch. Like
Right. Like she's coming here?
Yeah, she's coming.
Okay, what's her?
Joining you guys.
Okay. Would you mind joining the Zoom so that we can make you host? He doesn't have to show the slide though. He can just join the Zooms that we have a host.
p.m. right?
Yeah, so joining the Zoom until.
He is joining, is it?
He's messaging me.
Okay.
Okay, he says give me 2. I'm glad. Yep, let's do another sound check. So this is obviously not on.
Oh, there's a button on.
There's a button on it? Oh, that's convenient. Okay, cool. So now this is on. And then, hi Tim, I can see you're online. Could you go ahead and say something so we can do a sound check?
Yep, something.
Oh, nice. Okay. Could you say something else?
Something else, yeah. Can you hear me?
Yeah.
Right.
I can hear you. Okay, cool. And then recording is good. Let's just make this a little more. Well, we do want it on so that you can show this video. All right, we'll get started in about 2 minutes. Actually, maybe more like 1 minute. And so, Tim, I'm going to make you a co-host. So that way, I mean, right now you won't share your screen, but when I tell you, you can share your screen. So I just made you a co-host, but don't share it right now. Okay, let's go ahead and get started with our next invited talk, post-lunch talk. So yeah, let me fix this a bit. All right, so we're pleased to introduce Professor Tim Miller. Professor Tim Miller is a professor in the School of Electrical Engineering and Computer Science at the University of Queensland, where he also completed his PhD. Previously, he was also an honorary professor of computer science at the University of Melbourne, where he was the founding co-director of the Center for AI and Digital Ethics. Professor Miller's work is at the intersection of AI, interactive design, and cognitive science. His primary area of expertise is in AI with a particular emphasis in human-AI interaction, XAI, and reasoning about action and knowledge. He will now give a talk on human-centered counterfactual explanations for image classifications. So go ahead and share screen and go ahead and take it away.
Can you see the screen okay?
Yes, that's perfect.
Perfect. Okay, thanks very much. So the subtitle of my talk is called Explainable AI, Beware the Inmates Running the Asylum. So I'm going to talk a little bit about some lessons I've learned around explainable AI and how we've applied some of them to computer vision. And then talk a little bit about some of the way where we're going in this space now as well. And so the inmates running the asylum comes from this paper that I wrote. It's quite a while ago now, probably 2018, with some colleagues, Piers Howe and Liz Sonnenberg, where we talked about the risk with explainable AI was that we were perhaps looking at explainable AI from the wrong perspective. And the title of the paper comes from this book from Alan Cooper, which is called The Inmates Are Running the Asylum. And in the book, Cooper asks the question, why, if we train software engineers for so long, for 4 years at a time, and they have lots of experience, why does so much of the software that we have so terrible? And he made the point that quite often what we have is software engineers who write software for themselves, which is like the inmates running the asylum, rather than for their target audience. And this book's 20 years old this year, and it made quite an impact in areas like interaction design. So if you're familiar with things like personas, that was first introduced in this book. And so we asked a similar question of explainable AI. What happens if we continue working along the space as we were in 2018, where we were writing explanations for people with expertise in machine learning or planning or reinforcement learning or whatever, and not their intended audience? And we sort of made a rally cry for being far more human-centered in this respect. And in particular, we really ask the question when we talk about explainable, well, explainable to whom? And what you don't want with this lovely, this lovely image shows here is, some user who's down in the weeds of a model trying to figure out stuff. You want them to have some useful, actionable explanation. And so the way I view explainable AI is, just get my pin, sort of the intersection of three areas: artificial intelligence, obviously, but also cognitive science and human-computer interaction. And I'm a computer scientist, I sit here, but I work with people from these two other fields. And I really see that explainable AI is a subfield of human AI interaction. It sits in between these three fields where we need to study not just the technology we build, but the cognitive mechanisms behind how people deal with them, and then how we can build better interactions in order to do it. And explainable AI just sort of sits in this area here. And when we wrote that paper in whenever it was, 2018, explainable AI was sitting well over here, right? There was a whole lot of people writing a lot of algorithms, looking at the algorithms and thinking, what information could we pull out from this? And they weren't really thinking too much about whether it would be useful for a larger audience. And so at the time then, really, I went on sabbatical to Toulouse in France, and I was really getting serious about this problem. And I thought, what I'm going to read is I'm going to read some of the literature that's around here around how people explain things to each other, because I think that things like how people explain things to each other might give us some hints around some of the mechanisms that we should be writing in order to explain stuff over here. Because the way that people explain things to each other usually has some sort of patterns, and those patterns we might be able to exploit because they give us a hint about some of the ways that people understand and explain stuff. And so I went there with the idea of the first, I don't know, like 4 weeks, I would read the literature in cognitive and social science around how people explain things. And yeah, 4 months later, I had read 250 odd papers, and I had stopped, and there was still probably another 200 that might have been relevant, but I found those first 250 were less relevant. And I found it was really exciting. And I published that in this paper, which is called Explanation Artificial Intelligence, Insights from the Social Science. And that really just summarizes work from philosophy, cognitive science, and social psychology, mostly. How do groups of people explain things to each other? And I looked at some of the patterns that I sort of came out with. What are all of the patterns that people use when they're explaining things to each other, and can we use those in order to improve explanations coming from AI or explainable AI more generally? And this had pretty good impact, this paper. I think quite a few people have read this and built ideas from it. But also in our own group, my own group, when I was at the University of Melbourne and I've just moved to the University of Queensland, we're also building some mechanisms from these. And so what I want to do today is not share what I learned all in that paper. I'm just going to share in the short amount of time I have one insight that I learned and that we've been leveraging in computer vision based research. And it's this key lesson that I think has been impactful in this is just sort of one example of one of my students' work. And the key insight is this here. So this key insight comes from this gentleman here, whose name is Dennis Hilton, who was in Toulouse when I was there. He unfortunately passed away a few years ago. But he's probably say he's a social psychologist working on explanation. And this is a quote from one of his papers. I'm going to read it. The key insight is to recognize that one doesn't explain events per se, but we explain why a puzzling event occurred in a target case, but not some counterfactual contrast case. So that might not make sense if you don't know what some of these terms mean. Maybe it does. Let me break it down to it. What Hilton was saying here is that we typically don't explain why something happened. We explain why one thing happened rather than something else. And usually we want an explanation for some phenomenon if we expected B to happen, but A happened instead. And the question we ask ourselves is, why did A happen rather than B? And it turns out this has far-reaching implications in human-to-human explanation, and it's largely accepted in those sort of philosophy, cognitive science, social psychology, that this is the case, that we typically only really care about explanations in these cases for the most part. And so this kind of means that we ask this question, why did A happen rather than B? But not only in human explanation can it have some impact. I think in human to machine explanation, well, machine to human explanation, it can have some impact as well. And let me give an example of a particular instance called a contrastive explanation, which is the term that people give to this. And the idea of a contrastive explanation really comes from a guy called Peter Lipton, who did some philosophy in this in the probably 1990s, I'd say. So let's imagine now that we have a really simple classifier that can classify these three insects, these three arthropods that are here: spider, beetle, bee fly. And it does it by trying to identify these attributes: how many legs, whether it has a stinger, how many eyes, whether the eyes are compound eyes, which just means one eye is built up of multiple little eyes, as you might know from a fly, and how many wings. Okay, and so it classifies something as a fly, and we ask, why is it a fly? And so, well, a good explanation for that might be, well, because it has 6 legs, no stinger, 5 eyes, compound eyes, 2 wings, right? That's a reasonable explanation for that. That's good. But if we thought it was a beetle and we changed our question to why is it a fly rather than a beetle, what does a good explanation look like? Well, we could say it looks like this. Well, the fly has these properties and a beetle has 6 legs, stinger, eyes, compound eyes, 2 wings. We could kind of explain them both. And then that might help somebody understand why the algorithm worked as it did. But that's not a very good explanation, and it's probably not what a good person would give if they were trying to come up with a good explanation. They would just focus on this, right? It's a fly rather than a beetle because it's got 5 eyes instead of 2. And the reason you would say that is because all these other attributes, the number of legs, the stinger, compound eyes and wings, are the same between the two. And so in that case, things like legs and stingers, they are causally relevant, but they're not explanatorially relevant. They don't matter to the explanation because they don't help people understand this question here. Why is it a fly rather than a beetle? These attributes help people might help people understand why it's a fly, but it doesn't help people understand why it's a fly rather than a beetle because they're the same thing. And this is called the difference condition. And this idea, as I said, came from Peter Lipton, this philosopher. And I think this is something, I raised this as a key lesson in one of the key lessons out of this paper, one of the 4 main lessons, because I think this has really huge impact in artificial intelligence. So in this particular example here, what we've done is we've taken an explanation, the prior explanation that might have had, say, 10 attributes to give to somebody, and we've narrowed it down to just 2 attributes here. And we know that 10 attributes is probably overloading for a person, and 2 is quite manageable. And this might seem like this is kind of a crappy little example, I guess. I've painted a table by hand and hard-coded the attributes. But when you think about contemporary machine learning models that have tens of thousands of features and many more than that if you're using unstructured data, the ability to give explanations that can focus down on just a handful of things becomes quite promising. And indeed, when we think about this is the question, like why is it one answer rather than another? In a lot of these systems, we might expect that the 2 classes that we're talking about are rather similar, and they probably do share a lot of attributes a lot of the time, and it's just a handful of attributes that make them different. Indeed, we'll see that in an example soon. And so in the lesson in this paper, I thought contrastive explanation was a great way that we could look at framing explanations in computer science. And indeed, there's been lots of work in the last 5 years looking at that, based sometimes somewhat motivated by this, but also other people figuring it out themselves. So in applying these insights, we've done quite a bit on counterfactual explanation, and so have others, but focusing mostly on computer vision based stuff, we've looked at doing counterfactual explanation for image classification. And so before we get to that, I want to explain a little bit about some of the prior work that my student did on this. So this is from my student, Reihan Zhang, who actually was awarded his PhD probably about 2 months ago now, from a AAAI paper from his in 2021, where we looked at what's called concept-based explanation. And he did he proposed this model called invertible concept-based explanations. And so concept-based explanations look a bit like this. I'm going to zoom in a minute. But basically we have on the left here an image of a dog and a cat. And in this case here, we've got two different explanations. What are the concepts in this image that led to the classification of a dog? At least what are the important ones? And what are the classifications that might lead to this class being a cat? And in this case, what we've done in concept-based explanation, this is an unsupervised method that he's proposed that basically does dimensionality reduction on feature maps in CNNs and tries to find what are the key concepts that this CNN used in order to identify these things. So let's zoom in a little bit at the dog example. And it's not a great quality image, I realize. But the first concept, let me zoom out a little bit here. Here's the concept in the image that we've had. And here's 5 examples of that concept taken from our training set to help us understand what's going on. And so you might be able to see this, I'm not sure here, but to me here, what this is saying is this concept is looking largely at the nose of the dog. This is probably not a great example here. And this one here is probably looking at the ears of a dog, because there's ears in each of these photos. And similarly, we can look at the cats. Some of the important concepts for identifying cats are, this is, I think, the eyes, possibly the eyes and nose together. This is the skin, the fur. This is stripy fur. And in this case here, we've got a really good example. It's used some of the background in order to do this classification. And it becomes quite useful here. I'm not going to get into too much detail in this case here, but we've played around with now using these concepts, training classifiers on these concepts and removing these, let's say, spurious concepts that come through in order to make more understandable classifications. And we've got a project doing this with dermatologists right now. And so the important thing is what we do is extract these concepts here. And we've got some results from this to show indeed that using this model, which we call, well, we use different dimensionality reduction tools to play around with this here. And we showed that using non-negative matrix factorization was perhaps one of the best ones. But I don't want to talk too much about those results here because I can see I'm not going into too much time. And so the key here is that we have these concept-based explanations, and we're going to use these to do this contrastive explanation. Okay, so in contrastive explanation, we might have this particular question. So here we have a bird from the CUB birds data set here, and we've got the question, why is this classified as a barn swallow rather than a cliff swallow? And I don't know the answer to this question. I didn't know the answer to this question until I saw this, till we used this example. So what does a counterfactual explanation look like in this particular case here, rather than in our earlier spider and beetle case? Because we don't necessarily have labels on the parts of these images here, although this data set does have these labels. We were experimenting with if we didn't have these labels, what can we actually refer to when our features are pixels? And so we refer to concepts. That's what we used our concepts for. And so why is this a barn swallow rather than a cliff swallow? It looks something like this. Again, I'm going to zoom in a second, but it points to a couple of different features on the cliff swallow and says, well, these two features here are present in the class of a cliff swallow. And here's an example of those features. Here's 5 examples of each of those features, and is present in this photo. And this feature here is present in the class that's a cliff swallow, and it's not present in this image here. Therefore, that's what we have concluded to make this a barn swallow rather than a cliff swallow. And these, I can't remember with this example exactly, I think these were the only 3 features that makes the difference between a barn swallow and a cliff swallow. And so if we zoom in a little bit, it's a little bit clear here. We can see it's kind of pointing to this underside of the stomach here, I think. Probably the color of this is what's important. And in this case here, it's kind of pointing to the color of the underside of the neck, I suspect, or maybe around the head. Here, I'm not great with birds. So it's pointing out the different features that are relevant here. And indeed, we can then look at what does a cliff swallow had? Well, I think, again, it's probably pointing to the color of the underside of its chest here, and that's how they differ. And so What Rayhan did was in the CUB birds data set, went through and found, took a CNN model, looked at some of the classes that are easily confused by the model. That's where the confusion matrix is sort of strong in those areas, found all these differences, and went and looked at different bird websites and bird books to verify that indeed, like, some of the things that he interpreted seem to be the same things that people in bird books are telling us. This is a difference between these two closely related birds. Now, what I want to point out here is we can see this idea of a contrastive explanation, that the things that make up a barn swallow are a lot more than just the undercolor of the chest and around the neck. There's a lot more, like things like the shape of the feet and the shape of the wings, shape of the beak, the color of the eyes. These things all matter, but they don't matter when you're trying to find out why it's not a cliff swallow, because a cliff swallow shares all of those same attributes and just has these, these slightly different features. To the point where someone like myself couldn't possibly tell the difference without being told. And so that's the way we do this concept-based explanation. The pipeline's pretty simple. We extract the concepts here, and then we do some simple comparison against them, and then find this kind of counterfactual class here. And what we actually do in this study, we did a couple of different things. I'm going to talk about one of them. This was all calculated in latent space based on the concepts and based on the concept strength in the concepts. And we did this in what we call an analytical approach here. Most counterfactual image-based stuff are search-based. They might use gradients. They might use some sort of search. We calculated these analytically. And if it was a longer talk, I would talk a little bit how we did that. But it does mean we can calculate these really fast, as we'll see in some of the results in a minute. So we did a reasonably large-scale evaluation of this using in some human behavioral experiments. We had people sitting down and solving the task of identifying birds from pictures. Again, we only used easily confused classes, and we compared it to 3 baselines. ACE is automated concept extraction built on TCAV, which some of you might be familiar with. If you're not, don't worry about it. Here, ICE was Rayhan's concept extractor, and in those two, we just extracted the concepts and their weights and presented them to people. CVE is a counterfactual visual explainer that calculates counterfactuals in a search-based approach, finds the edits between 2 images, does a similar thing. And FCCE is this approach that we've proposed, fast concept-based counterfactual explanations. And we tested 3 things: subjective understanding, whether people rated that they understood the explanation, then their ability to identify birds, and their confidence in identifying birds. And we can see that the results were quite handy. ACE never really does very well in the experiments where we run them. Does okay, but not great. People do struggle to interpret some of those. ICE does quite well. If we focus on decision-making for now, which is one of the key variables here, ICE does quite well. People understand mostly 80% of them. CVE didn't do that well, 50%. This is almost random because we're only asking people to choose between 2 classes, and probably more worrying is they're quite confident in their choices. SC did reasonably well, a lot better than CVE, but the 2 things we want to look at here are these 2 are counterfactual explainers and these 2 aren't. So moving from ICE to a counterfactual approach seemed to have some help, 6 or 7% better decision making, and using these unsupervised concepts seems to help rather than these semi-supervised concepts that come from ACE. Here, so that was good results. We were pleased with those results there. But the question we might ask is, okay, but then what's going on here? Are these computationally much harder to calculate? And the answer is that they're not, right? We're using this analytical approach in order to do them. We can calculate counterfactuals in sort of probably, it's usually sort of 2 orders of magnitude quicker than the existing search-based approaches that come around, like CVE, which take about, they're averaging around about 8 seconds per counterfactual. We're averaging, 0.03 seconds per counterfactual in CUB. And we did some experiments on other data sets and saw similar things. And this is, again, because it's not doing any search, it's just kind of finding different areas of the space and giving us our prototypes back. Giving us our counterfactuals back, sorry. And so we got some really positive results by doing this. And so the lesson that, oh, and I should say, but there is one thing that we have to think about is it does actually cost upfront. There is an upfront cost to doing this, though. We have to calculate what our concepts are for the whole CNN initially, which was about 25 seconds, whereas these ones don't have this this upfront cost. And in fact, that's probably what gives us a lot of the time back, is that we're calculating the concepts initially, and we calculate them as a one-off. Okay. So the last thing I want to talk about, so that was a lesson, right? We did some counterfactual based stuff and it seemed to work quite well. However, in other experiments we've been doing, especially with expert decision makers, we're seeing that these results don't really work very well. Some of these things aren't really working very well at all. And in this case, we've got this, don't worry about what these things are. We've just got 3 conditions, no explanation, and 2 different types of explanation. And we're seeing results like this in a lot of our studies now, where explanations aren't really helping at all, and then occasionally they're hindering when we use expert decision makers. And so this recently led me to question, is explainable AI dead? Are we actually, and I should say that we're not the only group that's having this problem. If you look at papers that test, real decision making using explainable AI, most often they fail rather than succeed. And it led me to ask the question, is explainable AI dead? Maybe the experiment results we're seeing are just lucky. Maybe we just got lucky in some of these experiments. And so I want to do a quick survey in the last couple of minutes. I want you to imagine that you've got a really important decision you need to make in your job, and it's really important, you want to get it right, and you can ask 2 colleagues. You can ask your friend Bluster, who lives in the office next door to you, and Bluster's going to, if you ask him, Bluster's going to tell you what the answer is, and he's going to tell you why this is the right answer. And that's all that Bluster's going to tell you. It's a bit of a mansplainer. Alternatively, you can go next door to Prudence, and Prudence is not going to tell you what you should do at all. But if Prudence is going to ask, well, what should you do? And if you ask Prudence, well, I think I should do this, she'll give you feedback. She'll say, that's a good idea for these reasons, but here's some reasons why that might not be a great idea. And if that prompts you to reflect a little bit, you can start saying, okay, then if that's prompting me to reflect a little bit, I can have a different option, and Prudence will give you feedback on that. My question to the people who I can see on the screen and the audience now is to put your hand up. If you had this, would you go to Bluster or Prudence? So put your hand up if you go to Bluster. You can just see the people in the room. Well, put your hand up if you go. 1, put your hand up if you go to Prudence.
More.
I can't see the hands there, but
There's definitely more. I'd say it's like fourth of the room.
Yeah, so usually when I do this, I get people to put their hand up first so they know. And so that's the kind of results that I'm getting in these experiments. Usually we get things that look a bit like this. Like most people prefer Prudence. And the challenge that I kind of have here is to say, well, what we give you in explainable AI, when we talk about explainability, we give you Bluster, right? That's typically what we say. We train a machine learning classifier in order to give us a decision that we already we've got, lots of data trained on prior decisions. We train a machine learning classifier to give us a decision, and then we explain it, and that's Bluster, and that's not very useful. And what I want to challenge people to do is why don't we give decision support that looks much more like Prudence, something that actually, rather than us critiquing the machine when the machine gives us an answer, we flip it over, and it's actually the machine that critiques us. And I'll split forward a little bit here and talk about this paper that I had at FACT last year, where I actually really proposed that as a challenge to the community, thinking a little bit about how can we use the current tools, really, I think that we already have in explainable AI, in order to flip the mode around here. And rather than building Bluster tools all the time, we're building some tools that look more like Prudence, that are giving us feedback on our own decisions, rather than us giving tools feedback on their decisions in order to make that challenge. So I'll stop there and just summarize by briefly saying what I want people to get out of this talk is that, research in social and cognitive science can tell us a lot about things like explainability and decision making, and building on that does seem to have some effect. But probably a lot of the explainable AI stuff we're doing is not actually helping in certain areas, such as decision support. And maybe we need to rethink the way we challenge this for some types of decision support and start looking at a lot more bluster rather than prudence. So thanks very much for your time.
Thank you so much. Have a round of applause. All right, are there any questions from the audience? Please come to the mic if you do. Any questions? Do you have a question? Okay, come on up.
Hi, Kim. So been following your work for quite some time. I have a question. In your opinion, what's the best way to convey explanations to humans such that they start actually inviting them and they're more thoughtful about how the explanations are conveyed?
Yeah, it's a good question, right? And so the question that I think I had was, how do you display explanations so that people are more thoughtful and engaging with them? And that seems to be a lot of the problem we've observed. This paper was motivated off not data from my postdocs, but observations from my postdocs, doing studies with people and saying, yeah, they're not really paying attention to a lot of the explanations we give them. If they agree, we did fairly complex study with expert decision makers. If they agree with the decision, that they use it and they don't care about the explanation, they just use that to way they build their confidence. If they disagree, some of them give it a cursory glance, and very small amount of them actually engage with it seriously. And I think that's what this paper is motivated by. Is that's probably not going to work very well, that type of model, for important decisions where people really need to reflect on it. And I think the way to do it is to think really hard about how do we engage how do we engage somebody in the process of the decision making themselves, rather than say, look, your job here is to check the decision that comes out of the machine and agree or disagree. And I think that there's different techniques around now. There's this idea that I've presented. A few groups are calling this frictional AI. Some people are calling it cognitive forcing. Ways to actually engage people into the decision-making process and then giving them the information that might be helpful, rather than just giving them information and thinking they're going to accept it or reject it. And another tool that's really useful is things like uncertainty measures around models. There's I think now enough research to show that if you have a model that's really uncertain, that prompts people to reflect quite a bit on the way that they engage with the decisions that are given. But it still means if it's got a high level of confidence, but it's wrong, people might ignore it. So I'm not convinced that's the whole solution. Hope that answers your question.
All right, are there any more questions? Any virtual questions? All right, thank you so much. Another round of applause. All right, so we have Swin Lee. And Swin, could you say something real quick so we can just test?
Can you hear me?
Perfect, thank you. All right,
Okay.
so Professor Swin Lee is a Paul G. Allen Professor of Computer Science at the University of Washington here in Seattle. She completed her PhD at Stanford University, and her research focuses on developing ML tools and algorithms to advance biomedical sciences, particularly in the XAI domain. Professor Lee has been recognized with numerous awards, including an NSF Career Award and the International Society for Computational Biology Innovator Award. She'll now give a talk on explainable AI for clinical AI auditing. So go ahead and take it away.
Okay, thank you so much. I slightly changed the title, but it's something similar for medical image AI. So thank you for this introduction. And then the theme of this talk is about how explainable AI has been helpful for this medical domains and how it needs to evolve. A crucial aspect of this clinical AI is understanding the reasoning process of AI models, which aligns closely with the goals of explainable AI. So you can already see how they should be integrated well, why they should be integrated well. So in this talk, I will present some research from my lab that focuses on explainable AI in the healthcare domain, and then explore how to improve explainable AI techniques, particularly for image modalities. So the work I'm about to present were primarily done by the members of my lab, the Ames lab. We consist of passionate researchers pursuing their PhD in computer science at the UW, including those from the MSTP program who are concurrently working toward both of the medical doctor degree, MD degree, and PhD in computer science. And we work on a broad spectrum of problems, including developing, the theme of this workshop, explainable AI techniques, and also identifying cause and treatment of challenging diseases such as cancer and Alzheimer's disease, and developing and auditing clinical AI models. So today's talk will consist of 2 parts. So the first part will review the concept of explainable AI in the most traditional sense, especially for those who are getting interested in explainable AI, doesn't have much background yet. And I'm going to focus on the clinical context, and I will provide many examples illustrating how we can enhance the healthcare problem solving. I know this is a computer vision, workshop, but this part will highlight this importance of explainable AI in these clinical applications in general, and then describe some other modalities. And then in the second part of the talk, we'll focus on medical image AI models, exploring how explainable AI can foster trust and transparency in these models, and how to enhance, how we should actually improve explainable AI to further advance clinical image AI for this, particularly for image modality, so more relevant to this, CVPR conference. So we won't delve deeply into any specific project in this talk, but we'll, explore various examples of how explainable AI can revolutionize healthcare domain and how to improve it, for medical image AI in particular. Okay. So the key goal of explainable AI in the clinical context especially is to understand why a certain output was generated by a machine learning model, such as dementia onset, risk prediction model. So let's say that you have a set of patient features, say demographic information, clinical data, ApoE, some cognitive exam results, and a well-trained machine learning model, we can predict various, kinds of clinical outcomes accurately. However, in traditional machine learning paradigms, we couldn't answer a very natural question of why a certain prediction was made. It was all, AI magic. And then it is because with large modern data sets, the best accuracy is often achieved by complex models, even experts struggle to interpret. And then the idea of explainable AI is to explain the output of the black box machine learning model based on the contributions of the input features for each individual prediction. So now you're talking about one patient and one prediction, and they want to compute how much each feature is important. This is how feature attribution method, the most traditional form of explainable AI works. And my lab has developed a series of explainable AI techniques. The first one being named SHAP, Shapley Additive Explanations, which is a general framework that can be applied to any model, has desirable theoretical properties, which other methods in this domain do not. Just to give you a basic idea of how it works, the key question is how much adding one feature I changes the model output. That's how much that feature is important. And then this may depend on what other bodies, what other features also participate in this, prediction. So say you have, a subset of features S, and then without I, and then you add I, and then see the model prediction, model output changes. And then, so then how about we consider all subsets of features S, and then take the average of these results. So it sounds, very reasonable, and then it turned out that if you do that, then you will have desirable properties with the fairness axiom from cooperative game theory. We're not going to delve into this deeply in this talk, but the key challenges will be then that, a machine learning model needs to have a complete set of features. And then in this, idea, you have to consider a subset of features, which doesn't really work. You have to simulate feature removal. Also, computational complexity will be of a huge problem. So since then, my lab developed many, principles and techniques for that. So for example, in one paper, we showed that SHAP unifies a larger portion of XAI literatures with 25 methods. And then we showed that they follow basically the same principle, which is, explaining by removing features. And then also, that's going to help us understand what goes on when they fail or succeed, and then improve and develop new XAI methods. And then, on the computational side, we have explored many avenues to make SHAP computation even faster and then feasible. We developed, for example, fast, statistical estimation approaches where you can detect convergence. And then especially, we also developed many versions of SHAPs for model-specific SHAP algorithms, such as tree models, tree ensembles, and then deep SHAP, and also for vision transformers as well. Okay, so that was a brief, overview of this method. So using one of these developments, the tree SHAP, we revealed individualized risk factor of chronic kidney diseases, all-cause mortality, and then also other clinical conditions. And we worked closely with the clinicians, the domain experts, to make sure that these individualized risk factors all make sense. And then, those results can provide a new insight about these diseases, and also what matters to those clinical conditions, gives a lot of scientific insight. Then we also, tackled the question of whether explainable prediction can improve a clinician's ability to predict clinical outcomes in anesthesia care, because as we know, surgery and anesthesia are an integral part of the healthcare, but pose a considerable risk of complications and sometimes death. So we focused on unwanted physiological condition called hypoxemia, meaning low blood oxygen level, and then that can cause a serious patient harm. If hypoxemia can be predicted before it occurs, then anesthesiologists can take actions to proactively predict hypoxemia and minimize the patient harm. So for that, we developed a prescience system that can predict near-term risk of hypoxemia during surgery and explains the factors that led to that risk. So here is how it works. It outputs the risk prediction. So in this example, it will be 2.4-fold, which is not a lot of a risk, but some risk. And its explanations, which shows a set of features that increase the risk, the purple-colored ones, and a decrease the risk, the green-colored ones. And then the plot at the bottom is equivalent to rotating this explanation bar at a certain time point by 90 degrees, and then stacking the explanations for each time point horizontally. So you can see, from the risk trend that the large increase in the risk at the current time point was driven by tighter volume, meaning a drop in the patient tighter volume of gas exhaled per breath. A patient under anesthesia is connected to a ventilator. And then this tighter volume is something you can adjust to using the ventilator. Of course, there is a separate question of the causality, right? But, this kind of explanation that comes with the clinical, prediction can give a lot of insights in terms of what they can do, what clinicians can do next. So importantly, we showed that explainable prediction might improve the anesthesiologist's ability to predict the event. User study using a web-based interface. So to simply ensure that both prescience and anesthesiologists are given the exact same amount of information. So the result is that the anesthesiologist, when they anticipate 15% of the events, then with the prescience aid, they can anticipate 30% of the events, meaning millions of additional detection of hypoxemia annually in the US. So quickly, just to turn to the more recent. So I'm just showing you the oldest project in clinical AI area, and then one of the newest work that was done in my lab. We just talked about near-term risk of adverse clinical condition. Then how about much longer-term lifetime prediction task? It's about biological age. So And we developed enable age clock. So meaning you want to estimate an individual's biological age based on demographic information, lab test, exam results, and lifestyle, and so on. And then you want to predict the biological age, and it explains the prediction. So we trained using UK Biobank data from 500,000 people using 800 such features. Here is how it works. For 65-year-old woman who turned out to be 72 in terms of the biological age, the explanations is going to show which potential factors increased or decreased the biological age that comes with the extent in the unit of a year. So when I said SHAP has desirable theoretical property, so it's one of them, it's additivity. The explanations will be in the same unit as your prediction. And then this can make even more interpretable. And then cancer diagnosis, of course, accelerates biological age. And these explanations can provide, for various mortality causes. Neoplasm means cancer, and then circulatory diseases and respiratory diseases, and so on. Then we also identify the potential genetic factors for age acceleration through genome-wide association study. And then if you want to know, better about this work, it was, featured on the cover of the December issue of Lancet Healthy Longevity last year. Okay. So now, quickly turning to the second part of the talk, I want to talk about this explainable AI. So far, you heard all these successful stories in terms of how feature attribution methods were helpful in healthcare domain in general. And then now I'm going to show that when we use image modalities, when the data are medical images, it gets a little more complicated. We need more, kinds of, explainable AI methods for this modality. Okay, so the first task is about AI auditing. So in this example, we revealed that many published clinical AI systems to detect COVID-19 from chest X-rays learned shortcuts rather than genuine pathology. As we know, in 2020, there was a surge of a clinical AI system that takes chest X-ray data as input, and then it's going to say whether you have COVID-19 or not. And first, our results illustrated a potentially dangerous situation in which the algorithm appears to be highly accurate. So that's red ROC curves within one data set in cross-validation setting, of course, but fails when tested in hospitals external to the training data. And then to understand why these models have failed to generalize, we took a look at the saliency map. So that's the most traditional form of explainable AI. And then for this, input X-ray image, for example, it is turned out to be COVID negative. And you see this, what regions of the image, what features were important. In this case, input pixels will be features. And then it's right that the model used clear lung basis as the basis for determining negative COVID-19 status. But it's not quite right that the model used laterality markers on this image or medical devices that, it should not be used as a basis for prediction of COVID-19 at all. So overall, through many this saliency map-based approaches, we basically stopped the field and moved to the wrong direction. There were already 6 published papers, some very, very prestigious medical journals, and also hundreds of related models out there that learned the shortcuts. So now, this, and 1 year, after the Nature featured our paper through this, Outlook article, and then they had this nice photo of the co-first authors of this paper. So one as I mentioned, I'm working with several MSTP students pursuing computer science PhD. Alex DeGrave in the left, and then Joe Janizek, who just got matched to Stanford. He's going to leave for his residency then. Okay, so we see that it's very important to dig into what an AI model is thinking, reasoning, and then the next target for us is now a dermatology AI models in collaboration with Stanford University. There are many cell phone apps. You can easily find them, or high-profile biomedical journal publications about this problem. You take an image of skin, so it can be just a cell phone level image, or you can also, use dermoscopic image, which dermatologists use. And then you want to know whether you have melanoma, skin cancer or not. Okay, so and we picked 5 systems consisting of 2 academic models, 1 Nature paper, 2 commercial devices, and 1 competition winner. There was a whole competition, so we took number 1 and perfectly replicated all these models. So we basically conducted an audit of these 5 dermatology models. And then the result was somewhat, consistent with what we saw in this COVID-19 project. And then, but more interesting aspect of this project is that when we tried interpreting these models using this simple, saliency map-based approach, we ran into some interesting challenge. As you can see in this example, from the original image, this saliency map is not interpretable at all. I mean, just pointing to the entire region of the image. You can see, skin images are very different from X-ray images. And then, we need to go beyond this, feature attributions. And then so we developed an auditing framework that incorporates counterfactual images using generative AI. So the idea is that you want to generate the image that agree, with either with fully malignant, so you modify the image such that it just crosses the classification boundary to make it more malignant, or the other way, benign, by the model you are auditing. So you can generate many, counterfactual images like this, for example, and then you will suddenly see when this image became, the label of this image became, malignant, according to the classifier you are using, you start seeing these new visual features like, in the blue-white veil. So this project, I learned a lot of dermatology terms. So it's a bluish region, which makes dermatologists usually think that it's malignant. Okay, so, and then we systematically characterized, these visual features with anesthesiologists. Roxana is the main person we are collaborating with. She's a professor at the DBDS department and dermatology at Stanford, and then Zuo, her colleague at Stanford. So to just to show you the summary of the result, we used 3 data sets to show how these 5 models perform in terms of the prediction performance, and you're seeing the y-axis the area under the ROC curve, and then you see these names of the 5 systems that we audited. Some systems used some of this test data set for training, so we indicated as such in that case. So you see that usually in that case the test accuracy tends to be better, and the DDI is a brand new data set that was not incorporated into any of the publicly available data sets such as ESIG or Fitzpatrick's data. So again, the idea is that for each of these 5 models, you create a pair of counterfactual images that's more like malignant and then also benign counterpart. So that way, from one AI model you're auditing, you will get lots of pairs, many pairs of malignant and then benign counterparts. So here, left is benign and then right side is malignant. And then we analyzed in terms of major visual features with the dermatologist. So we can characterize each of these systems in terms of how each of the visual features identified by the dermatologist are perceived by the model. So for example, one of the systems is behaving very differently in terms of how it perceives this darker pigmentation feature. It thinks that it's basically benign, but it turned out it's what's consistent with the literature is the other way. It's a malignant. It should occur in malignant more. Okay, so that way you will you can understand how these features are really this information is used by each system. Okay, so after this paper, I got the really good opportunity to write a perspective article published in Lancet earlier this year that talks about, not just this, but, a broader set of applications, clinical potential of this counterfactual AI in clinical medicine in general. So in this line of a project, we also, came up with the second solution to improve the interpretability of this auditing process or classification process in general. It's using clinical concept. So the way humans perceive image data is not a bunch of pixels. We are not machines. And we think about the concept, for example, asymmetricity or borders or color, and so on. That's how dermatologists are thinking about when they see this kind of image. So we developed in the next paper, just published in Nature Medicine, we use a foundation model, image text foundation model, clip, and then fine-tuned it using 100,000 image text pairs from textbooks and PubMed articles. So basically, as we know, what it does is to bring image and text into one joint embedding space. So that way, when you have a new image, using some semantically meaningful dermatology terms, you can compute the cosine distance, and then that can be a way to featureize that image in terms of the relevance to that concept for each image. So you can basically turn your pixel-based image data into a set of a concept. So that was another way, totally independent way to improve the transparency of this clinical AI system. Okay, so let's conclude. So I just talked about the significance of explainable AI. I used the time series data and what else, tabular data, and then how just applying SHAP, feature attribution methods, would be impactful in the field of biomedicine. And then in the second part of the talk, I showed that for image data, it's a little more complicated. We need to develop broader set of explainable AI techniques to handle that. So that's basically what I said. Okay, so feature attribution methods are often, very limited, and then also we need to develop more methods. So just I gave two examples, one based on counterfactual XAI, and then the other one is a concept explanation methods. Okay, so story I was telling you today was the only subset of the research we do, and then you can find more about our research on our website. And then as I said, we work on a very diverse set of topics. So AI, biology, and clinical medicine. So every single paper is labeled in terms of the relevance. So A, B, C, A, B, and C to make it easier to navigate. Again, it was a very small, subset of a research project we have done. I just want to emphasize here that, we developed lots of, novel explainable AI techniques from feature attribution and then more. And then, we also, so that way we published lots of, you should be must be familiar with all this, machine learning conference names, but also very interestingly, we published tons of, other biomedical journal papers that covers, broad set of topics such as medicine and, cancer biology, and, Alzheimer's disease therapeutic target detection. So just the point is that, explainable AI is awesome. It's really important. Again, to remind you, the work I was presenting today was primarily done by my students, not me. I haven't generated any single plot. I haven't even written a single line of any of the code. It was done by all of them. And then our research had been funded by NIH, NSF, ACE, American Cancer Society, and Chen Zuckerberg Initiative. So the size of the logo, actually, I made it roughly proportional to the size of the support. Thank you so much. I'm happy to answer any questions you might have.
Do we have any in-person questions? Please come up to the mic. Otherwise, I'm going to ask one. All right, I'm going to ask one then. So I was wondering, for the dermatology paper, actually it's funny because that paper was assigned for a seminar I took this semester. And so one thing that I remember coming up as a question is you had two clinicians who gave feedback on the counterfactual images. And so I assumed that gave you an idea of whether or not they were realistic enough or not. But I was also wondering, in your experience, how much do clinicians agree or disagree? So, I mean, the two who you're talking about are from Stanford, so probably from, I guess, the same affiliation as well. So they probably agreed on those things. But if you were to ask clinicians from maybe different geographic locations or even different affiliations within the US, what do you think? Do you think that they would be consistent or no?
So we had, we saw general consistency between them. I mean, sometimes they differed in terms of the visual characterization, but, the way we worked with the clinician was not about labeling. Sometimes, clinicians have disagreement in terms of the disease diagnosis. In our case, they characterize each image in terms of the, major visual features. In this case, so to get, this kind of a conclusion. So in that case, it's not that critical that, how to deal with the disagreement. But you are right. I mean, when you work with clinicians, the more the better. It'll be ideal if you can work with like hundreds of clinicians and then take the average of your, result, but which is realistically impossible, right? So when it comes to, this user study or, you need clinicians' impression, you always need to work with, let's say, at least 5. We had another paper which I didn't have a chance to talk about. In that paper, it was about emergency medicine. We worked with like 5 to 10, and we co-authored them, all of them. And in that paper, we needed actual labeling and then also getting a sense of how efficient to gather features. So depending on what you are looking for some tasks you need to work with many clinicians.
Makes sense. Thank you. Are there any other in-person questions? There's a virtual question. All right, go ahead.
Right. So the question says, can you comment a little bit about the relationship between causality and explainability?
Relationship between causality and
explainability. So I imagine
explainability, right? So, if you identify causal factors, then that's probably the most explainable conclusion, isn't it? Right? Because not only which features are relevant, which features are predictive of your model output, you know the mechanisms underlying it. So that I think is the most explainable form of a conclusion, when you know what features are important at the same time, that features turned out to be causal. Of course, with the observational data, you can never, conclude purely based on your data which factors are causal. I mean, high SHAP values doesn't tell you that it's a causal, right? So one, way to address that challenge, difficulty with identifying causal factors, is to use a prior knowledge. So for example, if you can explain your explanation, say, if you can explain your high SHAP values based on some literature-based evidence about their relevance, and if it's a causal, then that can be a way to make it even more explainable, right? So yeah, that I'm not sure if I directly answered your question, but that's what I would say.
All right, thank you. So if there are no other questions, oh no, there's one more question. Yeah, go ahead, come on.
Thank you, Professor Lee. I had a question. So I noticed that as a model developer, I might use one image and spend a lot of time interrogating my model using just one example. For example, I'll interrogate the salinity map, or I might, for the melanoma example, spend a lot of time interrogating the malignant generated image versus the benign generated image. Is there any way that we can understand, like as the model developers, use these tools across maybe like thousands of melanoma images and understand the general model behavior using these explainability tools? Does this question make sense?
Yeah, that makes a lot of sense. Well, that's related to the idea behind this paper, right? I mean, the paper we were just talking about. You're interrogating the model by generating counterfactual, such that, well, that's one of the ways that that does what you just described.
Okay, and do you have to interrogate every image manually, or can you use computational methods like SHAP?
I think it depends. I mean, I think I can guess what the new method will be like if you use a SHAP. So you can, for example, interrogate the model with the new images and then see what the model was looking at using SHAP, right? So that definitely, gives you more information in terms of how the model behaves.
All right.
Thank you very much.
we'll stop the questions there. And yeah, thank you so much for presenting, and let's hear another round of applause for Kersting.
Thank you.
So we're going to move on to the second spotlight session.
Did you download the new one for Maximilian?
Oh, no.
Yeah.
Is it easier if I download and share it to Slack? You don't want, because yours is being broadcast.
Yeah, okay, sure. That's better actually.
Okay. So download the new one. Okay. You want it sent as a direct message on Slack?
Yeah.
Yep, that is in fact not a wall. We discovered that. Okay. I think peace first. I have your speaker notes here. Sharing, that's good. Looks good on here. And you have a PDF pulled up?
Yes.
Okay, go ahead. Let me get your speaker notes. Yeah.
Okay, so we'll now start with our second spotlight session. And again, we have 3 talks in this session as well, each of 8 minutes each. The first talk is titled Pure, Turning Polysemantic Neurons into Pure Features by Identifying Relevant Circuits, and will be given by Maximilian Trier.
What do neurons encode? That's an interesting but sometimes challenging question to answer. Challenging because neurons can be polysemantic, meaning that they encode for multiple unrelated features. And the task of this paper is to tackle polysemanticity by going to a higher basis. However, let's start at the beginning. So how can we find out what a neuron encodes? One popular approach is to collect the most activating input samples for a neuron, as we can see here. And then in this example, we see that this neuron activates for mazes, but also for dogs. Just as a side note, I do not show the full input images here, but I zoom into the actual relevant part, which makes interpretability easier. Why? For example, look at this example in the top row where I display the full reference images, and there's so much going on, it's not clear what the common theme is. However, when we crop into the relevant region, we see that this concept refers to the arm of humans. So how can we tackle polysemanticity now? The idea, or the underlying idea here, is that for each pure feature, there is a subgraph in the architecture that corresponds to this feature. For example, for the maze concept, there might be a lower level neuron that encodes for green color, which is characteristic. And for the dog concept, there might be a fur concept or neuron in the lower level layers. So, and if we then can identify the subgraph that is active for a sample where the neuron activates, we then know which semantics it actually refers to at this moment. And then we could, in principle, route the activation of this neuron to a new virtual neuron. And here we create these virtual neurons, so one virtual neuron per pure feature. And then in the end, we have 2 monosemantic neurons. That's the idea. So now we have to find out these subgraphs, which are also called circuits often. And this is the method. So we begin by collecting these most activating input images. And then for each image, we explain the neuron that we're interested in. So we explain the activation with some attribution method. For example, just gradient times input. And we propagate these attributions to the next lower level layer. Just for simplicity, we only look here. And we hope that in the previous layer, we find these characteristic neurons. And if we can, then when we cluster these attributions, we will see two distinct clusters, or as many clusters as there are pure features encoded by the neuron. And each cluster center here refers to this specific subgraph. And then for a new sample where we see the neuron activates, we just have to explain the activation of the neuron, attribute the lower level neurons, and then we can assign the specific cluster, and we know which subgraph is actually active. So here are some examples where we apply our method, which is called PURE for purifying representations. On the left, you can see a clearly polysemantic neuron that encodes, for example, for lipstick and also for dark skin of boars, for example. And when applying PURE, we can nicely disentangle these concepts, and we get monosemantic virtual neurons.
Just giving a format one.
Yeah, so this is a qualitative example. Now we want to quantify this a bit more. And the idea is to use visual foundation models, and especially the latent embeddings of them. And we take these activating image patches before we apply our purification method, and then after our purification. And when the beginning, we probably get very different visual embeddings when we have visual semantics present, so a high distance. We hopefully after purification have a low distance in these visual foundation embeddings. So here in the bottom, you see these bars, and basically the larger the bar, the better. And the best performance we achieved when we use another vision foundation model on these cropped maximally activating image patches, which is computationally very expensive and basically an upper baseline. With PURE, we are almost as good, and we outperform an activation-based approach. So why are activations not always the best choice? Because they're not very neuron specific. For example, here we have the semantics of vegetation on horizon. And in the first image pair, we have a similar background. And then the activations in one layer, so the layer where the neuron is, are also very similar. So we have a low distance. However, when we have varying background features, for example, plane and boat, then this is also captured in the activations, and we have a high activation distance. So now let's look at an application of where this is interesting, concept-based explanations. Here, for example, with the concept relevance propagation approach, where we explain the prediction of an elephant. And in the traditional heat map, we see that the task seems to be very important. And now we go to the concept level. So we take into account the neurons in some specific layer, and we learn that actually the most relevant neuron and concept refers to the background vegetation. The second one refers to the texture of the skin. And here we already see in these concept visualizations that there's, for example, also a red volcano or speed meter images, which in this case are very confusing for the user. And this is probably because of a polysemantic neuron. So when we apply PURE here, we kind of filter out these distracting visualizations, and we better illustrate exactly what is going on here. If you're interested in polysemanticity or concept-based explanations, feel free to reach out and talk to me during the poster session.
Do you have any questions from the audience or on Zoom? Yeah, go ahead and talk to the mic. Just a Zoom.
I can't relate, so sorry if you answered this, but how does this compare to sparse autoencoders? If you've heard about that one, this is one.
Yes. So with a sparse autoencoder, you basically now we're interested in neuron K, for example. So I mean, here we assume we look at individual neurons and we look at the concepts they encode. When you apply sparse autoencoders, you basically say it's not feasible to look at individual neurons because they represent random stuff. So I just insert a new type of layer with a ReLU activation, and then you kind of enforce some properties and hope that the neurons in this sparse autoencoder are interpretable. So this is a lot of work you have to put in and a lot of assumption you have to do. And this might work better, but I think it's worth also to try out and stick to the network you have instead of inserting new stuff. Yeah.
Yeah, go ahead, just very quickly.
Thank you. I was just wondering, because here you make, I think, an assumption that maximally activating a neuron means that it is most important for the neuron. And have you explored any techniques for researching it differently, like correlation, for example?
Like what?
Like correlation of activations and its.
So I just had to think of like an alternative for looking at the most activating input images. You, instead of measuring the activation, you can also measure the importance of the neuron for a specific input. Then you can also like sort according to when is a neuron actually used. And then you can look at these examples, and they can in fact also differ from the most or highly activating samples. This is also covered, for example, in this concept relevance propagation paper. In this work, I haven't looked into it, but it's also sensible to study these samples.
All right, let's move that up. All right, let's get ready for the second spotlight.
So the second talk is on quantifying explainability with multi-scale Gaussian mixture models by Anthony D. Rhodes.
Thanks, everyone. It's my pleasure to be here. So I'm presenting quantifying explainability with multi-scale Gaussian mixture models on behalf of my great collaborators. So I feel like I'm preaching to the choir here, but as everyone I think knows, or at least is present in this room, we're all fans of explainability and have seen some of the amazing results we've gotten from explainability in recent years to help us understand how machine learning models process data and, more importantly, how they actually make predictions that they make and why. And so in particular, one of the most important methods, as we've sort of seen in previous talks, to that end are saliency methods, which attempt to approximate the importance of input features and highlight those for model prediction in particular. So saliency maps have in particular help researchers evaluate and compare predictive models, enhance human-in-the-loop functionality, and also help improve fairness and generalizability. So as we just saw in some of the previous talks, especially in computer vision applications, one of the most common techniques used for saliency are saliency maps themselves. And so saliency maps, as we can see right here in this application to deepfake detection, can help highlight relevant pixel regions for model prediction. So in particular, I'll explain our algorithm, of course, in just a moment, but we're looking or focused on deepfake detection classifiers. So with deepfake detection classification, saliency maps in particular can highlight the types of artifacts that different classifiers are looking at and can reveal additional insights as well about how the models are making the predictions that they're making. So despite the fact that there are copious numbers of explainability techniques out there, still remains an open question in research, which is, which methods are the best saliency methods? How do we compare saliency methods? How do we understand sort of whether or not different explainability techniques are redundant as well? So generally speaking, when it comes to comparing different explainability methods, there's sort of three different categorizations that we can look at for saliency maps. So when it comes to the leftmost sort of column in our table here, if we're looking at image space analysis, we can look at things like what is the IOU between saliency maps, or look at structural similarities as well. Now, these techniques are great and useful for comparing saliency maps, but they do have some drawbacks in the sense that they can be sensitive to noise or individual pixel differences between saliency maps. On the other hand, if we want to zoom out, we could do an analysis on the level of the distribution space, where we look at different saliency maps and attempt to fit a probabilistic model looking at KL divergence or earth mover distance between saliency maps as well. And these are very useful techniques, but however, they're not necessarily inherently hierarchical, and some of the spatial structure can be lost when we zoom out to the distribution space if we want sort of better granularity. On the other hand, in the rightmost column, another technique to explain saliency maps is looking at input space analysis. So what we mean here are like post hoc techniques where we insert pixels or delete pixels and see the impact that this insertion and deletion has on saliency maps themselves. These are also wonderful techniques, but they do have a drawback because they require lots of extra inference and compute as well. So with our solution, what we're looking at is how to basically systematically compare and contrast and quantify different explainability techniques through the lens of saliency maps. So our technique is called Explainable Multiscale Gaussian Mixture Model Distance, or XMGD for short. So it gives us a principled probabilistic algorithm to help analyze and quantify any model or dataset similarity through this lens of explainability. And we demonstrate some of the critical advantages of our algorithm when it comes to comparing different saliency maps using traditional techniques. So just to highlight a couple of the advantages that XMGD gives. It tends to be robust, as I'll explain, against individual pixel saliency, because we are going to map things to a higher order Gaussian mixture model, as we'll see. It can be also less sensitive to data set size, so it doesn't suffer from poor convergence properties if you have small data sets or a small number of saliency maps. And XMG directly operates on saliency images themselves, so you don't need a post hoc analysis in terms of extra compute and inference steps to further analyze the saliency maps. Also want to point out that XMG can enhance explainability in a number of different use cases. It can be used to compare saliencies across individual images, entire data sets, or different models altogether. So I'll just briefly explain our algorithm. It just operates in 5 steps, essentially. So let's say, for instance, that we want to compare two different explainability techniques, and we want to quantify how similar the saliency maps are rendered by those 2 different explainability techniques. So one would take your data set and generate, using those explainability techniques, saliency maps, and then we project those saliency maps into a 2D unit grid, essentially. So now we have a set of normalized saliency maps. In step 2, we fit a Gaussian mixture model to those normalized saliency maps. And then we have 2 different distributions, and we want to just sort of quantify how similar or dissimilar are those distributions to get a sense of how similar or redundant are those explainability techniques. So in the 3rd step, we then calculate the distance between those Gaussian mixture models using just a standard technique, the 2-Wasserstein distance in this case. And that gives us a principled mathematical scalar value to say what is the similarity between those explainability techniques. And then finally, to improve the robustness of our technique, we repeat steps 1 through 3 across multiple spatial scales using a simple convolution operation. So there is some flexibility baked into our framework here, but essentially one can just use a convolution operation on the original saliency maps using different filter sizes to get a quantification of the similarities at different scale for those explainability techniques. And then finally, our final XMGD score is just going to be a weighted sum of these multi-scale distances, essentially. I just want to mention there's a number of knobs and kind of hyperparameters that one can tweak as need be in our framework. So number one, the number of scales, different sort of multi-scales that you use here is flexible. The kernel sizes are also flexible. Of course, the number of Gaussian mixtures that you're using is also flexible. The results will be sensitive to that as well. And then we evaluated our XMG algorithm in terms of its representativeness for 3 different criteria. We looked at diversity of distances. So what we mean here is we want to see a meaningful manifestation of differences across different explainability techniques, different models, and different data sets. Something that was more differentiated than traditional techniques, and we did see that in our experimental results. We also tested to see relevance to model-based metrics. So in short, XMGD was able to highlight techniques like integrated gradients and grade them more highly without the need for post hoc manipulation and extra inference. And then we also intuitively wanted to see strong correlations across the same detectors and generators when it came to deepfake detection, and XMG was also sensitive to those things. And you can check out our paper for the full experimental results there. And I'll just mention, I know those numbers are hard to see, apologize for that. What we're comparing here, just to go back to this notion of the diversity of distances. So we want to see a manifestation with this comparison of different explainability techniques that shows a differentiation between different techniques. So in the leftmost column, we're using SSIM, to structural similarity, standard technique to compare saliency maps across 4 different explainability techniques. In the middle column, we use traditional technique Hale divergence to sort of quantify the similarity of these different explainability techniques. And then on the rightmost, sure thing. On the rightmost column, we have the XMGD results. Again, I apologize, the numbers are hard to see there, but we do see the most numerical differentiation using XMGD for these different explainability techniques, whereas SSIM, Hale divergence, and traditional techniques did not give us a differentiation, did not see numerical differentiation between those different techniques. You can also, again, check out in our paper, for consistency, XMGD did get high correlation for deepfake detection across the same detectors and same generators. And that was also not something that we regularly saw using traditional techniques to compare saliency maps as well. And then lastly, I'll just mention in relevance to model-based metrics, as I was saying before, when we look at techniques where there's a post hoc, adding of pixels or deleting of pixels as shown at the bottom here, techniques like integrated gradients tend to score best with those kinds of saliency quantification algorithms, but at the cost of having to run additional inference and computation. Whereas XMGD did highlight and grade techniques like integrated gradients most highly compared to those other explainability techniques without needing extra computation and inference to do so. All right, so I think I'll stop there. Happy to answer questions and talk to people in the poster session as well. Thanks.
We have time for one quick question. Okay, we can just clap again and then move on to the next one.
Okay, so the third and final spotlight talk of this session is LVLM Interpret, an interpretability tool for large vision language models by Matthew Olson.
Hi, everyone. I'm Matt. Thanks for coming to my talk. It's my honor to be the one to present this large collaboration in building this excellent tool for analyzing large vision language models. So what we present here is not any particular novel contribution, but a nice tool integrating a variety of explanation tools
for large vision language models. There are no GIFs, they got all deleted, but my apologies. Our tool unifies not just running a VLM in your web browser, but being able to analyze a variety of aspects of it. If you're not familiar with large vision language models, they became extraordinarily popular 1 year ago with the introduction of Lava, which simply takes a pre-trained vision model like CLIP, takes a pre-trained language model like Vicuna, and slaps them together with an MLP, and you get extraordinarily good results. Shocking a year ago, and now a very popular topic these days. But of course, as with all deep neural networks, these are actually unexplainable black boxes, and so we do our best to provide you some tools on how to dig into the different components of these LVLMs. The first major component of our interface is the attention subpanel. You're able to select through any of your layer of a Lava model and select the different attention heads and see how do these different small components inside that LVLM and how do they work according to this input image. And so through this interface, we're able to interrogate a variety of different parts of the attention maps. The next part of that subpanel is the patch-based attention, where you can select just particular patches that you can click on and see how do those relate to your specific question. I'm particularly a fan of this because I implemented it in Gradio and it was terrible. It took like 8 minutes, or it took like 8 hours.
Sorry.
This is 2 minutes for me. Anyway, next is relevancy maps, a gradient-based method. We use a more modern relevancy map generator from Schaefer et al. From ICCV, where we're able to generate these gradient saliency maps and see just how much does your model actually pay attention to the image. With these saliency maps, we find that we can identify some root cause analysis why a model is not answering questions correctly. And then finally, we integrate a new recent NeurIPS causal mask or causality method, which was originally designed just for LLMs, but we adapted it for vision in order to build causal graphs. And so in short, it's a fairly complicated method, but the gist is you can, at the very last layer of this VLM, you can drop out different input tokens and then use that to generate the causal map here, where the edges correspond to a single hidden latent variable. And by finding the number of hidden latents that you can grab from the correlations, we can actually build this causal mask. And I've used it, and it seems to really work and have a good causal explanation for how your images are being interpreted by the VLM. And we've integrated that into the app for easy to use and click around. It's kind of fun to use. So next I want to go through a few case studies that we found were very interesting, that you ask a model this particular way of, is the door closed? It'll say, yes, it's closed. If you ask if it's open, it'll say, yes, it's open. And so we found we thought, is it only looking at the input images or is it just looking at the input text? We found with our relevancy map, it's not looking at the image whatsoever. And so we can plot out, we built in some charts to see how much does the model pay attention to the image, finding it's not looking at the image whatsoever. We also ask, we can find some different hallucinations, like if you say, is the elderly person sitting? They'll say, yeah, the person's sitting. Is the young ballerina not a character in the image? Is that person sitting? They'll say, yes, that person's sitting. We can again see with our charts that the model wasn't looking at the image at all. And then finally, it's good for some sanity checks to see, when the model answers questions correctly, is it doing it appropriately? And so with our app, you can hand color the images, and we ask, what color is the man's shirt? And it'll say yellow, purple, or green, and it answers correctly. And so with our saliency maps, again, you can see, yes, it's looking at the shirt as you would hope. And we can look at our charts before and see, again, yes, it really is looking at the image. We are quite confident that the model is not just guessing correctly, but truly looking at the image. And so finally, we can ask negative questions. Is the person's shirt blue? And once again, yes, indeed, it's looking at the shirt as we would hope. And so in summary, I've presented my web app on how to interpret large vision language models. We unify multiple explainable AI methods, and we put them into a nice, easy to use web framework. I will say I am looking for collaborators on a new project I'm starting on mechanistic interpretability. So if that's something you're interested in, find me. And also we were just approved for a new early career scientist. If you want to join part of our lab, please come find me at the poster afterwards. Thank you.
Any quick questions or virtual questions? All right, we'll go ahead and on to our next invited speaker. Thank you.
Oh, wait, you're right.
Sorry, we're going to a poster session, not the next invited speaker. Same board, same room, and the board that you're assigned to is also the same.
And please be back here by 4 p.m. for the next talk.
We're even getting a little tired.
outputs and enhance user understanding.
And so this
The
is,
semantic consistency score
they
we
must be
propose
getting that,
here is
right?
a simple approach to this problem that leverages multimodal embedding models.
No, but that's if they're speaking.
Clip score. To evaluate the model, we have some input prompt, which is used to generate n iterations.
Okay, I'm
of a
gonna go
model.
outside
In
and
this
see if I
study,
can
we
hear it.
examined two open source models, Stable Diffusion XL and Pixar Alpha. These n iterations are then passed through the clip image encoder and a pairwise cosine similarity
Yeah, I can hear.
is computed across embeddings for each iteration. When comparing SDXL and Pixar Alpha, we found that the distributions of consistency scores across the models were significantly different. For each pair of resulting models, you would labeled which image was the most consistent. The model with the highest semantic consistency score matched the most common selection among annotators 94% of the time. We also looked at the impact of fine-tuning of the semantic consistency score.
So
The
Peter is
distribution
staying here. Do you want coffee? Do you want to bring up like the snacks and coffee for me, and then I'll just go around closer to make sure everything's going okay?
It's important to note that there exists biases in embedding models like Clip.
In that case, I'll just take my stuff.
It should be explored. The idea behind this paper is to start a conversation around consistency in diffusion model image generation and find new ways to harness the power of multimodal embedding models for explainability. All code and data generated for this study are available in GitHub and Hugging-Face.
All right, cool. So that was my actually.
Welcome to our presentation of SUNNY, a visual interpretation framework for convolutional neural networks from a necessary and sufficient perspective. This is a collaborative work by the University of California, Davis, and National Taiwan University. Saliency maps are widely adopted for CNN interpretation, aiming to highlight the most important input features for model decisions. However, existing approaches often focus more on model parameters, overlooking the fundamental why behind their decisions. Aligned with counterfactual thinking intrinsic to human cognition, SUNNY rationalizes CNNs from the causal sufficiency and necessity perspective. Our method considers the input features as hypothetical causes and the model's predictions as outcomes. The causal necessity, N, is measured by the outcome differences when changing the causes, while sufficiency, S, is measured by the outcome stability when specific causes are unchanged. Inspired by Shapley values, we define the N as Shapley values to quantify the causal importance of input features bidirectionally. Our framework starts with a forward pass through the CNN to extract feature match. Then we obtain corresponding input features and perform interventions by removing or keeping them respectively. Following the definitions, we compute N and S Shapley values. The necessity and sufficiency heat maps are constructed by the weighted integration of feature maps. We evaluate SUNNY on 2 benchmark datasets using 3 different CNN architectures, where we compare SUNNY with 7 baseline methods to assess its effectiveness in providing class discriminative explanation. The quantitative evaluation with metrics such as the deletion insertion and energy pointing games indicate SUNNY's superior performance over competitors. By visually comparing with others and validating the sanity check results, SUNNY's capability of providing high-quality explanation can be further proven. Please check out the full paper for more details.
Hello, my name is Mohammad Reza, and I'm going to present our paper, Allowing Humans to Interactively Guide Machines Where to Look Does Not Always Improve Human AI's Team's Classification Accuracy. In this study, we explore a binary classification task where humans and AI collaborate. The AI receives an image of a bird and provides both a prediction and an explanation for its prediction. The human must then decide to accept or reject AI's decision. Current explanation models only offer one static explanation for each prediction. The question we want to address here is, what if we allow users to interact and manipulate the AI attentions to generate more prediction and explanations? We modify CHM core to allow the user to select specific regions on the image, forcing the AI to focus its attention on the chosen region.
In this example, the user selects only the body of the bird, which leads to the prediction of summer danger. After seeing the prediction, the user can decide to include beak, which leads to the correct prediction. We ran a study to measure the effectiveness of this approach and report two major findings. First, we found that despite being able to interact with the AI models, AI errors are still very challenging for human users to recognize. This aligns well with previous studies in XAI that show humans, even those with machine learning expertise, are easily fooled into accepting AI predictions. The second finding is interactivity does not improve overall human decision-making accuracy or static explanations. This finding goes against the popular hypothesis from the community that interactivity can improve human AI team accuracy. However, we found that for certain cases, interactivity is indeed more helpful than static explanations. In conclusion, we have open sourced our interactive interface to lay the groundwork for future work. Although we did not observe an improvement in human performance, we believe our interface can benefit other user-centric aspects of XAI, such as trust calibration, user satisfaction, and perception.
Hello, and welcome to a brief presentation of our work titled CA String, Attention-Based Pooling for Interpretable Image Recognition. What we present is an attention-based pooling mechanism that includes interpretability measurements on existing CNN models. How we do it is we introduce a cross-attention string that runs in parallel to existing CNN models, updating a class-agnostic representation, a zeros token, with feature maps found at critical stages of a model, generating a representation that is used to replace gap during inference to produce explanation. Overall, our approach improves interpretability measurements of existing CDC map methods. It provides class-agnostic raw attention maps, as well as maintains the representation properties of each one of the used. We validate qualitatively our experiments using class activation methods on both Pascal and ImageNet datasets, as well as we provide raw attention images on the MIT 67 dataset. This last dataset is important because it highlights the capacity of our class-agnostic raw attention maps to capture salient information from images and classes that it never saw during training. Conversely, regarding the quantitative experiments, we evaluate the interpretable properties following interpretability evaluation of two different class activation methods on both ImageNet and Pascal dataset. Experiments here demonstrate that our updated representation provides improvements for interpretability evaluation of different class activation methods, enhancing the interpretable properties that they made on them. We expect to see in our poster for further details.
Why does a model predict an image as private? I'm Miriam, and I will show you which objects influence privacy decisions. Most people don't realize that sharing images online can reveal sensitive information. Designing a tool that warns them and also explains the decision is challenging. We consider a pipeline that first detects objects in an image and then uses a privacy model to recognize if the image is private from these objects. To quantify the influence of objects on models' decisions, we used an explainability method that assigns scores to object features. Here are objects detected in private images correctly classified by a privacy model. The presence of a person influences the model. The number of objects has less impact. Here we show the scores obtained from two models on private images correctly classified. Person is the most relevant concept for both models. Interestingly, one model tends to classify images as public when more than two people are detected. So we derived two classification strategies that are explainable by design. The first one classifies an image as private if at least one person is detected.
Yeah, it's HDMI.
The second one does so if only one or two people are detected.
Like your laptop is.
The hybrid code in the private class for the first strategy will reflect that
Thank you so much. Yeah.
many private images contain people in the dataset. However, images with people are not always private. If you want to design a privacy model, make sure that it is not biased by the presence of people by comparing it to our person-centric strategies.
Yeah, so there were poster session that's going on. So the poster session at 4E, we're displaying talks, like 2 minutes snippets, starts from 4 o'clock. Okay. Yeah, so there are 2 talks. Yeah. I'm Pushkar. Nice to meet you. You are? Oh, wow, that's very good. Oh, nice. That's actually quite good. So a lot of my friends went to Manipal for their undergrad. Yes. So I'm currently at Toyota Technological Institute, TTIC, Chicago. It's a philanthropic institute by Toyota for PhD. So I'm pursuing a PhD. And a full-time PhD. Full-time. So it's like Toyota family founded a college. Also something like that. In the US to do AI research. So it's yeah.
When we are into research,
yeah.
Manipal students come here for master's.
Yeah, they're very like Manipal is actually quite one of the good universities. But my friends were from the 2013-14 batch, so not sure if you like overlap. But oh, you are nice. Oh, nice. But it's very beautiful. I've heard the whole. Is this your first CV?
Yeah.
Nice. Are you liking it? Oh, yeah, of course. Of course. So
yeah, it's a good experience.
Yes.
Are
you whom are you working with? Oh, University of Central Florida, right? There's also a professor called Bharat Shah there. Yes. Okay. So he came for a talk in TTI. Good friends of my advisor, but he had these. Yes. Oh, Bharat Shah. So he had a very famous set of lectures on computer vision and on YouTube. So yeah, he has an interesting sense of humor. Yeah. Okay, a good one.
How many years of PhD over now?
So this is my 5th year.
Oh. Publication, is it mandatory there? Or is
Yeah, it is mandatory. So they expect typically three top tier conferences.
So similar, the conference paper.
Top tier, like A-star.
A-star.
So like the only thing is they don't publish in journals in the US. So it's only
for us it's like 3 SCI index.
Yes. Yeah, so that's like the number is the same, but it's more conferences versus journals.
A-star also takes 1 year. Journal mostly takes 1 year.
Yeah, A-star it takes a year. I think it's more about if you get the idea right, like you know. So I think the first one takes a lot of time. Then it starts becoming easier. And also they are like 2 should be submitted because 3 pair and all can be very competitive also. So if 2 are published and the 3rd one is submitted, then also they are okay. Yeah. And
A-star ICC. You are into medical thing or different?
No. I am in computer vision purely.
You that's too.
Yeah. So it's like CPPR, ICCV, ECCV, sometimes UREP. So yeah, but the advices are very relaxed. Like they're
Yeah, here it might be different.
Yeah, it's not like India, where like publish. Here, in my advice, also it's more about the quality of application than the quantity.
See, few professors, they were like training their students.
Yeah. So my advisor has never contacted me in a weekend. And for the first 5 years, I didn't have a number. The only time he gave me a number when I said my tire was flat and I could not attend a meeting. So like, if you need anything, just contact me on this number.
Oh, that is nice.
Yeah. So he is very helpful and yeah.
Yeah, I saw it came before.
You should also like the next stop is.
Meaning,
Yeah,
that's
exactly.
why it came
Yeah. He's
So
very
I
nice.
take the one.
He's a very nice professor. Oh, nice. So
4 o'clock they told.
so 4 is Leon stuff.
Oh, is it?
It's just here.
Then after that.
So 4:30 is Leon stuff. But just cross check. I might be wrong also. Yeah.
Okay.
Today, I will be presenting our work on a semantic approach to quantifying the consistency of diffusion model image generation. There exists variability in diffusion model image generation due to the stochastic elements inherent to the diffusion process, and there are differences in the level of variability across different models. In real-world problems, how do we reconcile the desire for diversity and creativity in generated outputs with the need for consistency and coherence relative to the input prompt? By quantifying consistency, we can enable decisions reconciling creativity and consistency for particular applications, detect unintended bias, validate interpretations of model outputs, and enhance user understanding. The semantic consistency score we propose here is a simple approach to this problem that leverages multimodal embedding models with a pairwise mean clip score. To evaluate a model, we have some input prompt, which is used to generate n iterations from a model. In this study, we examined 2 open source models, Stable Diffusion XL and Pixar Alpha. These n iterations are then passed through the clip image encoder, and a pairwise cosine similarity is computed across the embeddings for each iteration. When comparing SDXL and Pixar Alpha, we found that the distributions of consistency scores across the models were significantly different. For each pair of results from the models, human annotators labeled which image was the most consistent. The model with the highest semantic consistency score matched the most common selection among annotators 94% of the time. We also looked at the impact of fine-tuning on the semantic consistency score. The distributions of scores across base SDXL and SDXL fine-tuned on Monet paintings using low-rank adaptation were significantly different. It's important to note that there exist biases in embedding models like CLIP. Alternative models and other consistency methods should be explored. The idea behind this paper is to start the conversation around consistency in diffusion model image generation and posit new ways to harness the power of multimodal embedding models for explainability. All code and data generated for this study are available in GitHub and Hugging Face.
Welcome to our presentation of SUNNY, a visual interpretation framework for convolutional neural networks from a necessary and sufficient perspective. This is a collaborative work by the University of California, Davis, and National Taiwan University. Saliency maps are widely adopted for CNN interpretation, aiming to highlight the most important input features for model decisions. However, existing approaches often focus more on model parameters, overlooking the fundamental why behind their decisions. Aligned with counterfactual thinking intrinsic to human cognition, SUNNY rationalizes CNNs from the causal sufficiency and necessity perspective. Our method considers the input features as hypothetical causes and the model's predictions as outcomes. The causal necessity, N, is measured by the outcome differences when changing the causes, while sufficiency, S, is measured by the outcome stability when specific causes are unchanged. Inspired by Shapley values, we define the N as Shapley values to quantify the causal importance of input features bidirectionally. Our framework starts with a forward pass through the CNN to extract feature maps. Then we obtain corresponding input features and perform interventions by removing or keeping them respectively. Following the definitions, we compute N and S Shapley values. The necessity and sufficiency heat maps are constructed by the weighted integration of feature maps. We evaluate SUNNY on 2 benchmark datasets using 3 different CNN architectures, where we compare SUNNY with 7 baseline methods to assess its effectiveness in providing class discriminative explanation. The quantitative evaluation with metrics such as the deletion insertion and energy pointing games indicate SUNNY's superior performance over competitors. By visually comparing with others and validating the sanity check results, SUNNY's capability of providing high-quality explanations can be further proved. Please check out the full paper for more details.
Hello, my name is Mohammad Reza, and I'm going to present our paper, Allowing Humans to Interactively Guide Machines Where to Look Does Not Always Improve Human AI's Team's Classification Accuracy. In this study, we explore a binary classification task where humans and AI collaborate. The AI receives an image of a bird and provides both a prediction and an explanation for its prediction. The human must then decide to accept or reject AI's decision. Current explanation models only offer one static explanation for each prediction. The question we want to address here is, what if we allow users to interact and manipulate the AI attentions to generate more prediction and explanations? We modify CHL core to allow the user to select specific regions on the image, forcing the AI to focus its attention on the chosen region. In this example, the user selects only the body of the bird, which leads to the prediction of summer tanager. After seeing the prediction, the user can decide to include beak, which leads to the correct prediction. We ran a study to measure the effectiveness of this approach and report two major findings. First, we found that despite being able to interact with the AI models, AI errors are still very challenging for human users to recognize. This aligns well with previous studies in XAI that show humans, even those with machine learning expertise, are easily fooled into accepting AI predictions. The second finding is interactivity does not improve overall human decision-making accuracy or static explanations. This finding goes against the popular hypothesis from the community that interactivity can improve human AI team accuracy. However, we found that for certain cases, interactivity is indeed more helpful than static explanations. In conclusion, we have open sourced our interactive interface to lay the groundwork for future work, although we did not observe any improvement in human performance. We believe our interface can benefit other user-centric aspects of XAI, such as trust calibration, user satisfaction, and perception.
Hello, and welcome to a brief presentation of our work titled CA Stream, Attention-Based Pooling for Interpretable Image Recognition. What we present is an attention-based pooling mechanism that improves interpretability measurements on existing CNN models. How we do it is we introduce a cross-attention screen that runs in parallel to existing CNN models, updating a class-agnostic representation, a CLS token, with feature maps found at critical stages of a model, generating a representation that is used to replace gap during inference to produce explanations. Overall, our approach improves interpretability measurements of existing CLS map methods. It provides class-agnostic attention maps, as well as maintains the recognition properties of each model that we use. We validate qualitatively our experiments using class activation methods on both Pascal and ImageNet datasets, as well as we provide raw attention images on the MIT 67 dataset. This last dataset is important because it highlights the capacity of our class-agnostic attention maps to capture salient information from images and classes that it never saw during training. Conversely, regarding the quantitative experiments, we evaluate the interpretable properties following interpretability evaluation of two different class activation methods on both ImageNet and Pascal dataset. Experiments here demonstrate that our updated representation provides improvements for interpretability evaluation of different class activation methods, in turn enhancing the interpretable properties that they might convey. We expect to see you in our poster for further details. Thank you.
Why does a model predict an image as private? I'm Miriam, and I will show you which objects influence privacy decisions. Most people don't realize that sharing images online can reveal sensitive information. Designing a tool that warns them and also explains the decision is challenging. We consider pipelines that first detects objects in an image and then uses a privacy model to recognize if the image is private from these objects. To quantify the influence of objects on models' decisions, we used an explainability method that assigns scores to object features. Here are objects detected in private images correctly classified by a privacy model. The presence of a person influences the model. The number of objects has less impact. Here we show the scores obtained from two models on private images correctly classified. Person is the most relevant concept for both models. Interestingly, one model tends to classify images as public when more than two people are detected. So we derived two classification strategies that are explainable by design. The First one classifies an image as private if at least one person is detected. The second one does so if only one or two people are detected. The hierarchical in the private class for the first strategy reflects that many private images contain people in the dataset. However, images with people are not always private. If you want to design a privacy model, make sure that it is not biased by the presence of people by comparing it to our person-centric strategies.
Today, I will be presenting our work in a semantic approach to quantifying the consistency of diffusion model image generation. There exists variability in diffusion model image generation due to the stochastic elements inherent to the diffusion process. And there are differences in the level of variability across different models. In real-world problems, how do we reconcile the desire for diversity and creativity in generated outputs with the need for consistency and coherence relative to the input prompt? By quantifying consistency, we can enable decisions reconciling creativity and consistency for particular applications, detect unintended bias, validate interpretations of model outputs, and enhance user understanding. The semantic consistency score we propose here is a simple approach to this problem that leverages multimodal embedding models with a pairwise mean clip score. To evaluate a model, we have some input prompt, which is used to generate n iterations from a model. In this study, we examined two open source models, Stable Diffusion XL and Pixar Alpha. These n iterations are then passed through the clip image encoder, and a pairwise cosine similarity is computed across embeddings for each iteration. When comparing SDXL and Pixar Alpha, we found that the distributions of consistency scores across the models were significantly different. For each pair of results from the models, human annotators labeled which image was the most consistent. The model with the highest semantic consistency score matched the most common selection among annotators 94% of the time. We also looked at the impact of fine-tuning on the semantic consistency score. The distributions of scores across base SDXL and SDXL fine-tuned on Monet paintings using low-ranked adaptation were significantly different. It's important to note that there exist biases in embedding models like CLIP. Alternative models and other consistency methods should be explored. The idea behind this paper is to start the conversation around consistency in diffusion model image generation and posit new ways to harness the power of multimodal embedding models for explainability. All code and data generated for this study are available in GitHub and Hugging Face.
Welcome to our presentation of Sunny, a visual interpretation framework for convolutional neural networks from a necessary and sufficient perspective. This is a collaborative work by the University of California, Davis, and National Taiwan University. Saliency maps are widely adopted for CNN interpretation, aiming to highlight the most important input features for model decisions. However, existing approaches often focus more on model parameters, overlooking the fundamental why behind their decisions. Aligned with counterfactual thinking intrinsic to human cognition, Sunny rationalizes CNNs from the causal sufficiency and necessity perspective. Our method considers the input features as hypothetical causes and the model's predictions as outcomes. The causal necessity, N, is measured by the outcome differences when changing the causes, while sufficiency, S, is measured by the outcome stability when specific causes are unchanged. Inspired by Shapley values, we define the N as Shapley values to quantify the causal importance of input features bidirectionally. Our framework starts with a forward pass through the CNN to extract feature maps. Then we obtain corresponding input features and perform interventions by removing or keeping them respectively. Following the definitions, we compute N and S Shapley values. The necessity and sufficiency heat maps are constructed by the weighted integration of feature maps. We evaluate Sunny on 2 benchmark datasets using 3 different CNN architectures, where we compare Sunny with 7 baseline methods to assess its effectiveness in providing class discriminative explanation. The quantitative evaluation with metrics such as the deletion insertion and energy pointing games indicate Sunny's superior performance over competitors. By visually comparing with others and validating the sanity check results, Sunny's capability of providing high-quality explanations can be further proved. Please check out the full paper for more details.
Hello, my name is Mohammad Reza, and I'm going to present our paper, Allowing Humans to Interactively Guide Machines Virtual Does Not Always Improve Human AI's Team's Classification Accuracy. In this study, we explore a binary classification task where humans and AI collaborate. The AI receives an image of a bird and provides both a prediction and an explanation for its prediction. The human must then decide to accept or reject AI's decision. Current explanation models only offer one static explanation for each prediction. The question we want to address here is, what if we allow users to interact and manipulate AI attentions to generate more prediction and explanations? We modify CHF core to allow the user to select specific regions on the image, forcing the AI to focus its attention on the chosen region. In this example, the user selects only the body of the bird, which leads to the prediction of summer tanager. After seeing the prediction, the user can decide to include beak, which leads to the correct prediction. We ran a study to measure the effectiveness of this approach and report 2 major findings. First, we found that despite being able to interact with the AI models, AI errors are still very challenging for human users to recognize. This aligns well with previous studies in XAI that show humans, even those with machine learning expertise, are easily fooled into accepting AI predictions. The second finding is interactivity does not improve overall human decision-making accuracy or static explanations. This finding goes against the popular hypothesis from the community that interactivity can improve human AI team accuracy. However, we found that for certain cases, interactivity is indeed more helpful than static explanations. In conclusion, we have open sourced our interactive interface to lay the groundwork for future work. Although we did not observe an improvement in human performance, we believe our interface can benefit other user-centric aspects of XAI, such as trust calibration, user satisfaction, and perception.
Hello, and welcome to a brief presentation of our work titled CA Stream, Attention-Based Pooling for Interpretable Image Recognition. What we present is an attention-based pooling mechanism that improves interpretability measurements on existing CNN models. How we do it is we introduce a cross-attention screen that runs in parallel to existing CNN models, updating a class-agnostic representation, a CLS token, with feature maps found at critical stages of a model, generating a representation that is used to replace gap during inference to produce explanations. Overall, our approach improves interpretability measurements of existing CLS map methods. It provides class-agnostic attention maps, as well as maintains the recognition properties of each model that we use. We validate qualitatively our experiments using class-activation methods on both Pascal and ImageNet datasets, as well as we provide raw attention images on the MIT 67 dataset. This last dataset is important because it highlights the capacity of our class-agnostic recognition maps to capture salient information from images and classes that it never saw during training. Conversely, regarding the quantitative experiments, we evaluate the interpretable properties following interpretability evaluation of two different class activation methods on both ImageNet and Pascal dataset. Experiments here demonstrate that our updated representation provides improvements for interpretability evaluation of different class activation methods, and try enhancing the interpretable properties that they might convey. We expect to see in our poster for further details. Thank you.
Why does a model predict an image as private? I'm Miriam, and I will show you which objects influence privacy decisions. Most people don't realize that showing images online can reveal sensitive information. Designing a tool that works and also explains the decision is challenging. We consider pipelines that first detects objects in an image and then uses a privacy model to recognize if the image is private from these objects. To quantify the influence of objects on models' decisions, we used an explainability method that assigns scores to object features. Here are objects detected in private images correctly classified by a privacy model. The presence of a person influences the model. The number of objects has less impact. Here we show the scores obtained from two models on private images correctly classified. Person is the most relevant concept for both models. Interestingly, one model tends to classify images as public when more than two people are detected. So we derived two classification strategies that are explainable by design. The first one classifies an image as private if at least one person is detected. The second one does so if only one or two people are detected. The hierarchical in the private class for the first strategy reflects that many private images contain people in the dataset. However, images with people
Not. Oh, that is not. Gotta mute myself. Fix that. Okay, cool. Yes. So actually, I'm going to just send you a link.
Sure.
I'm going to email you a link. Just email it. Oh, okay. Fine.
Stop sharing.
Just keep sharing for now. I need to make a co-host.
Join the audio.
No. We can just say join with computer audio, and we can just recording in progress. And mute yours, yes. And so, okay, perfect. So you'll be speaking. So mine is gonna get all the audio.
Okay.
Okay. So can you take your laptop outside and just do an audio test? I'll just message you to ask if you can hear what's going on. Okay, I'm actually gonna make you a co-host as well. What is your, is this you?
I don't know. Should be my name, but
I think this, let me try it and it'll show up on your screen if I made you a co-host. Yeah, it was you.
Okay.
Okay, so stop sharing screen real quick. You can stop sharing screen. You can stop sharing screen. Okay, now try sharing screen. So you have to pick your place. Okay, here. Okay, so can you hear me on Zoom? Can you hear me on Zoom? Okay. Maybe just condense that a little way. Yeah. Actually, yeah, that's show there. Feel free to, so he'll introduce you. Really not change anything. I'm hoping mine doesn't take out the audio again, but if it does, we have yours as backup. Okay, go ahead and in about 30 seconds.
Should be great.
Hold on, you can work it. Let's sort out.
Yeah.
Go ahead. Go ahead and get started. I think it's 4, right?
Could we wait a minute or so?
Okay, fine. We'll wait.
Okay, hi everyone. It's my great pleasure to introduce our next invited speaker, Professor Leonid Vigal. He is an associate professor in the Department of Computer Science, the University of British Columbia. He was awarded Canada Research Chair in Computer Vision and Machine Learning and is a remote faculty member of the Vector Institute for AI in Toronto. In addition, he serves as an academic advisor to Korean AI. He received his PhD from Brown University and has previously held positions at Disney Research, Carnegie Mellon University, and the University of Toronto. Professor Vigal's research interests lie in the area of computer vision, machine learning, and computer graphics, but also borders the fields of psychology and humanoid robotics. He is particularly interested in statistical and machine learning models for problems of visual inference, understanding, and reasoning. His work has received the Best Paper Awards at WACME and the Articulate Motion and Deformal Optics. He will now give a talk on understanding, control, and debiasing of text-to-image models. And please welcome.
Thank you very much. Thank you for the warm introduction and for all the organizers for getting me here and giving me an opportunity to give this talk. So this talk, as the title suggests, is going to be, we'll be talking about mostly test time performance of text-to-image models and controllability and interpretability that comes along with them. So text-to-image models is a subcategory of generative models that are trained to generate visual content conditioned on text. So there's many variants of these now. Some of them are sort of public implementations such as Stable Diffusion and Latent Diffusion. Others are actual commercial products like Midjourney, or the latest and greatest is Sora, which can generate videos in this way, really quite stunning quality. And most of these models, or all of the models on this slide, actually build on top of diffusion models as the mechanism for actually doing the generation. So most of you are probably familiar with those, but I'll just take a minute to kind of introduce them so that we have the same vocabulary going forward. So the diffusion models are very simple conceptual class of models where you have essentially learn a process that takes a noisy variant of an image and denoises it to make it crisper and cleaner. And the way these models are trained is that first you generate sort of noisy variants of your clean data, and this is what's called forward diffusion process. And then you train typically a neural network like UNet or something else to actually undo those noise perturbations progressively, sort of one step at a time. And usually if you run this reverse diffusion process forward about 1,000 steps, you get a nice and clean image at the very end. So the example is over here where you start from noise, and if you do a few steps, you get kind of a noisy image that you see on the output here. And then if you feed that as an input, again, then after a few more steps, you get a nice and clean image out. Now, generating high quality images is great, but it's not practically very useful. So typically what you want to do is condition them on some sort of input. And typically this takes the form of textual prompt, where what you want to specify is kind of what is the final image should actually contain in terms of the content, visual content that you're trying to produce. And so in this way, you're just basically taking a prompt, you're encoding it using some other neural network, and then feeding it as an additional context to the UNet or other architecture, whatever is modeling the reverse diffusion process. And that allows you to actually control the generative process so that you generate what you actually desire, specified by the textual prompt. And so this is some of the results that you get in this way, right? Once you train the model, you can feed it a prompt like baby sitting in a poppy field. You get a nice visual like this from Midjourney version 5. And you can do different prompts of various complexity and get various sort of visuals like this. So that kind of underpins all of these models. And what I'm going to particularly focus on and what we've been looking at mostly is stable diffusion and latent diffusion, because those are public implementations we can play with. But what I'm going to talk about more or less will apply to all our variants as well. And for latent diffusion, the only difference to what I've talked about is that when we're doing this reverse diffusion process and we're learning this network, instead of doing it in a pixel space, we're going to have an encoder and a decoder that's going to encode the input noisy image and then do the diffusion in the encoded latent space, and then decode the cleaned up, essentially latent representation into the final image. And that's a lot more efficient. All right, so now that we have sort of these text-to-image models that are now kind of a commodity with latent diffusion, stable diffusion, all of these different variants, they can generate stunning visuals. But what we want to do is kind of analyze what they actually do when we're trying to do that. Right, so let's consider a case where we want to generate an image. So we have in our mind some variant like this, which is something of what we want to generate. Right, it could be in our mind, or maybe we found an image on Google or something, and we want something of that style. And so the first thing we're going to do is try to essentially come up with a prompt that describes what we actually envision or what we want, push that into the diffusion model of our choice, and then out come the visual, right? And we look at that, and it may not look like what we want, right? So if we just say a cabin in the mountains, this in particular case, it doesn't have snow and other aspects that we were actually looking for. So we may want to modify that prompt and say something like a cabin in the mountains during winter and snow. And now it's a little better. It has snow, but now it has people, which we didn't want. And we can go through this process, keeping to modify the prompt to get sort of closer and closer to what we envision the actual output. And eventually we might end up with something like this, a cabin in a snowy mountain in a style of Disney, which will actually produce an image very much like the one you sort of we were envisioning. And so this sort of brings about the first issue I wanted to talk about, which is prompt engineering. So in order to actually generate the image that we desire, a lot of times we have to go through this iterative process of actually modifying the prompt in order to produce what we actually like. And this is difficult both because you have to go through this iterative process. You have to be able to describe what you actually want in natural language. So you need to have the right vocabulary to do that, but also the vocabulary in which you describe it might be a function of actually what the model has been trained on. Like, for example, if it never heard of cabins, but heard of buildings, now you have to name it a building in order for it to understand what you're talking about. And usually you don't have access to the data they've been trained on or distributions to actually know what kind of vocabulary would be best suited to actually generate the model. And so this has kind of introduced a whole subfield of prompt engineering. And if you want to make a lot of money, that's actually a pretty good field to be in. So you can make quite a bit. But it's still an issue because it does take a while to get those prompts. And what's more importantly is that if you don't get what you want at the end, it's very hard to tell whether it's an issue with the model, right? The model can't actually generate the visual that you want, or it's the issue that you haven't actually figured out what the right prompt is to actually generate what you want. So it can, but you just haven't figured out what the right inputs are. And so this was the premise for our work, which was done by Schiele, sitting right there. We're in collaboration with my PhD student Tanzila and in our faculty at UBC, which we call prompting hard or hardly prompting. And it's looked at trying to invert the diffusion model, essentially. So this is going to be presented at the main conference tomorrow. So the problem definition here, what we're trying to do is essentially invert the diffusion model. So given an example of a visual that we want, what we'd like to do is figure out what prompt most likely would lead to that visual. And if we're able to do that, then we'll be able to also have ability to control how we generate, right? We can just essentially edit the textual prompt directly to add additional content that we want to show up in that scene and so on and so forth, right? So that's the goal. And conceptually, this is relatively simple, right? So we have our diffusion model, which I introduced before. We can sample some sort of noise. We know what visual we actually want to get. Let's say we have a sample image, right? So we can fix that. And then what we need to do is optimize the textual prompt that was most likely produce that image under the different noising, noising perturbations. So that's pretty simple conceptually, but there are some practical challenges that we need to overcome. The first one is that each diffusion step is inherently noisy, right? Because the noise will modulate the gradients. And so it makes it pretty hard to estimate really accurate gradients. And so in order to deal with that, we actually ended up going with a second order optimizer instead of the SGD. And that works a lot better in practice for this problem. Now, the second challenge is that tokens are discrete, right? What we want to be able to reproduce is actual text. And so that means there's a discrete operation where we went from a discrete set of words into essentially a text embedding. So in order to differentiate from that discrete operation, that's a little bit difficult, right? One solution you may imagine is that we can do optimization in just the space, the contiguous space of word embeddings. And then after we're done, basically pick the words that are closest to those embeddings. Turns out that doesn't actually work very well. We've done some experiments with that. So instead, what we do is project the gradient descent. So after each step, we basically project onto a vocabulary, pick the closest vocabulary atom, and then continue in that optimization rather than doing it at the very end. And then the last challenge that it turns out that the diffusion steps are not sort of equally affected by the conditioning, right? So there's many diffusion steps, 1,000 in this process, and not all of them are affected in the same way. And so picking which actual steps do we want to invert is quite important. So here is a visualization of that. So what you see is the target image on the very left. And on the bottom are different inversions of the text that we would get if we inverted those steps within the diffusion process. And on the top are basically images that would result if we actually feed those inverted prompts back into the diffusion model to generate some new visuals. So ideally, those visuals should be close to what our target image was. And what you can see here is if we look at the very noisy step, so where there's more noise, essentially the diffusion is dominated by noise and there's mild interactions with the conditioning. And so it's hard to get that conditioning basically out. And if we look at the other side where there's very little noise, then essentially all of the semantics is already in the image and conditioning is no longer necessary because all you're improving is individual sort of pixels. And so ultimately what we found is kind of these middle steps are the most useful in this process. And this is how we can get nice and semantic prompts, which are also in, sort of fluent. So now that we have this approach, we can actually do this for a variety of images. So of course, the output is also going to be a function of the text encoder that we use. So for example, there's different typical encoders that you use in diffusion models, T5, CLIP, and BERT. And they basically, in terms of quality, go in that order. So T5 is most expressive, CLIP is a bit less expressive, and BERT is the least expressive of the three. And you can see the inverted prompts that you get for the two images here, which in the case of T5 actually is quite readable and contains the semantics of the images that are there. If you go to CLIP and BERT, then the semantics are still there, but it looks a little bit more like bag of words because those are sort of inferior text encoders. So there's less of a textual prior. All right, so now that we have this model, we can also apply it to a few applications. So here, what we've done is a few target images. We estimate the prompts and also use the prompts to feed back into the diffusion process to actually generate sample images. And you can see that both the prompts are fairly fairly good, and the images that result are quite representative of the target images as well. Now, in comparison, if we compare to a prior method, you can see that the prompts aren't quite as readable, and the images are also not quite as good, not as close to the original targets. Now, we can use this for a number of applications. For example, compositional generation. So here, let's say we want the cabin on the left, but we want it in the style that's on the right, essentially in this artistic acrylic style. So what we can do is, instead of describing that in text, we can take those two examples. We can invert the prompts to get the textual prompts from them. Then we're simply going to concatenate that text and pass that concatenation into our diffusion generative model. And this is the outputs that's going to come out. Right? So it looks pretty good. Basically, it still has the content of a left image, but in the style of the right, in this very easy, sort of simple concatenation textual format. Now, we may want to add some other visuals to this, for example, sheep. If we really want sheep in this, what we can do is, again, invert those two sets of images. So we can invert ones that we generated, invert the sheep, concatenate those, and now we're going to produce some new visuals with the concatenation. So that's a way of essentially composing different concepts together in a textual format, and you can directly edit those textual prompts as well. We can also do generation refinement. So here, if we start from a textual prompt, we generate some images, and let's say we like some of them and we don't others. We want to sort of narrow down on the set what we actually like. So in this particular case, for example, we like the fact that there is a flooded scene, but we don't like that there's boats in it. So what we can do is essentially treat the left two images as a positive set, the right two images as the negative set, and then use the inversion with positive and negative gradients coming from those two sets to do the inversion, and then use the inverted prompt to essentially prompt the diffusion model to generate some new visuals that would look like this. Right? So now to remove the boats, essentially. Now, finally, you can even do something like unsupervised segmentation. So given an image, what you can do is essentially do the inversion, get all the textual prompts, and then for every word, take the cross attention between that word and the patches in an image, and that allows you to generate essentially a heat map of where that object is in an image. And in our shameless plug, we have another paper that deals with essentially doing segmentation from cross attention in visual language models, and that's going to be presented tomorrow as well. All right, so that's the first thing I wanted to talk about, which is essentially how do we deal with these prompt engineering issues that we have with these models. And the second thing I wanted to talk about is the bias perpetration and exaggeration, such as racial bias and gender stereotypes and various others that these models have been known to exhibit. And so this is actually unpublished work, which is done with a number of my students who are in the audience, Adi and Gaurav, as well as Pushkar in the back there, and in collaboration with TTI, Kartik from Wharton, and Jerry from Carleton. And so what we're trying to do here is identify and evaluate biases in these text-to-image generative models, as well as mitigate them. Right, so these models, as I said before, can generate really nice visuals, but they do tend to exhibit various biases. Those could come in a variety of forms. One such bias could come just from real-world biases in the world. Right, for example, there are more men than women in computer science, and that just comes from labor statistics. Right, and so if we ask the model to generate a computer scientist, it is likely to generate a male interpretation of a prompt versus the female. But what's worse is that often it exaggerates those biases, and even sort of the misrepresentation is much worse than what it is in the real world. There's also incidental correlation. So for example, things like cows tend to occur on grass. And so if you ask the model to generate a cow, very often it'll generate one on grass, even if you ask it to generate it in other contexts, because it's only seen that kind of data. And a lot of these biases do come from training data sets and training procedures, and they're sort of embedded in these models. So we're not the first ones to look at this. Of course, there's other works that looked at bias detection. And often what they do is they essentially figure out what is the fixed set of biases that we want to look at. So those are typically things that are societally meaningful, like gender, ethnicity, skin color, right? Those are the biases that we want to ensure these models do not have. And then they build tools to essentially measure how much of such biases exists in these various tools. However, in practice, this works well when you're generating humans, for example, but in a lot of cases, these models are used to generate just objects or other things that are inhuman. And in those cases, some of those bias axes may not make sense. For example, if you're generating, capybaras getting married in Italy, knowing whether there's a gender or ethnicity bias doesn't make a lot of sense. I'm not sure what ethnicities capybaras are, right? And so what we wanted to do is have a more general approach that would essentially be able, for a given prompt, to figure out what are potential biases that may exist, and then figure out whether those biases are actually exhibited by the model or not. And so the way we're going to do this with this model that we call FET is that first we're going to use an LLM to figure out sort of what are potentially biases of axes for a particular prompt that we want to use for a generative model. And then for those biases, we're going to try to quantify how much bias there's actually is. So let me show you how that works. So let's do a simple example here. So let's say we have an input prompt, which is an old man in a church. So we start with this input prompt, and then we prompt an LLM to basically say what potential biases may exist for this particular prompt. And it's actually pretty good in identifying these biases. So for example, it would tell us that there's potential for physical appearance bias, for potential for culture bias, gender bias, racial bias, and a number of others. Now, once we have those potential bias axes, what we're going to do is prompt LLM again. So this is GPT-3 in our case, and try to get it to essentially propose a counterfactual prompts along each one of those dimensions. So for example, for a physical appearance bias, we can generate a counterfactual like a, sorry, I can't see, a middle-aged man, or a fit man, and so on and so forth, right? So we can essentially generate sort of these different counterfactuals to our original prompt. And we can do those counterfactual for each one of the potential bias axes that we have. Now, once we have all of these counterfactuals, what we can do is just use our model that we want to test whether it contains biases or not. That could be any model. In our case, we tried it with stable diffusion of both the older and the newer version. And we can generate a number of images using that model, using both the original prompt and all of the counterfactual prompts, right? So we can generate some set of images, let's say 48 for each one of those prompts. And so we get multiple sets of images now, right? One for each prompt, either original or the counterfactual. Now, once we have these sets of images, what we can do is analyze them for what kind of concepts they actually have in them. And we do that by building little histograms over the concepts. By running, you can do this in various ways, but we do it by using a BQA model, which we prompt to basically identify what's in the image, right? So you can ask it to describe the concepts of the image. You can ask it whether, what's the gender of a person in the image. There's other prompts that you can do to basically create a histogram of concepts that are in each individual set. And then we can compare these histograms between the original prompt and the counterfactual prompts for each individual axes, right? And so we can do that by aligning the two histograms along the similar concepts and basically computing intersection over union score of those two histograms, and that gives us what we call a CAT score. That's the score of similarity, and then we look at the variance of those scores to basically tell whether the bias exists. And the idea is that if all of the counterfactuals are basically different in the same manner, then there's no bias. And if one is sort of outstanding or does something very different, then you would see variance, and that would be an indication of bias. So now, given this sort of infrastructure, we can actually compute the biases for different axes. And in this particular case, you can see that the variance for abletism is higher, so that's the bias that is more prominent in this one. Now, what also trivially comes from this model is the fact, because we do this concept-wide decomposition, we can also look at sort of which concepts are actually contributing to the bias that exists, right? So that's kind of trivially comes out from this model as well. All right, so that's the entirety of what we've done in order to analyze sort of these biases using Tibet. And now for sort of the elephant in the room, right? What I've actually told you about is we're using LLMs and VLMs to analyze a text-to-image model. And so the question is, there could be biases in those models as well, right? And how that's going to affect the performance and so on. And so we did a lot of analysis in terms of actually validating that this works well and conforms to what humans would do on this data. And I'm not going to go through all the experiments that we've done there, but those are in the archive paper. All right, so now that hopefully you believe me that this works, we can actually apply it to a few test cases, for example, bias mitigation, right? The idea was going to be that we choose a prompt, we sort of figure out what bias exists for that particular prompt, and then we mitigate that bias to see if we get less bias sort of generation at the end. In this particular case, the prompt that we've chosen is a beautiful mountain landscape in Italy on the Dolomites. So this is exactly the type of prompt that sort of previous methods and sort of societal biases wouldn't be able to actually analyze. But in our case, we can generate a set of images, do all the counterfactuals, pass those into the Tibet model, and the Tibet model is going to come back and say that essentially the biggest bias that exists is one of perspective. And so what we can do is use the counterfactuals from analysis of that bias, pass it into ITI Gen, which is an existing bias mitigation model, and now generate a much more diverse set of images for the same prompt, right? So now, yep. So now we have a much better illustration of the same concept, but now it's much more diverse. We can also do this analysis across different professions. So here we analyze Stable Diffusion version 1.5 versus version 2.1. And as advertised in version 2.1, it tends to be less biased than the original. But if we apply our bias mitigation technique based on Tibet, then you can do even better. We can also do some cross intersectionality of biases analysis to basically see how different biases of genders, for example, differs based on geography. So if you prompt to generate essentially a pharmacist in North America, then it's actually, the model gives you sort of equal, more or less amount of male and female interpretations, whereas if you do this in Asia or other countries, then it actually gives you a much less balanced distribution. All right, so that's basically the end of it. So the take-home message is we have powerful generative tools now, and we need better ways to understand what they're able to generate, control those generative processes, and ensure that they behave in a responsible manner. And I just give you sort of two examples from my group where we're trying to do that, but there's sort of many others. So thank you very much. I'll take questions. Thanks to all of my group. Not just this work, but a lot of work that's going on and all of the funding sources that contributed to this in our works. And I'll take your questions. Thanks.
Are there any in-person questions? Please come up to the mic if so. If not, I will pull out a question from my question bank. Okay, so I was sort of wondering for the counterfactuals that were generated. I mean, in images, we generally are concerned whether or not they're realistic or not.
Yeah.
In terms of text, is that a concern, or is it just generally fine as long as it's good grammar?
So, I mean, ultimately, we're going to use those counterfactuals to prompt the generative model, right, the diffusion model. And those models do tend to usually generate good-looking things. They might not actually conform to what you want, right? So the fact that you're prompting it with a counterfactual doesn't necessarily mean that it's actually going to follow the instruction. And that's what the biases are going to actually measure in part. So yeah.
Okay, thank you. Are there any virtual questions? A virtual question? Okay, we'll go ahead and wrap that up and go ahead and give another round of applause.
change anything. I hope this didn't. Yeah, looks like it's fine. All right, so go ahead and.
Okay, so it's my great pleasure to introduce the final speaker of today, Professor Vineet N. Balasubramanian. He's a professor in the Department of Computer Science and Engineering at the Indian Institute of Technology, Hyderabad, in India, and was recently a visiting faculty at Carnegie Mellon University. He received his PhD from the Arizona State University. Professor Balasubramanian's research interests include deep learning, machine learning, and computer vision, with a focus on explainability, continual learning, and learning with limited table data. He is listed among the world's top 2% of scientists by Stanford University. He is an INSA Research Fellow and a recipient of the Google Research Scholar Award, NASSCOM AI Game Changer Award, and Research Excellence and Teaching Excellence Awards at IIT Hyderabad. He will now give a talk on moving beyond an afterthought towards learning by explanations. Please welcome him.
Thank you. Thank you very much, and thank the organizers for the opportunity to share our research at this venue. Let me get started. The quick TLDR for my talk is going to be that explainability has to go beyond being an afterthought, at least in applications, risk-sensitive applications that need them. So how do we learn models via explanations which are inherently interpretable? Okay.
Otherwise, I'll email you the link. Join, let me know, I'll make you a call.
Do I mute?
No. Just mute your volume. So like just mute your volume. Okay. All right, you're now a co-host.
We can share that.
Mm-hmm. You should be able to share screen.
Okay.
All right, sorry about that.
Okay, great. Okay, so that's the focus of the talk, to talk about how do you build inherently interpretable machine learning and deep learning models. So let me quickly go further. So I mean, explainability has had tremendous amount of work in the last decade, I would say. And a predominant amount of that work has been on post hoc approaches, where you develop methods that explain a model that was trained a priori. Right? So which means methods like LIME, SHAP, GradCam, and that entire gamut of models are all post hoc methods that you train after a model, methods that you use after you train a model. So they serve their purpose. They were very useful for all these years, but it may be time for us to move beyond that paradigm and see how you can learn via explanation, is what I'd like to advocate for. So in a sense, what we ideally want is explanation modules have been dealt with the way you see it here. So where they're added post hoc after a model is trained, we ideally want to move towards a setup where explanations are baked into the training process itself. So a slightly zoomed out view as to why you need this. If you look at the traditional supervised learning paradigm, right? So you have your data is given to a machine learning model, and you get labels. And your machine learning model is typically trained using one of several algorithms, and neural networks and deep learning being the most popular of late. If you just sat back and imagine that this is the way we taught our kids, right? You'd imagine we teaching our kids using multiple choice questions, all subjects from their kindergarten all the way to their PhD, right? So that's the way we've been teaching machines all these years. So what then should we do? We ideally want to go for an approach where you can go from learning via prediction, where you give an image of a cat, use a machine learning model, and it calls it a cat, towards maybe something like where you give the image of the cat, and the model now captures pointy ears, whiskers, beady eyes, four legs, furry coat, and so on, and hence reasons and says it's a cat because I can see all of these intermediate semantics. And that's what I'm referring to as going toward learning via explanations from learning via prediction, which is the de facto method today. Beyond giving reasoning, reliability and robustness come free in such an approach. Reliable because the model can explain how it arrived at a particular decision. And robustness because now you cannot change a few pixels and get all the intermediate semantics wrong, right? You could get one output label wrong, but it's very unlikely that you're going to change a few pixels and get all the intermediate semantics wrong, right? So these come for free with such an approach. I do know the first talk for today was perhaps quite closely aligned with a very similar thought process. So I had two directions of efforts planned for this talk. One was concept-based interpretability of deep learning models, which is what I spoke about. Another is on a different perspective to explainability itself, is on how do you integrate domain priors of attribution while training deep neural network models, right? So because I know an earlier talk talked about the first, probably an inherent interpretable approach significantly, I thought I'll focus a bit more on the second direction in this talk. But before I go there, I'll very quickly talk about some of our efforts on concept-based interpretability of deep learning models. One of our earliest work was in CVPR a couple of years ago, where we tried to bring this kind of a concept-based intermediate semantics into any neural network model, right? So the idea was, if you have any CNN, can you have a bypassing path here, where you have a set of concepts which you could learn in a supervised setting, in an unsupervised setting, or a semi-supervised setting. And those concepts are used to finally construct your final class label. Okay, this is what we had done at that point in time. I'm not going to go too much into this. As I said, I'll focus on the other work in this particular talk. But the overall idea here was an architecture where we had a few different losses, a fidelity loss, a reconstruction loss, and a classification loss, where we try to ensure the concepts that you learn as an intermediate step, firstly, are semantically well placed, they're semantically well grounded, but they're also useful in trying to predict the final class. That's what we tried to do in this particular work. And we showed that this was outperforming earlier baselines like self-explaining neural networks and concept bottleneck models and so on multiple benchmarks. We also showed there that you could do concept interventions, which means you could take a particular concepts that activate a class. Now, if you know there is a misclassification and you can identify which concept was wrong manually, then you go flip that concept manually and you now see that the class was turned out to be correct. That tells you how well the model learned that concept class relationship as part of the learning, right? And if you're interested more, this work is available on arXiv and the code is available. I'll leave it on the slides if you're interested to look at this further. We've also extended this work to prototype approaches to explaining neural network models. And also a more recent work is on how do you do continual learning with such concept-based work, right? So where you want to learn with concepts on transformer kind of models, but you also want to learn continually where newer classes and even newer concepts could be introduced over time. But for the remainder of this talk, I'm going to talk about maybe a different approach. I just thought I should give a different flavor of explainability perhaps for the session today, which is our work a couple of years ago on causal regularization with domain priors. This was joint work with students Gautam Srinivas and collaborator Amit, joint work with Microsoft Research. And this work is on providing causal explanations to neural network models. And before I get into causal, I thought I should just give a very quick primer on the topics that we need for me to explain this. The fundamentals of causality lie with a structural causal model, where you assume that all the data that we see around us comes from a structural causal model, where you have a causal graph, and the nodes of that causal graph are related through structural equations. That's how the SCM is constructed. And intervention is the notion of what would happen to a particular random variable x4 if x1 is set to a certain value. When you do that, your structural equations change because one of your variables gets set to a particular value, and that cascades across your structural equations, and that denotes the notion of an intervention in a causal process. And finally, the third topic that I need for just explaining what I'm going to talk about is the notion of a confounder in causality, where a confounder is a variable that influences an exposure and an outcome variable, causing a spurious correlation. The most popular example people quote is that if you have the data of, say, ice cream sales and shark attacks in a particular, say, in a certain area around the world, both of them peak in summer, but clearly there was a confounder, which is high temperature, that caused both of these, which makes you think that the other variables are correlated. Okay, those are the three concepts that we need to talk about further. Firstly, why do we need causal explanations itself? Why doesn't explainability as we use it today suffice? The same joint distribution, I'm quite sure all of you agree that supervised learning is primarily about modeling your joint distribution between your data and your labels. And it's very simple to show that the same joint distribution can actually be generated by different variable relations. Here is a very simple example, where at the bottom, you see the same joint distribution in 3 different cases. And you can see the Python code here, where in one case, X causes Y, in the other case, Y causes X, and in the third case, Z, a confounder, causes X and Y, and all 3 of them give exactly the same joint distribution, right? So you could ask the question, so why does it matter to me? My model works. Why does it matter which causal model it is? Things start getting tricky when you start changing variables now. If you intervene and set a particular variable to a specific value, now you see that each of these causal models give 3 different distributions. So which means if you want better generalization, you ideally want to isolate your causal attributions in your models. So knowing the true causal relationships makes a difference. So trying to give a more practical view to this, let's say if you had a data set that had data related to, say, some heart condition. Let's say you wanted to predict heart disease risk from a bunch of different parameters. Right? So let's assume that this is the causal graph, that these are the ways in which the variables were related to each other. If you simply took a standard random forest and ran it on this particular data set and used the standard post-hoc explainability method, you would notice that the variable with the highest attribution is blood pressure. But clearly, blood pressure is not causally responsible for a heart disease risk. It's possible that something like BMI could be a confounder for both blood pressure and heart disease risk. So ideally, when you convey the explanation to a patient, you ideally want to give an explanation that's causally responsible for the outcome on which the patient can actually take action. Just giving blood pressure as an explanation may not be practically useful to the patient. And that's what we want to do in this. But coming to this idea of causal regularization with domain priors, in reality, we have a lot of domain knowledge that we actually don't use when we train deep neural networks with just data. And the gold standard for causal knowledge is considered RCTs, randomized controlled trials, are considered the gold standard for causal knowledge. And if you take a medical domain, you have a lot of literature on such causal priors provided already. For example, we would know in this particular case that the body mass index has a U-shaped relationship on heart disease risk. This is documented through randomized controlled trials. This is available domain knowledge to us. Is this the only one? Not really. You have known relationships between age and heart disease risk, known relationships between smoking and heart disease risk, known relationships between cholesterol and heart disease risk. Right? The question that we are trying to ask here is, how do we ensure that when you train a neural network, it respects this attribution that's known to you and maintains that during the training process? Right? So is this the case only with medical kind of applications? Not really. You could have maybe a model trying to predict a college admission score, where we know that the student's test score has a monotonic relationship on the output. We know it, right? But this is something that we don't try to enforce when we train a neural network model. Right? It's a domain knowledge, but we don't try to use it per se. Or you could have fairness constraints, where you want an input to have zero attribution on the output, right? So that also is an inherent case of the same approach. And you could have any other nonlinear function, U-shape, J-shape, whatever nonlinear function you want. You could have that as domain priors. So the question that we try to ask is, how do you ensure that these causal domain priors are maintained in a neural network while you train the model? Ideally speaking, if you had such domain priors, you should need lesser data to train the models because you already know the relationship of certain variables in your ecosystem. So our approach to doing this is called causal regularization, where we take a causal domain prior and we want to maintain the relationship of an input variable on the output to be equivalent to the causal domain prior that's given to as input to the system. So that's what we refer to it here. So to explain our method, I probably need to go into one more level of detail, which is causal effect per se is defined as the effect is given as the effect of a predictor on an outcome. And there are two kinds of causal effects that we typically talk about. One is a direct effect, where the predictor has a direct impact on the outcome, and an indirect effect, where the predictor has an indirect effect through a mediator. Right? And the total effect is the sum total of your direct and indirect effects. That's quite straightforward. So if you take the example that we just saw, BMI could have a direct effect on heart disease risk, whereas family history and age could have indirect effects on the heart disease risk. The question is, how do you ensure that your model, your neural network, can respect these kinds of causal effects while training in the model itself? There's one more piece of definition that I have to introduce. Even within a direct effect, causality literature talks about two kinds of direct effect. One is called a natural direct effect, and one is called a controlled direct effect. In the interest of time, I'm not going to get into these details. But what we show in this work is that we can regularize a neural network model to maintain these causal attributions that are given as domain priors in three different scenarios: for direct effect, be it natural or controlled, or total effect. We also show in a later work that was published this year that you can also maintain indirect effect also through a neural network, but I'll come to that a bit later. For the moment, I'll talk about direct effect and total effect. Okay. So the controlled direct effect is said to be the causal effect of a variable on an outcome when all parents of the outcome except the treatment are intervened to some predefined control values. Okay, that's standard definition from causality literature, and this is the definition that's given. So the first thing that we show in this work is that the control direct effect is actually identifiable in a neural network. Okay, that's the first thing that we show. And identifiability is a condition that permits to measure causal quantities from observed data in causality parlance. So the first thing that we show here, I'm not going to walk through the derivation here, is that control direct effect actually turns out to be identifiable inside a neural network. Okay. And once we similarly show that you can also show the identifiability of the natural direct effect and total effect also in neural networks. But the interesting part comes after this is, once we know it's identifiable, we show that the regularization of this control direct effect on a neural network happens to be you can show that the matching of that domain prior turns out to be equivalent to matching the nth partial derivative of the Jacobian of your neural network. And that what that leads to is a simple regularizer to your neural network loss function, where you simply match your gradients of your domain priors with a masked with your masked matrix of specific elements of your Jacobian for which you have your domain priors. You simply just have to match the gradient of your domain prior with the corresponding elements of your Jacobian, and we introduce a simple margin kind of a loss to know to what extent you want to do this matching. Okay? And just adding this simple loss to whatever empirical loss that you want to use to train your neural network helps maintain the causal attribution that's provided before training the model. So the idea here is to do explainability anti-hoc, which means you know some explanations that hold from domain knowledge. How do you maintain that while you train a neural network is what we try to do in this particular work. So the overall implementation is fairly simple. While I had to introduce all of this to convey what I had to say, the final implementation is simply just add one loss function to whatever loss you're training a neural network with. Okay, that's all the implementation turns out to be. What is the use of this? We show it on multiple different data sets. This is on the heart disease data set itself. You see here 3 curves. One is ERM, which is your standard empirical risk minimizer through which you train your standard neural network model, whatever loss function, in this case, binary cross entropy or least square loss. The ground truth is what we expect the relationship between that particular input variable and the output variable to be. And you see here that the ERM model, which is green, I think, which is green, does not respect what the ground truth should be, but our curve here, which is blue in color, actually maintains the ground truth even after training the model. And all of this comes with no loss of accuracy. We show this with a few other data sets. I'm not going to go into each of them, but let me just show you one of them here, which is a data set called Mehra, which is on environmental, it's an environmental data set, where we once again want the ground truth to have a certain relationship, which is the red curve here. While the ERM model does not maintain that particular relationship, we show that adding our regularizer gets closer to the ground truth attribution in these kind of scenarios. The more interesting conclusion here is that fairness in such a case becomes a special case of anti-hoc explainability. Because when you want to do fairness, you want to maintain zero attribution. So you simply try to add a regularizer where you say that your domain prior has a zero relationship, and you ensure that your Jacobian matches the gradient of that domain prior, and that helps maintain fairness in scenarios. So this is the recidivism dataset where we show that on the x-axis you have race, African American here, y-axis is recidivism. You see here that an ERM model, which is green in color, keeps increasing the recidivism output with an increase in the African American variable, which is not expected. But the blue curve here, which is our model, gets closer to the ground truth in terms of giving a flat curve, and that happens for other races too. If you're interested, the code and the paper are publicly available. Just a quick follow-up of this work, where we also showed that you can also maintain indirect effect using these kinds of neural networks, is a recent work that was published at XAI 2024. I'm not going to walk through the details, just give a high-level perspective. This is joint work with students Gautam, Saket, and Vashneya. And in this particular work, we try to understand to see, can you also try to maintain indirect effects between variables in a neural network when you train it? Can it be done at all? It's a question. And the first thing that we show in this work is that it cannot be done as long as you don't have lateral connections between the input neurons of a neural network, right? If you don't have lateral connections between the input neurons of a neural network, we show kind of an impossibility result that you cannot capture indirect effect in that kind of a scenario. So this is just an example to say that indirect effects such as family history and age can be captured using such a model. So the overall idea here is that while we have the true causal graph and a standard neural network, we use a two-phase training strategy of a neural network, where in the first phase, we train a neural network as is in a standard way. And in the second phase, we introduce lateral connections between the input neurons of a neural network, and then try to enforce indirect effects that maintain known indirect attributions. Okay, I'm not going to take more time on this. If you are interested more, the paper and the code are openly available. Just to conclude with a few thoughts here, I know the whole day has been about explainability. There have been different facets of explainability that's been spoken about. But I think the biggest elephant in the room, perhaps, is the definition of explainability itself, right? The elephant in the room seems like the proverbial elephant that's felt around by 5 blind people, one of whom thinks it's a snake, a rope, a pillar, so on and so forth. And depending on whether a person is a business owner, a data scientist, an IT ops person, an auditor, or a customer support agent, explainability means different things to each person. So I just wanted to end the talk with one open note, is that the last few years have led machine learning and deep learning models come closer and closer to the human-machine interface. Until a few years ago, machine learning predictions were a removed entity, right? So they predicted, you use them much later or in whatever ways you wanted to use them. But as we start interacting with machines, this the explainability in particular has brought the technology closer to the human-machine interface here, which means you need more porosity and mechanisms for specifications of requirements, more participative system design and test cases before you start building your machine learning models when you talk about explainability. One way you could see this is the automation revolution that we went through software development has a very well-defined process where you begin everything with user requirement specification. Unfortunately, with machine learning models, we really don't start formally that way, right? But depending on what explanation a particular user wants, maybe it's time for us to think through and come up with ways in which, processes in which users can specify the requirements upfront. Someone may need an explanation that's an attribution. Someone may need an explanation that's in visualization. Someone may need an explanation that's an exemplar or a prototype, right? But that's something that the user has to specify depending on a particular application context. It perhaps is time for us to have well-defined user requirement specifications upfront, test cases upfront, validation metrics upfront, and then start building machine learning models and use your explainability methods that cater to those specific user requirement specifications. I think I'll stop here. Hopefully I finished within the time and it was of some relevance to the full workshop. Thank you again for the opportunity, but happy to stay behind for questions.
Thank you for your response. All right, are there any in-person questions? Come to the mic. I'll pull out one of my handy dandy. Okay, do you have one? Okay, cool. Come on.
Great talk. I had a question. You talked about models learning the causal structure. How? My question is there a metric that you're measuring? Or that's not relevant to the context?
We don't learn the causal structure. I was just giving that introduction to define the terms for causality. We only assume that certain causal domain priors are given to you in the form of functions. Right? So it may not even be well defined. Somebody could just tell you, let's say I was a domain expert. I could tell you that I know that this variable should have a monotonic relationship on the output. I know that much. So which ideally means that when we train a neural network or a model, that model should respect that monotonic relationship, right? So that's all we do at this point. We don't really try to learn the full causal graph. In fact, our approach works even if you're just given partial domain priors. It's just for a few variables. So what it would do is it would maintain those attributions, and for the remaining variables, it would just learn correlations the way it should learn. Right? So just.
Do you measure that monotonic relationship? Or...
Yes. So obviously, in this particular case, we are going to assume that for those, the user has the domain prior, so we can check at the end whether with your model, what the model has learned matches that particular domain prior. I mean, there's a little bit of more deeper technicality to it. I didn't go into those details. So we had actually an earlier work for this, before this work that we had done was on how do you measure the average causal effect inside a neural network was an earlier work that we had done. So we actually used that metric to measure whether the average causal effect between an input and an output variable in a neural network matches that domain prior that the user had specified. Okay, that's the way we do it.
Thank you.
Thanks very much for the talk. So I was just wondering about the regularization and how does that apply to sort of image-based method? The images are out of the variable, how do we even do that?
No, that's an interesting question. I kind of glazed through that part to say that this has nothing to do with images. But I thought this was an interesting perspective to bring to the audience. I think the tricky part about data like images and NLP and probably related, it's a lot easier to show these things with tabular data. The tricky part about images, NLP, and similar data is that your observed variables and your reasoning variables are different. Right? So I do think like concept-based approaches could be one way to bring them together, where you first learn intrinsically interpretable models, where you have some shared intermediate semantics. And now on those variables, you can compute the causal effect. So one thing I should add here is our approach can work with any neuron and any neuron. We just study it with input and output because that's what matters. But you can even take an intermediate neuron and study the causal effect of that on the output neuron. So once you start having intermediate semantics, which is where you could do it with vision, you could probably, doing it at a pixel level doesn't make as much sense. But then once you go to an intermediate step where you have some concepts and latent representations, you can do a similar.
So like maybe doing those segmentation, semantic segmentation, and then using those.
Sure. I think there are multiple ways of doing it. Segmentation could be one. Having a variational autoencoder and learning some latent representation space which generates the data, and now reasoning on those bottleneck representations could be other. Learning concept-based representations and reasoning on those concept-based representations towards the output could be other. So there could be many ways of doing that. So the framework as such is general.
All right, yeah, just.
Thanks for the talk. So this is just pure curiosity because it's highly improbable. But have you ever made like a series of experiments where you look if a model with no information about the causal model trained somehow follows a pattern where you choose some hyperparameter in some way that it actually gets the causal model better than another?
Absolutely, very much, right? So it can happen. So in fact, probably I would say that some of our experiments that we ran, it happens very rarely though. I mean, I showed some curves where the ERM model, which is the standard way of training neural networks, was way off what the ground truth should be, right? We did find occasionally that it would go close to the ground truth. So it does happen. It can happen. But this would be an approach to kind of guarantee it, right? So that's what this approach would.
But there are no like even heuristic thoughts about why that appeared.
I think that's pure chance. Okay. Because it depends on where you initialize your model and how you train. That's pure chance. I think that is the benefit of this approach, that you can actually guarantee that using this kind of an approach.
Thank you.
All right, and then were there any virtual questions? Okay, cool. So we'll wrap it up in another round of fun. Just gonna wrap with some closing remarks and feedback. Okay, so thank you all for attending this workshop. We really appreciate your attendance throughout the workshop or part of it. It was really a fast-paced but really fun experience. So yeah, I mean, we've had a lot of good talks and also posters I'm seeing, particularly about like counterfactual seems to be a theme, and also birds. I see a lot of birds popping up everywhere. So yeah, we're getting into other domains. So we'll stay a couple of minutes to get any field any questions. So feel free to come up and ask us. But also, I want to draw your attention to this link. Sorry, let's just do it that way. Attach this link right here, which is a feedback form. So you can either scan the QR code or type in that URL. So basically, we want to get your feedback about what went well, what didn't, and also if you're interested in becoming an organizer next year. So you know, we're definitely going to be on the lookout around August or September. So yeah, we'd love to hear your feedback, and thanks again for attending. Have a good rest of your day. Thank you. Should I end the Zoom?
Thank you. Stop sharing.
Yeah.
Of course.
Oh, okay, sure. Well, make sure you like send it to. We're gonna make a folder, a Google Drive folder of photos. So, yeah. Let's just stay for a few minutes here first, and then.
I stopped sharing.
That's fine. Hi. Yeah, it's really fun. One more chat. One day for the picture, is that going to be posted? Yes, exactly. I'm going to make a Google Drive folder and then I'll share them out. Yeah,
Cool,
don't worry.
thank you.
Just wanted to thank you guys. Yes. Thank you. We had it is a ton of work. Thank you. There's a ton of emails. I'll say that. But yeah, thank you for attending and presenting as well. Yeah, absolutely. This is great.
Yeah.
Okay, are we doing it up here? Okay, let's it's okay. Just stay. Let's make a nice background. Photo credits is not okay.
People do that anymore. I just care.
Exactly, that's what I'm gonna do.
All right, let's do it against that background.
Yeah.
I don't know if the light is from the back is gonna
You
like.
can pick that up.
Okay, we could turn up the lighting. We can just go on here.
Okay, so straight to Germany. Don't let the conference end and then just go. Look, I'm looking around because I heard this on the TV. So I see your like 10 years yeah. I'll come back. Yeah, you can be going. They didn't need to get back to me. I feel like I will do.
Yeah,
I'll
be back in an hour.
Yeah.
Right. So, yeah, let's just hang around for about 15 minutes.
So we still need to be on Zoom.
I'm gonna leave on Zoom just in case anyone has any chat questions. Hi, all. I'm going to be ending the Zoom now.